everyone, welcome to this course on machine learning using Python. Today, machine learning is becoming a part of almost everything around us. From movie recommendations, fraud detection to price prediction and smart assistant, machine learning helps systems learn from data and make better decisions. And that is exactly why this skill has become so important now. It's no longer just for researchers or data scientists, it is now one of the most useful and practical skills for anyone who wants to work with data and intelligent systems. So in this course, you will understand how machine learning works using Python, which is one of the most popular language for building machine learning models. So we will start with the core concepts, then we'll move into regression, classification, also understanding how to evaluate and improve models properly. So if you want to build a strong foundation in machine learning in a very simple and practical way, this course is a great place to begin with. So let's talk about what we have covered in today's video. First, we'll understand what machine learning is, how it learns from data, and how the basic workflow works using features, labels, training data, and test data. Next, we'll look at some important concepts like overfitting, underfitting, so you can understand why some models perform so well and others do not. Then, we'll move into regression, where you will be learning how models predict continuous values using techniques like linear regression, lasso ridge, and polynomial regression. And after that, you will explore classification, where you will understand how models predict categories using methods like logistic regression, KNN, decision trees, and SVM. We'll also cover model evaluation using metrics like accuracy, confusion matrix, and mean squared error. And finally, you will see how to improve model performance using grid search, cross-validation, and pipelines. Also, if you're interested in mastering the future of technology, then the professional certificate course in generative AI and machine learning is the perfect opportunity for you. This is offered in collaboration with the ENICET Academy, IIT Kanpur, and it's an 11-month live interactive program providing you hands-on expertise in cutting-edge areas like generative AI, machine learning, AI tools like ChatGPT, DALL-E 2, and Hugging Face. You'll also be gaining practical experience to 15+ projects, integrated labs, and live masterclass classes delivered by esteemed IIT Kanpur faculty. Alongside earning a prestigious certificate from IIT Kanpur, you'll be receiving official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So what are you waiting for? Hurry up and enroll now. The course link is mentioned below. Now, before getting started, here's a quick quiz question for you. Which type of machine learning problem is used to predict a continuous value like house price? Your options are classification, regression, clustering, or filtering. Let me know your answers in the comment section below. So without any further ado, let's get started.
What machine learning is, which is a subset of artificial intelligence, right? That's basically machines learning from data in order to make decisions, essentially. So this was a big departure from the rules-based systems at the time, right, that were explicitly programmed to make decisions. So just think of an example like a really big kind of if this, then that, then that, then that, and else if this, right? So a bunch of rules that had to be pre-programmed in order to come out with some final answer. With machine learning, it's the exact opposite of that. We're actually training something from examples from existing data in order to predict something or make some type of decision. And so we're going to learn about the various ways we can do machine learning. But if you guys remember, we talked about some of this, like the differences in the basically rules-based approaches to learning from data approach. And included in that is going to be complex unstructured data. So things like images, text, audio. What handles those really well is deep learning, which we will get to in the course after this. But those are certainly in there as learning from data, even complex data. So we had this picture, and I think this is kind of around where we left off last time, was just distinguishing between those three terms. We see artificial intelligence, deep learning, and machine learning kind of used interchangeably, but this is really how they fit in. Artificial intelligence is kind of a broad, anything mimicking human intelligence, which doesn't have to be learning from data, but machine learning is part of that. And then one way to accomplish machine learning is to use neural nets, which is the focus of deep learning. And so deep learning has found a lot of success, especially recently, with those complex data types like images, speech, text, right? So deep learning used all over the place, even in modern like generative AI, we see deep learning used quite a bit. It really anything that's using neural nets is going to be deep learning. Um, and again, we'll focus on that later, but we're going to be mainly focused on machine learning for this course, primarily machine learning that does not use neural networks. Okay, so just models that are not necessarily neural networks be our focus. So in machine learning, we had an example of a game, essentially learning what decisions to make based on the kind of current state of the board. This could be a machine learning example that learns from many previous examples. So a lot of data around these games are used to train these kind of robots that can play these games and play them at a very high level. So there's been a lot of successes actually in machine learning and deep learning around uh, playing games like chess or Go using machine learning algorithms. So pretty cool. All right, so I think this is where we ended. Last time we said there's a bunch of different use cases for machine learning. So recommendation system is going to be a big one, and we will actually study that in one of our final lessons of this course. Chatbots, like generative AI doing sentiment analysis, chatbots we'll study later, but those are certainly an application of learning from data in order to generate responses to text prompts, right? Spam filtering, that's a good example, like classifying an email as spam or not spam. That gets trained from examples and learning from data, such as previous emails. Social media posts analysis is another kind of text data use case, but you can do a lot with that text. Like you can predict the sentiment, you can predict the category of what the post is talking about. Those kind of things all can be done with machine learning. And many other use cases not on this list that we will cover, as we go further. Okay, so this is where we kind of left off. So what's doing all the
Yeah,
hard
and
work
its
here
classes and all
is
that
the
important. It's interesting.
machine learning algorithms. So these are things that will learn from the data. So they are basically um, algorithms or sets of rules that or mathematical rules, I should say, not formal rules, like in the sense of a rule system, but mathematical formulas and mathematical rules essentially that help us learn from the data. So they correlate the data to some type of outcome. So some type of prediction, whether that's going to be, as we will see, whether that could be like a number, like we're predicting a price or demand or sales, or it could be a category, like is this transaction fraud or not fraud, or what's the probability that this is fraud? So we have different kinds of predictions we can make with machine learning. Um, but we will study the kind of the differences of those coming up. But machine learning algorithms are really what power, they're kind of the models, right? They're the models that help power machine learning to actually learn from data. So we're going to spend a lot of time in this course studying those algorithms, like the different models that we can build and what their differences are, what their strengths are, what their weaknesses are. We'll learn a lot about those. Okay, so as you can imagine, like everything is so data dependent, right? We're learning from data, so it makes sense that the quality of data really, really matters here in determining how strong the model can be. So you see this graph here charting kind of the high quality data versus just any old data, but a decent enough quantity of it. You can see that performance, and the performance is measured by some evaluation metric. So think of it as something like an accuracy. Like if we were predicting fraud or not fraud, how accurate can our model get at actually detecting fraud? Um, it gets better and better and better. And this graph shows that the higher quality of data that we have. So there's kind of that there's a saying in machine learning called garbage in, garbage out. What that means is if you have poor data, even the best model in the world, poor data is not going to result in having a good model that can be accurate and perform well. So it needs to be high quality, meaning there needs to be a decent amount of it, and it needs to be labeled appropriately, as we'll talk about. Um, and it needs to not have any, significant outliers. It needs to be clean, not have those missing values. All of those things, you have a good chance at deriving good predictions from higher quality data, as this kind of shows. Okay. So one thing we're going to learn as we go along is quantity matters as well. So not only quality, but a decent amount of it. And we're going to learn those kind of rules of thumb, like how much data do I need for certain algorithms. Um, One thing that we will see is that the basic machine learning models that we'll study don't need as much as a neural network would. Neural networks are going to require a lot more than a basic learning model. So that's something we will see as we go along. But this is something we'll talk about and discuss with each model that we study is kind of how much data do we actually need to produce a high quality model. Okay. Any questions so far? Okay. Let's talk about the different types of machine learning that we're going to discuss. There's going to be two primary ones that we will study in this course, and then a couple others that'll be a little bit more advanced that we won't get to, but worth knowing about. So there's going to be four total that we'll study or talk about, and they'll be on this list here, which is supervised learning and unsupervised learning. Now, I'd say the majority of our focus will probably be on supervised learning, and we'll talk about what that means. But we'll also cover unsupervised learning as well. And so we'll look at the most popular techniques in each of these types of machine learning. Um, and then we'll talk about these two, but not really study them because they're more advanced topics that will be beyond the scope of what we'll do. But these are going to be different styles of machine learning that are going to be characterized by um, what kinds of predictions they make, what kind of data they need and require, um, and what kind of outcomes they're actually producing. Um, so let's get into each of these. But the one that we'll probably spend the majority of our time on is going to be supervised learning, but we will study unsupervised learning as well. We'll study both, and we're going to define both of those coming up. And again, these will be a little bit more advanced topics that we won't spend too much time on, but we'll discuss their relevancy in machine learning um, and give a good definition to it. Okay. All right, let's start with supervised learning. Now, this is going to be a term that really refers to using examples. So using labeled examples. So here we say labeled data to help our model train. In other words, help our model be able to predict guided by specific input output pairs. So supervised really refers to the fact that we have answers, we have examples, we have answers with those, and we use that collection of data to build our model off of so that we can predict those kinds of things like a price, like a category, like a spam, not spam. In this slide, like we would be predicting if this shape is a square, a triangle, or a circle. Um, but but when we build a model for that, we have data that has an answer attached to it, right? We've talked about this before a little bit with labels. So there's a guide there that can guide us towards building our model. There's an actual every example has an answer, and that answer is really critical to help build our model off of. So that's it's almost like you have a bunch of exercises in, let's say, like a math textbook. You have a bunch of exercises and you have the answers, and that way you can kind of check your work. You think about model training, that is really a lot of that process of model training, as we are going to discover, is basically checking our work against these answers in our data, in our training data. Okay. So supervised learning is any type of machine learning that involves learning from labeled data in order to predict outcomes. Okay. Predict outcomes. Like now the outcomes can be numerical. They can be like a price, temperature, demand, sales, revenue. They can be numerical, but they can also be categorical. So they can be like spam, not spam, fraud, not fraud, cancer, not cancer. Um, Dog, cat, giraffe, those kind of categories. We could predict those. It's some type of outcome. Okay, some type of outcome. The key is we're using labeled examples to guide our model building. That's why it's called supervised learning. So we know in our data, we know what the inputs are, of course. Those are going to be, think of the inputs as like all of our columns, and then we have a special label column that represents the output we're trying to predict. So if you think about that housing price data, the label could be the price. And that's something we would build a model to predict. But we have answers for all of our examples in our rows. We have answers to help guide our model building. They help tweak our model because we know the answer ahead of time. So they're really good examples to build our model off of. Okay, so that's supervised learning. And this example is circled not in the prediction because it's not part of the test data, even though it's in the labeled data. No, it just not necessarily. It just means that like we learn against all of these examples that have these answers. And then when we observe new examples, we can try to predict what those would be based on what we've seen before. So if there was it's just a coincidence. We only have two examples in our test data. Like we could have a circle here, in which case we would predict circle. That's fine. Or at least we would hope our model would predict circle, right? That's what we're hoping. May or may not get it right. Um, but it's only not there because we only like we're just assuming that we only have two examples we're testing against. But in reality, we would probably do a lot more than two. It's just a coincidence, really. In reality, we would test against a lot more data. And we're actually going to see why we would do that. Like, why would we train our model and then kind of use additional data to evaluate it? It's actually really important that we do that step to get a sense of how good our model is before we take it out in the real world. So if we apply our model that we build on our label data to this kind of set of test data that we haven't been exposed to before, it helps give us a sense of how good is our model. So it's test data is usually used for evaluation. So that's something we'll study. How do we train? It depends on the model. So training will be an algorithm that will basically update the model according to the data, these labeled examples. Every model is going to be different in exactly how it trains. So we're gonna talk about that when we get to the individual models that we'll study. But loosely speaking, they're going to use the data to adjust itself. Like imagine adjust like tuning a bunch of knobs. Um, like the best example I can give you is I think I did this one last week where you have kind of a function that predicts the price. And let's say it has weights like weight one with feature one, weight two with feature two, weight three with feature three. So imagine we had three input features and we built an answer according to that. Essentially, what we would do to train the model is adjust these in order to get this correct based on our labeled examples. Okay. So that's something we're going to learn about coming up shortly when we actually dive into model. Every model is going to be slightly different in how it trains. But at a high level, it's going to use the training data with those examples, right? The labeled examples to help guide the formula essentially to adjust to generate the proper kind of model here. These things are going to be adjusted according to the data in order to produce the correct output. So think about these as knobs that will turn. Okay. Which type of machine learning is used? Probably supervised, which is what we're talking about now. So probably supervised because most people want to um, build some type of model to predict something. So yeah, I'd say supervised. Yes, we are definitely going to learn how to train. Yeah, we'll see, we'll do the code. I'll tell you about how it's done. Yeah, we're definitely going to learn it. But what I was saying is that it's kind of on a model by model basis. So I want to wait till we get into the individual models, then we'll talk about how they're trained. But yeah, we'll learn how to do that. But yeah, supervised is used all over the place. Even for generative models, they use supervised learning because like an LLM is going to use labeled examples in order to train, right? In order to train how to generate responses according to prompts. Um, it needs to learn against a lot of text examples. So that supervised learning is what results in that model, right? Learning from those labeled examples. Okay. It is, yeah. A lot of image processing is supervised, like object detection. So the YOLO model is an object detection model, yes. Because it has to be trained, right? Uh, it has to be trained on images with labels such as this is what object is in this image, this is the box around the object. Yes. So if if it ever uses label data to train and build the model, it is supervised. So YOLO is definitely supervised. And we will cover the YOLO model later on in our deep learning course. We talk about object detection. So we'll study that. But yeah, it's supervised. Okay, so on the slide we have some common supervised learning algorithms that are we will study. So all of these we will study and understand what they do and how they work, but just giving you some to name them. Linear regression is kind of the one I just drew out, which is this is the prototypical, like easiest to understand model that is kind of the exactly like this, where we have a weight times a feature, a weight times a feature, and then a weight times a feature, and on and on and on. You can have as many as you want. Um, that is a linear regression, and so that's a supervised model because we need this value here, and we need all of our inputs in order to actually train this model and generate all those weights. Um, that that uses labeled examples to help tune all those knobs. Same with all these other models. So we're going to talk about decision trees. We're going to talk about logistic regression and SVMs, which are support vector machines. We'll talk about all of those, but they're all examples of supervised learning. Okay, we'll talk about all of these. They're all supervised because they all require labeled examples in order to train them and then subsequently use them. Okay. Okay, so what are some use case examples? So for instance, in supervised learning, we may be predicting temperature based on yearly temperature trends. So we would have that yearly data as our labeled examples, and those would supervise the learning of a model that predicts temperature. Same thing with predicting crop yield based on seasonal crop quality changes. So maybe we have a bunch of features relating to crop quality. We could predict crop yield. We would just need historical examples with those labels, right? What the crop yield is for each time period, let's say. We would just need those supervised examples and we could easily build a model off of it. Um, this last one, sorting waste based on known waste items and their corresponding waste types. That's kind of like spam. It's like filtering basically, like a spam filtering. So think of it like the shapes example. We sorting things into squares, circles, triangles. Same kind of idea here, where we have a bunch of examples on what those waste items should belong to, like what waste bins they would go to, for example. Um, and those could be labeled, and therefore then we could understand what category of waste they belong to. Same thing with spam. Something is fraud or not fraud, spam or not spam, cancer or not cancer. All of those are going to be supervised learning examples because they're going to require, in order to train them, they're going to require data that has those labels. Okay, so anything that has labels is going to be supervised learning. So again, this is where we will spend probably the majority of our time is doing supervised learning problems. Ones that we have labeled data, we're building a model and we're going to predict those labels essentially. Okay. Before we go to unsupervised, any questions about supervised? Okay. All right. So supervised requires labels in order to have an example to go off of to build your model. And that's because you're predicting those kind of outcomes like spam or not spam, cancer or not cancer. Now, unsupervised learning is completely different. It's the opposite. So, unsupervised learning is where we do not use labels whatsoever. So, we're not using any labels at all. So, it can be completely unlabeled, or even if it's labeled, we're not using labels in any way. But we primarily would say it's unlabeled data. We have no guidance because we're not using the labels in any way. We have no guidance to predict anything, but that's because we're not really predicting anything in unsupervised learning. Generally, what we're doing is looking for some structure or pattern. Okay, with unsupervised learning, we're looking for some structure or pattern. So, one type of example that's very, very popular is going to be this second one, which is identification of user groups based on similarities or commonalities. Now, this is going to be a problem basically known as clustering, and it's a problem we will study quite a bit. There's going to turn out to be lots of different algorithms that can accomplish clustering. So what clustering attempts to do is basically say we have data that's like this, and then data over here, and then data over here. Let's just group these together. So like this should be one group, this should be one group, and this should be one group. And we can find those structures and say, okay, this is group one, this is group two, and this is group three. One, two, three. And we can basically build what we would call clusters of data based on how close together the points are kind of located in these kind of cluster zones, like these boxes I've drawn. Okay. Now, that doesn't require any label to do, which is really fascinating. So, unsupervised, you don't need any label at all to accomplish the algorithm. So clustering is one good example. Finding outliers or anomalies is another. So we don't necessarily have any label of what is an outlier or what is an anomaly. We are deriving that from the features alone. There's no guidance, there's no label to doing like outlier detection or anomaly detection. Okay, so that's another good example. One that's not listed on here but is also really important that we will study is something known as dimensionality reduction. So dim reduction. And what this focuses on is basically compressing the data set a bit. So we take our data and basically compress it but we do it in such a way that we retain as much information as we can. It's a very like smart compression. And what it does is it lowers the dimension. Think of the dimension as like number of columns. Number of columns. So imagine we had 100 columns in a data frame. What we could do is actually reduce that down to 10. So like 10% of that. So we reduce it down to 10. And but those 10 are, it's not like we chopped out 90 other columns. We smartly kind of compressed all that information into these 10 new columns that are compressed versions of the 100 that we used to have. So dimensionality reduction is another unsupervised technique. It requires no guidance, no label to do, but is a really useful technique to reduce the size of your data if you're doing things with it. So this is another one that we'll study how to do it and basically more details behind it, what the algorithms are. So probably those two in unsupervised, we'll spend the most amount of time on clustering and dimensionality reduction. And supervised, if some data is present but we didn't label it, means an example, we had circle, triangle, square. In the training data, we add pentagon. But we didn't label that in that case. Yeah, so every in supervised learning, every row, think about it as like every row in our data frame needs to have a label associated to it. It needs to have a column that represents the label. So if we've never seen Pentagon before, I can't use that as a label. So the Pentagon has to exist in the data if I'm going to be able to predict it. Right, so it can't predict, right. If we've never seen it before, we have no examples to go off. We have no guidance. So how could we predict that? Right. We can't predict it. If it's in there, so if we have labels of Pentagon, let's say, then yeah, we could predict Pentagon. We could remove what? We wouldn't, if it was talking about the Pentagon, we wouldn't remove that. No. Let me go back to that page. We wouldn't remove it. Um, it's just if it's not in our labels, we're not going to be able to predict it. So Pentagon's a good example here. Uh, Pentagon is not one of our labels. So it currently is not in our data set as one of the labels. We only have data that's either a triangle, circle, or square. We don't have Pentagon. So I would never be able to predict Pentagon. I'll never be able to do that if I haven't seen examples of it before. Okay. But let's say we had that in there. So we had Pentagon. So if we had Pentagon, we could have an example of it in our labels. And then yeah, it could be then we could predict it. Yeah, yeah. The don't worry about the test data. So the test data is just saying here's a shape. What is it? Okay, that's a square. Here's a shape. What is it? Okay, that's a triangle. And we could have as many of those examples as we want in our test data. So we could have a circle and say, okay, what's this? Should be circle, right? The test data can be whatever it wants. But yeah, if we've never seen Pentagon before, we're never going to be able to predict it. These are the label data and labels are basically the talking about the same thing. The labels just mean what are the categories that are present in our data. So in this data, we only have three labels that are present. So the are relative to our label data, right? It's saying what labels, excuse me, what labels do we have in our data? And we only have those three: circle, triangle, square. So Pentagon would not be part of those labels. We couldn't predict it. No, so unsupervised is not going to make a prediction. That's the big difference with unsupervised. They're not going to make a prediction like this. So unsupervised is not going to make a prediction. It's going to do something different, like basically say like these guys are similar, these are similar, these are similar. This is a cluster, this is a cluster, this is a cluster. It's not going to make a prediction. That's what supervised learning does. Clustering, yes, which is unsupervised. Yes. Clustering does not require any labels. Unsupervised just means we don't have any labels. We don't require any labels. So the other thing unsupervised might do is it might say, and again, without the labels, it might say that this is an outlier. It might say that this guy is an outlier because there's only one of those and they're not like the other. So that's something that unsupervised could do. It yeah, yes and no. It kind of labels a cluster in the sense that it would basically assign a number to it. Like this is cluster one, this is cluster two, this is cluster three. It'll assign a number to it, but it's not a very meaningful. It doesn't assign like a prediction label in the traditional sense of a label. It does provide like a numerical index for the cluster because what we want to know is like, okay, this guy has the cluster one. This guy belongs to cluster one. This guy belongs to cluster one. This guy belongs to cluster two. This guy belongs to cluster two. Does that make sense? So there needs to be some like index of what cluster you belong to. So it's kind of like a label, but not in the traditional like prediction sense. Okay, very good. So again, unsupervised, no labels. You're doing things like identifying clusters, identifying outliers, doing dimensionality reduction. These are all like structure and pattern oriented things. They're not predictions of a label. Okay, they're not, which is what we would see in supervised learning. Okay. So an example would be that we put in the data, we can group together data such as images into categories based on similarities, which would be like those clusters. So these would be groups that we don't have any label on ahead of time. Like we don't say that this image should belong to this image should belong to this. We derive that from the characteristics of the data. So think like a good example is customer groups. So we would identify customers based on like, okay, do they have similar spending levels? How many days do they go shopping in a week? How much money do they spend? And we could kind of group together customers based on similar qualities. Clustering will find those groups that should exist. It will discover those groups based on um, the similarities in the data. But there's no labels that say like this person should be in this group, this person should be in this ahead of time. There's no labels of that. It gets derived during the algorithm. It's unsupervised, right? There's no unsupervised really literally means no guidance. There's no guidance to doing it. We just derive that from the structure of the data, which is the similarities. Okay. All right. So a couple more for you. So we had supervised, which uses the labels. We have unsupervised, which uses no labels, looking for structure. And then we have something that's kind of in between, which is what is known as semi-supervised learning. And this is where you use a combination of a little bit of labeled data, but most of your data is actually unlabeled data. And you try to get some use out of that labeled data in order to build a model out of it. And so it uses that label data to um, generally provide some guidance on usually what happens with semi-supervised learning is you use your label data to kind of predict what the label should be for the unlabeled data, and then you can go from there. So you can create artificial labels on this unlabeled data and then you can use all of it once it's all been labeled, kind of like a supervised learning approach. So, but this is semi-supervised basically refers to the fact that you start out with most of your data not being labeled, but you do have some labeled examples. And what you can do is basically extrapolate those labels into the unlabeled data set and then provide some artificial labels. And then now everything has a label, you can do supervised learning. Okay. So it falls kind of between supervised and unsupervised. And there, so this is kind of rare. Most of the time, you're not going to do that. You're actually just going to um, prefer to just start with all labeled data. That's usually the preferred approach. Most of the time, you'll actually just be doing supervised learning, not really semi-supervised learning. So it's pretty rare, but it could like if yeah, it could if we had a lot of examples of Pentagon and we wanted and so they were unlabeled and then we tried to guess what kind of shape they were and provide an artificial label and then use that whole data set to build a model off of then yeah, it could fall into this category. Going back to the question, they still use some kind of label data like age, gender. They use those aren't really labels. That's the features. So yeah, they still use the core features of the data. They just don't have any like labels in the traditional sense of a label. Like you should think of a label as something we are trying to predict. So whether that's a price, whether that's like a category like spam, not spam, cancer, not cancer, it's something we'd be interested in kind of predicting. And so in our data, we would have an answer for every row. We'd have one of our columns would be like the result, like the outcome answer that we're trying to predict. That's the label. So in unsupervised, we don't have any of the labels. We do have just the regular features like gender, age, income, square footage, bedrooms, bathrooms, all those things. Okay. So we have semi-supervised that falls in between supervised. Now the reason it falls in between is because there's a decent amount of data that's unlabeled. In fact, a majority of it unlabeled. But what we can do is try to label it. We can try to take what we know from our existing labels and predict an artificial label and then use all that data together in kind of a supervised fashion for a model down the road. So that's kind of what this picture says is we can try to take, maybe we try to infer some labels based on we have some labeled data here. We have most of our data is unlabeled, and we try to supply some labels to it. Like maybe we have a babies category, a teens, a tweens, youth and adults. And then we try, so we take our labels and we try to extrapolate those into artificial labels for this unlabeled data so that we can use it now, because then everything has a label at this point, and then we can just go ahead and do supervised learning from there. So we can do supervised from there. What we would prefer to do and what we'll do in this course is just start with supervised. We'll just start with the labels. We won't try to derive artificial labels usually. We'll just start with labels. So one example in the real world is something like Google Photos, which whenever you take a picture, it can provide labels based on previous images in your library. So it can produce tags or labels on those. Generally, when you take that picture, it's kind of unlabeled unless you go in and specifically provide some tags and some labels. But if you don't do that, it can still make it can artificially create one of those based on the other labeled data that you already have. So um, that's an example. Okay. All right. Last one in terms of machine learning. So we have supervised, we have unsupervised, then we had semi-supervised, which is somewhere in between a mixture of having some unlabeled data and labeled data. Now we're going to talk about reinforcement learning, which is completely different. It's completely different than the other three. It's a type of machine learning where we basically learn from interaction with the environment. And you might ask, what are we learning? We are learning what actions to take in the environment. And the way we do that is by reinforcing positive actions that lead to a reward. So that's where the word reinforcement comes from is we basically imagine like a child that's, learning from trial and error. Like they're trying to crawl, they're trying to walk, and they keep falling down. Eventually, they learn how to do it through trial and error, and they might get a reward, or they might reinforce some of those positive movements that lead them to walk or crawl. Um, or they might learn from the penalties, right? They might learn from some type of feedback. So they might learn from falling down, like, oh, that hurts. I should support myself a little bit better, right? Or be a little more coordinated. Um, and so they learn from those actions and their interaction with the environment. Um, so this is a complex algorithm. Essentially, it deals a lot with again taking actions. Usually, when you take an action, something changes in the environment. Then you kind of observe some type of feedback. So think about like a board game where you're trying to figure out what move you should make. Or another good example is like with a robot trying to navigate a maze. So, like, what route should it take? Should it move forward? Should it move backward? Should it move left or right? Those are different actions it can take. Also, like a self-driving car, should it turn? Should it speed up? Should it slow down? Those are all good examples of things that have been trained from reinforcement learning. Yeah, so real world examples would be like in a board game, a reward would be like if you win the game. Or if you like capture a piece, like in checkers or chess, that's a reward. A penalty would be like if you lose the game or lose one of your pieces, that could be a penalty. Um, in a board game, or sorry, in like a robot navigation task, it could get rewards for moving in the right direction towards the exit, or like when it like let's say you wanted to train a robot on how to open the door and navigate a room, you would penalize it for bumping into the wall. You would give it a reward for moving. Usually, the algorithms themselves, usually it's like a step function. It's like a discrete function that kind of is based on the state. So the reward, it could be like depending on the let's go back to the board game example. Like the reward could be like, or even the maze. Let's say like navigating the maze, like getting to this. Let's say this was the exit and this was the entrance. Then if they make it to here, they get a numerical, like if they make it to the exit, they get a numerical reward of like plus 100, let's say. So it's just a number. And then if they if they go into here, like let's say this is kind of like a death trap or like a pit, this would be like a minus 100. So it could be like discrete numerical values could be the reward. If they're moving in the right direction, like let's say we want to encourage going this way, then we could give smaller intermediate rewards. Like this should be a plus. Like if you move forward, this is a plus 5, this is a plus 10, this is a plus 15. If you're moving in the wrong direction away from the exit, That would be like a -5 or a -10. Does that make sense? So they're numerical in nature, and what you're trying to do is collect the most reward. You're trying to get the largest reward you can through trial and error. So you try this out many, many, many times. You basically simulate running through this maze many, many times, and what dictates like where I should go is based on what I've observed in the past. It's almost like you're a child remembering like, okay, what move should I make from this space? Like if I'm here, which way should I go? Should I go down? Should I go right? Should I go left? You kind of know that from experience. Does that make sense? Based on the reward that I've seen in the past. Like when I've moved down, I've gotten a higher reward than moving left or right. That makes sense. So yeah, it's a numerical value is the reward. Yeah, that's a great question. How does it differentiate rewards based on gain and loss, i.e. trust? So it's a very complicated answer, but essentially so in the chessboard, you can think of the board as like every space is a state. So I could be in this state, I could be in this state, and then it's not only is every space, but where all the other pieces are. So there's lots of states that are possible. So the way there's a way to quantify essentially what's the value of taking a certain action, like moving my piece left, moving it right, moving it up or down, given the rest of the state. So you're right. It may be beneficial to sacrifice, but we would learn that through experience. That okay, the best move in this situation is to sacrifice. We would have to learn that through trial and error many, many, many times. Which is to say, like, okay, if I'm in this current state of the world, right, all these pieces are distributed in this way. The best move for me right now in the long run to get the most reward in the long run is to actually sacrifice my piece and move it right, move it into like a bad position theoretically. But we know from experience that's actually the most long-term reward is from that position. Like moving it right may be the best action for me. So what you learn is how to take actions. And actions are usually like move right, move left, move up, move down. You think about like a self-driving car, though, that's going to be like slow down, speed up, turn your wheel 10 degrees, um, those kind of actions. So the short answer is there's a calculation there that you learn what the long-term value of every state is, every unique state. And then you're trying to basically say, what action should I take from that state, given that current state of the world? Okay. And I really like reinforcement learning. It's actually probably my favorite field of machine learning. Unfortunately, we won't be covering it in our main course. We have offered electives around reinforcement learning in the past, so stay tuned. Maybe when we get to the end of this program, we'll offer an elective on it, and if enough people sign up for it, we'll run it. But um, we it's not part of our we don't really cover reinforcement learning as part of our main topics. It is an advanced more advanced topic than what we'll cover, but I really enjoy it. I find it very fascinating. Okay, so all of this is kind of illustrating what I was saying, which is you think of like the thing that's interacting in the environment, like the robot or the car or the human moving a chess piece, is known as the agent. It's interacting with the environment by taking actions, which updates the state of the environment. So that's why you see this word state here. This gets updated constantly every time you take an action. Ultimately, what reinforcement learning is trying to do is learn the best action, like what would be the best action to take. Um, and the best action is the one that leads to the most long-term reward. That's the best action. So you have to learn what leads to a good reward by kind of experiencing this over and over and over through trial and error. So there's a lot of kind of simulation or letting the robot try something a lot in order to kind of learn what's rewarding and what's not. Think about it again, like I think a good example is like with children, right? You kind of have to let them try things until they learn on their own what can they do and what can they not do? What's the best actions, right? So reinforcement learning has made its way into other places. So I said like a good example is self-driving cars or robotics. A lot of reinforcement learning is used there. One place it's found its way into recently is recommendation systems have kind of merged with reinforcement learning. Um, and this is because you can imagine there's kind of a built-in reward for you clicking on a video and kind of watching it. So that kind of reinforces that recommendation. And then that's where um, you can then kind of recommend a similar thing and see if that's rewarding and generates a click or generates some view time or watch time or whatever. So reinforcement learning has found its way into a lot of areas, recommendations being one of them. Because it's just natural for the idea of like, what should I recommend next to generate the most reward? In this case, the reward is kind of correlated to did they click on it or not, or how long did they watch? If they watch for longer, it's more rewarding. Those kind of things. But places where reinforcement learning have been used, I said self-driving cars, games. So one of the most famous examples, if you want to look it up, is the AlphaGo. This was in 2016. The AlphaGo algorithm was a reinforcement learning bot that beat some of the world's best Go players, which, if you're not familiar, Go is a board game that is a little bit more complex than chess. It has it's a larger board, more pieces to it. But there was a reinforcement learning powered bot that actually learned how to play the game so effective it could beat world kind of masters at the games. It was pretty amazing. That's the AlphaGo, and that was by DeepMind, Google and DeepMind in 2016. That was only 10 years ago, not that long. Um, so we said recommendation, even autocorrect, learning to predict like what is the best correction to generate a reward, which would be like you accept that correction or you reject it would be a penalty. So reinforcement learning has been adapted to these kind of problems very successfully. Let's take a look at the packages that we will use throughout. So, of course, we will rely on these three, which we've already relied on to do a lot of things like NumPy to do numerical manipulations and calculations, Matplotlib to do any plotting, and not only Matplotlib, but maybe Seaborn as well, both of those to do plotting. Um, Pandas is a big one because that's where all of our data is going to be manipulated and prepped before it goes into modeling. So all of that stuff we learned from Pandas is definitely going to be applied here in this course as we actually build models. So of course, like these old ones that we've been working with quite a bit, still going to be useful here in the modeling stage. Um, Mainly for different reasons, though, mostly to get our data prepared to do some type of modeling or maybe to visualize it before we do modeling to get a sense of what it looks like, those kind of things. Um, SciPy is sometimes useful for certain processing, like in unsupervised learning, we'll actually use SciPy a little bit to do dimensionality reduction or help us do that. So SciPy will be used here and there, and we've seen it before with hypothesis testing. We use SciPy, like the t-test and z-test came from there. Some of the unsupervised learning stuff will come out of there, but the package we will use by far the most in this course is going to be Scikit-learn, which is here. And we've already seen a little bit about Scikit-learn in terms of its pre-processing capability. So we use the min-max scaler and the standard scaler from there, from the pre-processing module in Scikit-learn. But it has many different models built into it that we can use to help do our training and predictions. So it's a incredibly useful machine learning library. It is the industry standard machine learning library. If you're going to do anything in machine learning, it would be expected that you know how to use scikit-learn. Now, what's really lucky about that is that scikit-learn is a really easy package to get used to. Nearly everything we do in Scikit-learn will mostly follow the same pattern, and so the code will be extremely simple. They did a great job with that package of making things really user-friendly, really simple. It's a really fantastic package, and we're going to get a lot of practice with it as we go along. Every model we build will essentially be from Scikit-learn, and not only like the models, but doing the training, doing the predictions, and then doing the evaluation will all come from different scikit-learn modules. So that'll be really nice, and we'll get good exposure to that package throughout the course. So if anything, we'll come away from this course as scikit-learn experts. So that'll be very nice. So this will be the new one for us, scikit-learn, but we'll get a lot of practice with it. Okay. All right, so just to recap that lesson before we move on to lesson three, we talked about machine learning as learning from data, which is included underneath the AI umbrella, but deep learning is also included under machine learning because it's still learning from data, but it's learning using neural networks. We talked about the four different types of machine learning. So we had supervised, unsupervised, semi-supervised, and reinforcement. So those are the different types of machine learning that are out there. And then we talked about some of the Python packages that we will use, the main one being scikit-learn. And of course, we'll use our older like Pandas to manipulate our data and get it, pass it into our model training, etc. But scikit-learn will be our go-to for anything machine learning. All right. So I have some questions for you guys, some checks. So let me know in the chat, what do you guys think? Which of the following best describes machine learning? Which choice do you think makes the best is the best for this? Very good, very good. I see a lot of choices for A, and A would be the correct choice. So machine learning is definitely a subset of AI. It's underneath that AI umbrella, but of course we're learning from experience, and of course that experience is recorded in the data without being explicitly programmed. So it's the exact opposite of B and C. We're definitely not learning from rules, and it's definitely not just used for image and speech recognition. It can be used for many other things beyond those. So yeah, A is the best choice there. What do we say here? Okay, what do you guys think about this? Which example illustrates the use of machine learning to enhance customer experience in an e-commerce company? In other words, what would be some typical use cases of machine learning? Good. So I think C is going to be the best answer here. Definitely C. So it's using machine learning to do fraud transactions. So that would be a prediction, probably a supervised learning, right? If this is fraud or not fraud. And then maybe some customer behavior that might be unsupervised. So maybe grouping together customers, clustering them based on their data, like their shopping behavior and characteristics. Um, that might be unsupervised, but either way, it's machine learning. Okay. Okay, final one. What distinguishes deep learning from machine learning and artificial intelligence? So what's unique about deep learning? Very good. Yep. So deep learning uses neural networks so you guys are right on top of that. Deep learning uses neural nets. That's what makes it unique. So machine learning would be part A. Machine learning is focused on learning from data. Underneath of that is learning from data using neural networks, which is what deep learning is. Very good. All right, let's go to lesson three. And lesson three has two notebooks. We're going to be starting with 3.1. So you'll want to open up that notebook. I'm going to go over to it now. Give you a moment to open that up. So I'm going to open the 3.1 notebook. There's two of them. We'll see how far if we can get into the second one today. Probably will. But we're gonna start with 3.1 notebook. Do you guys have this notebook? It should be in your materials for this course. I'll give you a moment to open that one. Do you guys have it? Okay. All right. So we're gonna start by talking about supervised learning. In our machine learning journey. So remember, we're going to talk about supervised and unsupervised after we do supervised. And there's going to be a lot to cover with supervised, mainly because there are two different types of problems we can tackle, which we'll talk about in a moment, predicting different kinds of values. But let's talk about the kind of what we're hoping to learn here, which is talk about the different kinds of problems that we'll study, which are these categories of supervised learning. Those two categories are going to be called classification and regression. We'll talk about those and their differences, and then talk about some applications and some example algorithms. And that's just within this notebook. 3.2, we'll get into regression in particular, which will be very, very interesting. Okay, so that'll be our first models that we'll build will be over there in 3.2. Okay, so if you guys remember, supervised learning is where we learn from labeled data. So we have input and outputs in our data set. So you train a model on this data that includes input features and corresponding outputs that are the labels, right? So the goal is to learn a relationship between the input and the output. Of course, that's what any model is trying to do. And what this allows us to do is then take that model and use it to make predictions on never before seen data, right? So then we have a predictive model out of that that we can use going forward on new examples. So remember, we will have in our data a bunch of features which are columns, and then generally one of those columns will be the label that we're trying to predict. And our model is going to try to learn some type of relationship between those inputs and the output label. So the output label could be like fraud, not fraud, cancer, not cancer, a price, a temperature, those kind of things. So let's talk about that. Inside of supervised learning, there are two different types of learning that we can do, and they're really based on the label, or sometimes that label is known as the target that we're trying to predict. And depending on that type, we get these two different categories of learning or two different types of learning. One is known as regression. So that's generally when we are predicting something that is continuous or something that is a numerical, so numerical value. So think of price, think of temperature, think of revenue. We're trying to predict something like that, versus something that is categorical. So that the predicting something categorical would be like fraud, not fraud, spam, not spam. Those are discrete categories. And the problem of predicting categories is known as classification, because we're trying to classify examples as belonging to one category or another. So we have these two main types of supervised learning problems. We have regression and we have classification, and they're going to be handled slightly differently, um, for many reasons that we're going to uncover. One of the primary reasons is that, of course, we're predicting something that's continuous in the regression case versus something discrete. So the models have to be slightly different to account for that. Um, but then a step beyond that is the evaluation has to be different too. I kind of alluded to this last week, but when you're predicting a regression, it's very, very difficult to get the exact numerical answer. So generally, we don't care about that. Um, Generally, we don't care about getting it exactly. We don't care about getting it exactly right. We just care about getting it. We care about getting it nearby, getting it close enough. Whereas classification, we do care about getting it exactly right because it's a discrete category. So we're going to be able to evaluate that a little bit differently to say, did we get the answer right or wrong? Regression is going to be, did we get close? Because we assume it's going to be nearly impossible to predict a continuous number. That's very hard to do. Okay. So any questions on that? Any questions on those two differences? Let me give you some examples. Maybe it'll help too. So again, the classification is going to be predicting something that's categorical. Regression is going to be predicting something that is continuous. So think about trying to predict the price of a house based on those other features we talked about before, like square footage, bedrooms, bathrooms, all of those things. We predict the price. That would be a regression problem because the price is a continuous value. Let's take a look at an example here. Imagine we were trying to predict the temperature tomorrow. That's going to be a regression problem, a supervised learning kind of regression problem, because we're trying to predict a numerical temperature. Okay. And versus a category, like a discrete category would be, this would be a classification. So this is a regression on the left. This is a classification on the right, classification, because we are predicting one of two categories. This is just hot or cold. Now, we're not saying exactly where that threshold is on what's hot or cold. That would be a decision on what we want to, what our discrete categories actually mean. But we only have two choices, hot or cold, versus predicting the entire temperature, which would be a numerical prediction of some exact number, right? So that'd be a regression, and then on the right would be a classification. Now, again, why is this so different? You can see the types of predictions we're making are completely different. One's a number, one's a category. But again, with evaluation, it's like if the true answer in our labels was 84 and we predicted 83, that's a pretty good result. That's still pretty close. That's pretty close to this. So from an evaluation perspective, that's pretty good. Whereas like if I predicted cold and it's actually hot, that's a wrong answer. So they're evaluated slightly different. And that's something we're going to see as we talk about evaluation of our models once we build them, is depending on if it's classification or regression, there's going to be different ways of evaluating them. You can kind of see why. It's very difficult to say, okay, we got exactly 84 when it could be any number. Our model is going to be predicting a number that's really hard to pin down an exact floating point number. So the best we can do is kind of say, how close did I get? Like this would be a worse answer if I got something all the way down here. That's a really long distance to here. That's bad. That's a bad prediction. But if I get something really close, that's better, right? That's a decent prediction because it's pretty close, right? Of course, being perfect would be getting it exactly right, but that would be nearly impossible to do. Okay. All right. Any questions on this? Does it make sense on regression versus classification? We're going to use those words quite a bit as we go along. So regression, predicting that continuous value, classification, predicting a category, and they're going to be different models that do that, different models being used for regression versus different models being used for classification. All right. Let's talk about supervised learning applications here. So, just to name a few, we have HR operations. Imagine your recruiter tasked with finding the best candidates. So, supervised learning can help by rejecting or accepting candidates. Now, this is something that happens quite a bit even today. Um, and it's kind of like how recommendations happen. Like this resume should be recommended. This should not, from a whole pool of applications. Um, so there's those kind of use cases of predicting a category that would be like a classification. Should we accept or reject the candidate? Um, Finance, you see this all the time with things like risk and loan approvals. You can predict the category of like if the loan, if we should accept or reject the loan application. Um, that would be a classification. Um, what's interesting about classifications, by the way, so it says here, like we can predict the likelihood of a loan being repaid. Um, is a lot of the classifications, we say that they predict a category, but under the hood, they can actually predict a probability, and we turn that probability into a category. So, like we could say the likelihood of a loan being repaid is very low. Let's say it's less than 50% probability. Then we could label this as reject, right? We could label that as a rejection. If it's greater than 50%, then we could label this as accept. So we can set a threshold there and say, Okay, truly we're predicting a probability, like our model spits out a probability, but we turn that into a category by saying, should we accept, if it's less than 50%, we should reject. If it's greater, then we should accept. Okay, so that's something we will see with some of our classification models is that they actually produce a probability and we turn that probability into a category label by doing something simple like this, putting a threshold on it for the category. So finances is used all over the place, not only just loans, like fraud. We talked about fraud, not fraud. That would be a classification. Predicting sales revenue, that would be a regression, right? What is the revenue going to be in the next 2 quarters? That's going to be a regression problem. Uh, Emails like spam, not spam, that's going to be a classification. That's going to operate on that's going to take the text input and predict if this email is a spam or a not spam. That's going to be a supervised learning problem, but it's going to be a classification problem, right? Manufacturing, supervised learning is used to inspect and quality and classify products into different grades. For example, a factory might use a model to check for defects. So this is actually something that happens is you look at images of products as they go through the assembly line, and you can take a look at those images and predict if it's a high quality, low quality, medium quality. So they can be, this is a classification, right? They're going into different categories of quality. So it's much like a manual kind of intervention by some QA or quality control specialist. Okay, but that's a classification. So in the maritime industry, supervised learning can be used to predict currents, so current level, and that can be used to forecast supply and demand. So those would be like regression models that are used to predict, kind of like temperature, but in this case, like tidal levels. We talked about fraud already, so that's there. That would be a classification. Okay. Any questions on these examples? Of course, there's many more. Um, Recommendation is kind of like a supervised learning problem where you are taking examples of things that people have viewed in the past or reviewed in the past and using that to predict what they would want to watch in the future. Um, so recommendation is supervised learning. Um, and it's like a classification, trying to predict um, certain number of categories of shows or movies that you would want to watch. Um, and that's something that we will study in the future. We'll have a whole lesson dedicated to recommendation as well. All right. So when it comes down to the actual models themselves, so there's going to be lots of different models that we are going to cover, and they are going to be different in their purpose and kind of their what kinds of problems they're used for, and their how they actually train is going to be different. But at a high level, they're all trying to do the same thing, which is learn some sort of relationship between the input data and the label. Right? That's really what they're trying to do because they're all supervised. They have those labels, trying to build some relationship there. They just do it differently. And what we're going to study is the pros and cons of a lot of these models. Like when would I use one of them? When would I use another? So we'll try to talk about that as we go along. But they're all trying to learn some relationship between the input features and the output, right? So you have to keep that in mind. They're trying to model that relationship. They just do it in different ways. Okay, so as we go along and learn about new models, we will learn the details, we'll learn the ins and outs, and those pros and cons, but they're no matter what, they're all trying to learn that relationship, right? And be able to make predictions on new data. Okay. So here's a list of models that we will cover and work on throughout the sessions that we have. We're not going to do them all in one sitting, but the first one that we're going to start with and that we'll cover today is going to be linear regression. So we will cover linear regression, and then we'll cover the rest of these guys mostly in the context of classification. So what's interesting is some of these guys can actually be used for both regression and classification as long as you make certain adjustments to them. They have variations that can be used to do classification and regression, which is very interesting. Um, but we're going to start with linear regression today and then work our way through the rest of these models when we're going to do a separate lesson 4 on classification. So all of these guys will come from lesson 4. And then we will do this guy in lesson 3 in the 3.2 notebook. We'll do all about linear regression. Yeah, so logistic regression is a classification, which is kind of strange that its name is regression, but it's doing a classification. But the reason is that the logistic regression computes a probability. So it does a regression to predict a number, but that number is actually a probability. So it produces a result that's between, it produces a probability that's between obviously 0 and 1. So and then we take that probability and we turn it into a category, like a spam, not spam, fraud, not fraud. But so logistic regression is kind of special. It's sort of like a regression, but it's predicting a very specific type of value, which is a probability. So for that reason, it's a classification algorithm primarily. So we'll study that one in lesson 4. But yeah, that's why it's under that kind of umbrella of classification is because it's producing a probability as its main output, which we can then turn into a category as long as we interpret that probability as in the right way, like the probability of spam, probability of not spam. Okay. Okay, so let me focus on linear regression. I'm not going to go through all of these other use cases because we haven't learned these models yet. So I don't think they're good. I don't think it's good to read about them yet until we've covered them. So once we cover them in lesson 4, I'll come back and describe these examples to you guys, and we'll see why it makes sense. But I think for linear regression, which is what we'll cover next, let me talk about that example. So a prototypical example would be like predicting the house prices that we've seen in that house price data set. So if we wanted to predict if we wanted to estimate the market value of a house, so the price, um, we could do that by using the features such as number of bedrooms, square footage, location, age of the property. And then when a new house comes on the market, we could estimate what the price should be based on those features. So linear regression is a good one to predict the price, like a housing price. And we'll actually practice that in the next notebook. So and then all these other, now there's descriptions of these other models, but again, we haven't covered these guys yet, so I don't want to really go through those until we get to those models. So we get to those, I'll come back and mention the example. Can K and N be used for clustering? No. So the clustering model is going to be different. It's going to be K means. K means that's the primary clustering model, not K nearest neighbors. K nearest neighbors is used for it can be used for regression, it can be used for classification. So we'll talk about k and n, which is the k nearest neighbors in lesson 4. It sounds really similar, yeah. It sounds really similar, but k-means is a clustering algorithm that's slightly different. There's no labels used at all. This k nearest neighbors is a supervised learning algorithm. It uses labels. Good. Any other questions so far? Okay. So that being said, let's move on to the 3.2 notebook. Let's move on to that, which will be our first discussion around regression. So going into supervised learning and regression, give you guys a moment to pull up this notebook. But yeah, you want to pull up the 3.2. We'll do this one next. So we'll focus in. So our plan is to do regression first, and then we'll talk about classification in lesson 4, which we will cover all those other models which you can use for classification on that list. But then we're going to talk about linear regression first. All right, so we have a big agenda. This is a big notebook to go through a lot of material here surrounding regression. So we're gonna start with linear regression and see how we actually perform it, what that model is doing, which we've kind of seen the idea of it a little bit already, so it should be somewhat familiar. And then we'll talk about how to adapt that linear regression idea to what's called nonlinear regression, which is going to be using like polynomial features. We'll talk about how to do that. And then a big, big, big topic for us is going to be evaluating the model. So it'll be quite easy to actually build it. Building the model will be really easy, but evaluating and interpreting that will be a lot of interesting work there because we want to know what the performance of that model is once we have it built, right? We want to know how good of a model is it? Is it worth using, or do we need to retrain it or get new data or change the model up? We're going to talk about that. How do you determine what to do based on that performance? And then we'll talk about here a couple things. We may not get to this today, but regularization, which is used to boost the performance in certain situations. Whenever the model is kind of performing poorly against test data, even though it performs pretty well on training data. In that scenario, you can use offshoots of linear regression that do some what's called regularization. We'll talk about that. And then we'll talk about hyperparameter tuning generally as a strategy, which is something you generally do want to do when you're training machine learning models. Um, so again, these two we may not get to today, but quite a lot to get to prior to that, mainly centered around evaluation and building linear regression. Okay, so pretty cool. We'll get to our first kind of model here, this linear regression to start with. Okay. So let's start with linear regression here. And really what linear regression is attempting to do, and I want to show you this in this picture, is draw this line, sometimes what is known as the line of best fit. So this is our model that kind of goes through the data, and it's generally a good predictor. Because if you give me features, if you give me new features, and let's say you give me a feature that's right here. So you say, okay, I have a feature that's this value on the x-axis. then I know all I have to do is plug that into my line equation and I will generate a value that's like right here. Okay, that's on that line at that input. And that's going to be my prediction for what the output variable should be. It's just going to be something on that line. And what you can see is this line is a decent estimate for this data because it slices through this pretty evenly. So it's a good guess as to what the output should be given any one of these inputs. It's a good estimator, this line. And so our goal building a linear regression is to kind of build the equation of this line. So we want this equation of this line is going to be our model. Yes, it's going to look just like that, mx plus b or yeah, mx plus c. It's going to look exactly like that. Except that it's going to be more than just mx because we have generally more than one feature. So if you think of x as a feature, it will be more than just mx. It'll generally be like it'll generally look like this. And then plus maybe some bias here. Plus an intercept. Yeah. It'll generally look like that. So yeah, you're exactly right. MX plus B is the right idea. Exactly right. It'll generally look like that. Nonlinear, it can be adapted to nonlinear. Yeah, if we transform, we're going to talk about that. If we transform all of our features in a nonlinear way, we can apply linear regression to it. Yes, and that would be a nonlinear regression. So yes, we can do nonlinear things too. We'll talk about that. Okay. So linear regression again is the art or science, I should say, not really art, but it is an exact science of finding the equation of this line that fits through this data. Now, why one thing you should be thinking about is why is this line a good predictor? And the argument is that if you take a look at this distance from these blue points, so let's say these blue points are our actual data points, this line is going to be found such that it minimizes this distance from the points to, actually, I should draw it this way, from the points to the line. So we want this distance to be, actually, I should draw it that way, this way. We want this distance to be kind of at a minimum. So it would be bad to draw a line all the way out here because then that's a lot of distance, right? So, and that would be a lot of error contributed from not being able to predict those points in our data set very well, which is our training data. That's why we have labels, right? That guide us in building this line. So our goal is to build that line especially so that this error or this distance can be as minimum as possible, right? Which are all these distances from these points to the line. We want those to be as minimum as possible. So our goal is to find this equation. So we're going to build a model that's going to find this equation of the line such that our error is minimal. And what is the error? The error is the distance of our data points to the line that we build. So essentially what we'll do in order to train this will be to adjust the parameters in that, like I think is really good. You brought up the mx plus c. Basically the m and the c will adjust. So we adjust those accordingly to make this distance as small as possible. Okay, to minimize that distance as much as possible. Okay. So, where is regression used? We've already seen some examples. Here's some more advertising, like predicting sales, predicting oil production and demand. Those are like forecasts. Those are regression problems. Retail, like demand forecasting for inventory. Healthcare, predicting the levels of certain blood markers or something like that. Real estate predicting prices based on those talked about like square footage, bedrooms, bathrooms, those things. So regression is used again whenever we want to predict a number, a numerical output. That's a regression problem. So this kind of regression we're talking about here is generally known as a when that equation is linear, that is known as a linear regression. So to go back to that picture, when that equation of the line that we find is a linear equation, meaning that it is exactly the form I've been telling you. So it's something like weight times feature plus weight times feature plus weight times feature, and then maybe some intercept term, like some bias term there. This is a linear equation because all of the features are to the single power, so it's a linear power, and this is a linear combination of features with those different weights. So this is a linear model because it's what in math we would call this a linear equation, right? Everything is to the first power. It resembles mx plus b. It is a linear equation or a linear model. Um, so when we talk about linear regression, that is a regression model. So we're predicting some continuous target that assumes our model is formed from this kind of equation, a linear equation. So this is going to be our model for a linear regression. Okay. And so when you train a linear regression, your goal is to learn these weights so that you can plug in any one of your input features and you can generate a prediction. Which is going to be something on that line, right? It's going to be a value that's sitting here on this line. We put in all of our features and we end up there somewhere on that line, this output. Okay. Okay, let me pause there. Any questions on the linear model here or why it's called linear regression? Okay. And by the way, in these notes, this bullet point here where it says it uses the least squares criterion to estimate the coefficients, that is exactly what I said earlier with the distance. So the distance is based on the square of this quantity, like how far away you are from the line is based on this square distance here and here and here and here. So what we're trying to do is find the least distance or least squares, which is that minimum distance. So that's how we find all of these weights is from minimize. We basically tune them enough using our labels. So here's our label, which is the Y. We basically plug in our data and tune those enough to minimize the error. It's an optimization problem, right? We're trying to find the minimum of this quantity, which is that best fit line. Okay. So we have linear regression, um, and we can do a simple linear regression that only has one feature. So if it only has one feature, that's exactly so if there's only one input feature, sometimes that is known as simple regression or simple linear regression. And there's only one feature. So one independent variable is the feature. There's only one feature. And so this equation resembles the exact equation that you guys just put in there, which is mx plus b, right? It resembles exactly that. We're just using different symbols for those, like beta 0 and beta 1. But basically, exactly that simple line is only one feature. So, and that's because um, that line is going to be generated according to that equation. So here's kind of what it looks like. This is the best fit line through all of these blue dots. This is something we're going to be able to build. We're going to be able to build that equation pretty easily in Scikit-learn. So we'll be able to find that, and it won't be too hard. So this line will be y equals beta 0 plus beta 1. So some weight, beta 1, times the only feature we have, x1. Okay, so in this case, we would be predicting sales. So sales would be the value, basically the label that we're trying to predict. And the feature that we're putting in is, I think it's the number of TV expenses. Yep, TV expenses, which is on the x-axis. So there's one feature, which is TV expense. So on this graph, this would be our model. Okay, that would be our model. We only have one feature, and we have these two weights. We have an intercept B0 and or beta 0, and then a one weight which gets applied to that one feature, beta 1. And so our model would have certain value for beta 0 and a certain value for beta 1. That's these guys get learned during model training. Okay. So those are what get learned during our model training. And they get learned by what's called a least squares algorithm that is trying to minimize that distance. It tries to tweak beta 0, beta 1 to minimize this distance of this line to all of these points, trying to minimize this. So imagine taking a line and kind of moving it around and turning its slope, its angle, to try to find that best fit, which reduces that error the most, right? That's kind of what we're doing. Can I explain? Yeah, so sales is in dollars and TV expense um uh TV, actually, I think it's the other way around. I think the sales is actually a quantity. So I think this is number of sales that we have, and TV expense is I think it's in dollars. So how much money, how much expense did we put into the product? And then this is how many sales did we have of that product. So I think it's the other way around. But what this graph is showing is the blue points are our actual data points. Okay, so we have a collection, like we have a data frame that has, so imagine we had a data frame that has the true values. So it has the TV expenses. It has points that are like one. So it has points that are like 120, and then the sales could be like 700 units, let's say. And then it has so this is just our data set, right? This would be like in a data frame that we have. And then we had ones that were 50, and then um, this could be 400, let's say, and on and on and on, right? So this is our data, and this data is plotted in the blue. So these are these blue points here, right? So these are the blue points here, and the red points are is our model. So we built a linear regression model where we are putting in some values. We're putting in some fake X values here and generating some predictions, which is this line, this linear regression line, right? And that line is derived from this data, right? It gets learned from this supervised examples. Does that make sense? That line is derived from the data. It's actually learned from, like, the line of best fit is learned from that data. And the actual data is in the blue. So you can see we're trying to build this such that this distance is kind of a minimum. So it's an optimal fit to balance out these distances. So it's just plotting, so it's just building that relationship between the input and output. Like when the expenses are higher, we seem to have more sales. Okay. What's perpendicular? Like the distance? This should be perpendicular because it's a distance here. Is that what you mean? Like the distance from the real points to the line? Yeah, that should be perpendicular because it's a distance formula. Okay. All right. So more generally, now, do we usually have one feature? No. So generally we expand this to the more general case where we have more than one feature, like what we see in the housing data, right? Where we could predict a price, but we have many different inputs like bedrooms, bathrooms, square footage, etc. So more broadly, instead of simple linear regression, we have what's known as multiple linear regression, which means we have multiple variables or multiple features. This is exactly the equation I've been talking about. So we just extend that one into many features, so which is this case, and then a intercept term, which is there as sometimes known as the bias. Um, but this is the intercept term to kind of orient the line to start out in the right place. Um, and but this is the equation that we would be building the model. This is our model essentially, right? This is the equation we would be learning. Intercept is like a constant. Yeah. So if all of the features were zero, this is what our data would be. This is what our result would be if basically if this was zero, this was zero, this was zero, it would reduce to this as the prediction. Yeah, it's like a constant. Yes. So in geometry, the intercept's actually really important because it orients where your line should start. So it orients like So these values are kind of like the slope. They orient the tilt of it. Like, should it be tilted like this or should it be more sloped? But the intercept orients where it should start like vertically. Like, should it start all the way up here? Should it start more down here? That's what the intercept kind of tells us. Okay. So this is the situation. This is going to be our linear regression model that we will be building most of the time because we will have, again, these are all going to be features. So this is some feature, the X, this is some feature, this is some feature, X1, etc. These are all features. And what gets learned during the training are these coefficients. So all of these coefficients, including the beta zero, um, will get learned. So these will get learned from our data, right? They get learned, they will be trained from our data in order and how do they get trained? It's from reducing that distance. We try to get that line of best fit by tweaking those betas enough until we reach a minimum distance. But there's an algorithm behind that that Scikit-learn will run for us to find that best fit. So we don't need to do that manually, but that's the process is basically tweaking those weights to end up with that line of best fit. So in higher dimensions, instead of a line, you get more of what's called a plane here, which kind of looks like this. So the best fit is actually this plane where all it kind of dissects all of these points just like that in higher dimensions. So this is instead of a line, you get this in 3 dimensions, you get this plane like this. But it's like a line of best, it's just a more general line of best fit. It's still the same idea. We're still trying to come up with the best coefficients to minimize that distance from our points to the line. Although in higher dimensions, it's no longer a line, it's more like a plane like this. So you're trying to minimize this distance from here down to the plane, here up to the plane in higher dimensions. So I want you to keep in mind what we're trying to do before we go into the code, because the code is going to make it seem really, really simple. And that's because scikit-learn is great and that's what it does. But we should realize that there's something really complex going on, which is, again, finding the best value of these weights that minimizes the distance of this line to the data points that we have. So there's an algorithm there that will keep trying to make adjustments to this based on those distances. So it's going to use those distances as a guide to kind of tweak them to find the one that results in the lowest amount of distance. So we keep making tweaks, keep making tweaks, keep making tweaks, and eventually we converge to the set of weights that gives us that best fitting line. And there's an algorithm there that occurs. Now, luckily, that gets abstracted for us a bit behind scikit-learn um, finding that best fit. So there'll be a function that we use in scikit-learn when we build the model that will go ahead and find the best weights for us, and that's then we now have our optimal model, right? That then we can just plug in different values of these features and generate a prediction, which is going to be this result, right? So that's what we're ultimately trying to do is train the model, which will find all those optimal weights, and then we can predict with it, which would be plugging in different feature values to generate a prediction. Okay, so let's see how that happens. It's actually going to be super easy with scikit-learn. So in this scenario, we're going to import our pandas because we're going to load our data from that. So of course we need some data to work with. So we're going to load this CSV. Um, I so I was not actually able to find this CSV for this example, but I mean that's okay because we'll do other examples where we'll work with the data. If you happen to have it, great. I didn't see it in my files, so we just have to take the word for it that this is that TV and sales columns here from this data set. Okay. As an example. So um, just to see how it's fit, what we're going to do, and this is going to be a very standard process for us for building a model. These steps are going to be very, very standard for us, which is going to be, first of all, splitting the features away from the label. That's the first step that we always will take. So if you take a look at this code, it's taking all rows, but only the first column. Okay, so it's extracting all the features from the data frame, which happen to be, which is just the first column, which is the TV column, right? Just that column there. And our target variable, which is our label, so our target variable, aka the label, is the second column, right? It's that sales column. Um, and so our first step here, let me call that out here. First step is to always split apart features from labels. Okay. So we put all those features into a data frame called X, and we have all of our labels into technically a series, but sort of like a data frame, right? Called Y, which is just the uh, labels. So that's just the TV values. Now you're going to see why we do that. It's because we need our features and labels split apart to put them into the model building function. It expects our independent variables or our features to be separated from our answers or our labels that guide the model building. That's the first thing you got to do is separate those. Okay, so this code will separate those out into a capital X and a lowercase y. And that's actually pretty industry standard notation. Whenever you split apart all your features, usually you put them into a data frame called capital X, and then you have a lowercase y to represent your labels. That's actually pretty standard. So it's pretty standard that X represents features and Y represents labels, label column, whatever our label column is. In this case, it is the sales because we're going to be predicting sales using the TV column, the TV expense quantity. Yeah, so the assignment is that the assignment is that uh, we are splitting apart our data so that when we first read in the data, it is a data frame, right? That has two columns, TV and sales. Oh, perfect. Thank you, Tim. I will I will go ahead and so if you look at this data, it only has those two columns, right? It only has those two columns. Okay. So what we're doing with this is we are splitting apart our our independent variable, our features. So this X will contain our features and Y will contain our label. Does that make sense? We're splitting this data apart. So we're only grabbing that first column here to be our features. And then we're grabbing the second column, which is the sales, because we're going to predict the sales. This is our label. We're going to build a model to predict the sales given the TV input, TV expense input. So the first thing we have to do is split apart the features and the label. Okay, that's the first step we usually will take. And the reason we have to do that, just to reiterate, The reason we have to do that is because our model will expect our data features to be separate from the label. We will pass those in separately. X is TV. It's the first column because we're using iLoc, right? It's all rows but the first column, which is TV. Y is sales. This is what we're predicting. We are predicting the sales given the TV expense value. Yeah. Which is why we split it into, so this is the second column, right? The index one column. You just put in read CSV and pass in the URL. So you could, so exactly the code that was up earlier from Tim. You just do this and then data equals pd.read CSV URL. So we split our data into X and Y here. All right. Now, one other step that we're going to take that's a very, very critical step, and we're going to see this step over and over and over and over again. So splitting apart into X and Y we'll do that over and over and over and over again. Not only that, but doing this next step, which is what's called a train test split. Now, let me show you what the train test split does. It takes our data and it's going to split apart our data that we have, our X and our Y data. It's going to split it apart into a percentage that will be used to train the data, and then a percentage that will be used to test. Now, why would we want to do that? It's mainly so we can do evaluation. So we build the model over here and then we test it on data that it has not seen before. So we reserve a percentage of the data to be used for test. Usually this data is somewhere between 20 to 30%. So somewhere between 20 to 30% of the original data. So that means the majority of it is used for training. So the majority of that X and Y over here is going to be between 70 to 80%. Will generally be used for training. Okay. So somewhere between 20 to 30. The industry standard is anywhere in between there. A lot of people like to use 30%. Some people like to use 20%. Anything in that range is acceptable. I think we generally will favor like 30% um, to be used for testing. But the point is we don't want to mix those together. We want those to be separated out so that we can have a fair evaluation, right? We want to train our data on this, train our model on this data, and then see how well it performs on this data that it has never seen before, right? So in order to have data it's never seen before, we're going to take our X and our Y and we're going to split it using this function called train test split that will do this kind of splitting for us. Okay, so scikit-learn has a function called train test split that will go ahead and we're going to pass our X and our Y and we'll pass in a percentage, like 30%, that we want to split out into a test set. And then the remainder of that, the 70%, will be used for training the model. Okay. So what we're going to get, let me redraw that. So what we're going to get out of this for the train test split is we're going to have an X and a Y per training and test. So we're going to get an X train and a Y train. So we're going to get training features and training labels, and then we're going to get test features to plug into our model and test answers or test labels to do evaluation, because what we should be able to do is build the model over here and then apply the model on this data, meaning we can take these features and plug it into our model and then see what answers we get and compare those answers to this testing data, right? We should be able to do that to generate an evaluation. Okay. Now you may be wondering, why do we do any of that? What's the purpose of that? Evaluating it on this test data gives us a good sense of, will our model generalize to new examples, right? If it performs pretty well on this data, that's a good signal. Like when it's performing pretty well on data it's never seen before, that's a good indicator that it's going to perform pretty well when we use it on brand new examples in the future, right? So that's why we do this evaluation on this data that it has not seen before. It's going to see this training data, right? We're going to train the model on that data, but that model will never be exposed to this test data until we do the evaluation and generate some metrics to see how good is this performing and does it have a good chance of generalizing to never before seen examples, which is what we want, right? Because we're going to use this model in the real world. It's going to be being used on new examples that it hasn't seen before. We want it to perform well. So this is kind of our test, our evaluation. Okay. Any questions on we're going to do this in a moment. I'll show you what it looks like in the code, but conceptually, any questions on the train test split idea? It's a very, very important idea that we basically use part of the data to train it and then another part of it to evaluate. It's very important we do that. By the way, this has a term. This in machine learning, this is called cross validation, because we are using one data set to train the model and then we're crossing that over into another data set to validate it, which is the testing set. So this is called cross-validation. There's actually many ways to do cross-validation. That's something we'll study. This is a very simple way of doing cross-validation. There's more complex ways. You can take your data and you can actually divide it into many sections and basically train it against most of these and evaluate it against one at a time and then rotate. So that's another way to do cross-validation. We're going to study that. But this is the simplest way to do it here. Okay. So let me show you what you get when you use train test split. So we're going to import from sklearn. From the model selection module. Now we haven't used this before. This is our first time using it, but here's our model selection. We're going to import this train test split function, and we're going to use it on our X and Y, and we're going to set a test size of 30%, which is zero point 0.3. So our test size is 30% converted to decimal, right? Converted to zero point 0.3. So that means we're reserving 30% for that test set. You can set a random state. Now that's completely optional. The random state is for reproducibility, because what the train test split is going to do is it's actually going to shuffle the data and then split it apart into the 70/30. So, yes, the seed, exactly, it's like a seed. So it's saying like when you do that shuffling, every time I run this notebook, I'm going to get the same result. But it's going to be random it's going to be random, but I'm going to be able to reproduce that randomness with that random state. Yes, it is like a seed. It's you can choose any number to be your your random state. 42 isn't important. You could choose 0, you could choose 1. You could choose any positive integer. 42 is kind of like the industry standard. It's you'd have to look it up why it is. Apparently 42 is a special number um, in kind of the history of development of this stuff. There's nothing really special about 42. You could choose a random seed to be 0. That's fine. It doesn't really matter. You could choose it to be 1, 2, 3. You could choose it to be 15. You can choose it to be anything you want it to be. It's really so that your shuffling is consistent. Every time you run this notebook, you get the same shuffle result. So I'm always going to get the same rows in these splits. Hitchhiker, there it is. I knew it was from something. Hitchhiker's Guide. Yeah. Yeah. So 42 is kind of like it's just used ubiquitously. As kind of a um, paying tribute to the Hitchhiker's Guide to the Galaxy, but there's nothing that special about 42. It's not going to change our result or anything. It's just so that this train set split is going to shuffle our data and split it apart into 70/30. You just want to set this to something so that you get every time we run this notebook, we get a consistent shuffle. And so the data in these sets are consistent. That's all. Okay, but do you guys see how we pass in our X and our Y and we generate four different data quantities here, which is we generate training features, test features, training labels, and test labels. Because again, we're generating data on these two different sets, a training set and a test set. So we have training features, training label, and then test features, test label. Okay. That's why it's so important to split apart our data into the X and the Y. We need those split apart in order for this part to work. So by the way, these two steps we will always do for any model we build. We'll generally do X and Y and then train test split in order to generate the data that we will use for building our model. Okay. So this data here is going to be what we actually use to guide the training of our model. So it's definitely supervised, right? Linear regression. Um, we will use that. Okay. So we haven't built the model yet. We're just getting our data split apart and ready for the training. We haven't actually built our model yet, right? That'll be coming up in a moment. But this is getting our data ready. We started with our data frame. We split it apart into an X and a Y, and we split that into train test split. And um, then we can go ahead and pass in to our model training, which we'll do in a moment. That's a good question. So what you could do is you could run. Did we import NumPy? Let's see. We did. Okay. You could run the average on you could check the np.mean on the X train and um, see how it compares to X. So you could do that and see what the average of this feature is compared to the average of the original. They may not be perfect because we are taking a reduced data set size. So I don't think there's not like a one size fits all validation we can do because we're taking a random shuffle and we're taking 70% of the data out. So we're not guaranteed to maintain the same statistics. We can see if they're close. But does that make sense? Like we're not guaranteed to get the same stats because we're taking a slice of it. We're taking 70%. So it's not guaranteed to be the same distribution, really. Delete that. It's a good practice. Yes, it is. It is. 30% is the industry standard. Anything between 20 to 30, so 0.2, 0.25, zero point 0.3, any of those are acceptable. It's really up to you. I mostly see 30%. I think zero point 0.3 is a good practice to use for sure. I did explain random state. Random state is so that you get consistent shuffling. You can set this to any integer that you want it to be. It doesn't really matter. You can set it to 100, you can set it to 10, you can set it to 15. It just ensures because what this split will do is it will shuffle the data first. It'll shuffle the rows and then split it apart into the train and test sets. So you set the random state so that the next time you run this, you get the same consistent shuffling. That's the only thing it helps you with because it is randomized, but when you set a random state, it's so that like if you run it again, you'll get the same shuffling. You'll get the same. The shuffling matters because it dictates what ends up in these sets. Okay. All right. So let's see. Let's build the model. Um, and let me show you how easy this is going to be to build a model. And this is really how it's going to be for every single scikit-learn model will basically look the exact same for training it, which is what's going to make it really, really nice. So the first thing we have to do is import our model. So from scikit-learn, we're going to be using from the linear model package or the linear model module, I should say, within sklearn. We're going to be importing the linear regression and we're going to create an instance of the linear regression here. Okay. So linear regression and look how easy this is going to be. Nearly all sklearn models use .fit function to train. So every one of them, no matter which one we use, like the decision tree, like the logistic regression, any of those like we use for classification that are going to be coming up in lesson 4, they're all going to look the same in terms of it's going to run .fit, which is scikit-learn's generic function for training your model. So this will execute the training once we run this code. And again, the linear regression training is going to do that least squares distance procedure or algorithm to try to find the right weights. It's trying to find those weights that minimize that square distance from our line that it's trying to build to the data. And what I want you to notice is what we put into the dot fit. See how we put in the training data where we put in the training features and we put in the training labels. Now this is supervised. So of course we put in the labels, right? Of course we put in these labels here. And of course we put in our features here. So we're putting in all of our examples from our training split into this dot fit, which is going to train the model so that we can use it for prediction. Okay, it's really fast. If I run this, it's going to be pretty much instant. Pretty much instantly it gets trained, and you can see here we now have a linear regression. You can see in this little box. And this information says that it has been fitted. So it's now ready to be used, right? So that's it. We've trained our model. That's how easy that was. We did .fit. Now what we should realize is there's a lot of work going on behind the scenes of this .fit. Okay, there's a lot of work being done there to do the least squares algorithm and find those weights and create that line of best fit, right? So there's a lot of work being going on there that's going on there behind the scenes, but Scikit-learn is abstracting it away for us, right? And all we have to do is dot fit when we're using this code. Really easy, dot fit. And there we go. We've trained our linear regression model. And by the way, if you want to see what the coefficients are, you can actually extract them if you do. So if you take your lin regression and you do coefficients like this, dot coef with an underscore. So this gives us the trained weights, coefficients, also known as the coefficients, right? Um, so if you run this, you can see right now we have this coefficient here, which is the only coefficient we had on our feature. So we only had one feature coefficient there. And we can take a look at our intercept, which is this. So this gives us the train weights. And so we can look at the intercept, we can look at the coefficient. So obviously, if we have multiple features, our model has many features, it's going to have more values in that coefficient. But the intercept is just a single value, 7.23, and then the coefficient is 0.046. So that's the weight that gets learned. Is there a size limit? No, not really. There's no size limit. No, you can use as much data as you want. There's really no size limit other than what you can fit in memory. I'd say that's the only limit is basically what the amount of data that can fit in memory. Okay. All right. Were you guys able to run this? Were you guys able to run the linear regression dot fit? Okay, perfect. Perfect. You were? Okay, great. Great. So we have a model and we can use it to predict. And so that's actually what we're going to do next. If we go down here, we're going to have a function that's going to build a scatter plot of our original test data. So we're going to have our test data here. Um, and we're going to take our training data and plot. We're going to use this data versus our sales predictions. So you can see we're going to use this is how, by the way, this is how you use the scikit-learn model to predict. You have a fit to train it and look at the function you use to predict. It's literally just called predict. That's how easy it is. And you pass in your data, all your features into this predict, and it generates a prediction for every row. So every row in these features in this data frame will end up with a prediction using our model. So what we're going to do is plot our training features against the predicted sales to see how good of a fit that really was. Okay, to see the regression fit. Okay. And so there's the regression fit. We have all of our test data here plotted in the green. We have our blue, which is our blue, which is our training data line that we built our model on. So that's a pretty decent fit. And then our test data is here, which is plotted in the green scatter. But the thing I want you to see is this prediction, right? We were able to generate some predictions on that training. by running our predict function with our model. Now, this model has been trained, so we've already fit it, and now we're using it to predict, right? And so we're predicting the sales and plotting that on the y-axis. So the sales are, we're using the predicted sales there, which is our blue line. So this is our line of best fit. So this is our model prediction. This is our model predictions, right? You can see it's a pretty decent line, right? It's a pretty decent line of best fit. Of course, there's some error here. Like there, it's not perfect, but it does a decent job of being a best fit line. Okay. So look how easy that was to just to recap this. To fit our model was a linear regression dot fit. And of course, we're going to do more examples. So no worries on that. We're going to see this many, many, many times throughout this notebook. But we have linear regression dot fit to train it. And then we have linear regression dot predict and we pass in our features and that generates a predicted output, right? So what this is actually doing is computing this quantity. We could do either. We could do either. So one thing we could do is plot, so we could swap it out. We could do either one. It's not a big deal to do the training set. So we could plot X test and then we could plot linear regression X test. So it's a similar line. Um, it's just different input features, but the line is going to be the same. Just different inputs. But the coefficients are the same, right? It's the same line. It's just we generate different outputs. So yeah, you could do either one. This is honestly, this is probably better. I see what you're saying. This is probably better because this is the line of best fit through this data. So that probably makes sense to do predict on the test set. Agreed on that. Probably makes about most sense. But you could do either one. Yeah, I think that makes the most sense is for it to be on the same one, just to validate. So like we could do training here and then train and train just to see how that data lines up. Really what we're trying to do is have our scattered data and then our line of best fit on the same plot. That's all we're trying to do, right? So yeah, I think they should be the same. I think that makes sense. These values, or which values do you want to see? Yeah, we could generate those if we just do let's go down here. So the line values are going to be the prediction. So the test predictions equals test predictions equals linear regression dot predict x test, and then we could print out our test predictions. Yeah, so we could see what those actual values are on the test set. Yeah. We will do that. Yeah. So you thought we were checking how well our data was trained. We will do that. Yes. We haven't learned how to evaluate this yet. We're going to talk about that coming up next. Yeah. We will do that. We just haven't learned how to do proper evaluation of a regression model. But yeah, it's something we're going to talk about for sure and see how to do in our code. Okay. All right. Any other questions on this example? Again, big takeaways, dot fit to train it, and then dot predict to use it, dot predict on the features to use the model and make predictions with it. So here is an example. We made all the predictions. These are all the values that are on that line. These are all our predictions. And notice this is a truly regression, right? These are all floating point values. So this is definitely a regression, right? Okay. That's a good question. I'm not sure if there's like a verbose. There's not really a verbose. I mean, you can look at the source code if you really want to see. You can view the source code to see how it's done. I can tell you, I mean, so generally linear regression is done in two ways. Either you use a formula to solve the optimization problem of minimizing like this distance from the points to the line. Um, or you use something called gradient descent, which is how a lot of these things do it, is they iterate through a bunch of different iterations where they update these weights according to a certain basically a gradient of the error function. The error function in this case is the squared distance from the line to the uh to the points. So we can compute the gradient of that and do gradient descent. So if you really want to look into it, I would do some research on like linear regression gradient descent. Okay, linear regression gradient descent to see how that's being done. Yeah, it's a pretty simple procedure. Again, you have the notion is that you want to minimize the loss or the error. In this case, the loss is the square distance. So it's like there's like it's a formula. It's like a sum of a square distance from your prediction um, or your label, sorry, to your model, which is the beta zero plus beta one x1 plus beta two x2 etc., like your model, and then squared. So this is the square distance here, and you're minimizing this guy, which is like a calculus problem. You basically find I'm getting so far into the weeds of this, but this is like a parabola, and you work your way. No, no, you're good. It's a good question. Um, you work your way down to the minimum of it. Does that make sense? Like you're working your way down here, and you do that through a descent process, like a descent iteration. Um, so that's how these are found. Um, but you don't see that happening in the background. But if you look at the source code, I guarantee you it's either going to be this or they're going to use a matrix formula to basically solve an equation that involves this. Basically the derivative of this set equal to zero and you find the minimum. Either way, you're finding the minimum of this. Okay. But yeah, I don't think Scikit-learn has like maybe there's some type of verbose flag you can look for. I don't think they have that though. Not that I've seen. All right. So I have an important concept to talk about next, which is going to be called overfitting and underfitting, which is a really important concept that's related to the training and test data we just split apart to do evaluation. And essentially, the issue with machine learning is that it's not perfect and it can struggle in different ways. And the two ways that it primarily struggles is going to be overfitting and underfitting. So, overfitting is a situation where the model basically memorizes the training data so well that it fails to generalize to new examples. So what we see with overfitting is this exact sign here where we have really good performance on the training data. So when we do that train test split, we see a really good accuracy or really low error on the training data, but it does not perform anywhere near that on that test data split. So what that means is that the model is overfitting to the training data. It's basically memorizing it and it's not able to generalize very well. Now, why does that happen? It's usually because the model is way too complex. And that means generally you need to do something to reduce the complexity. Either you need to use a simpler model or you need to use some type of technique to mitigate overfitting. And we're gonna study some of those techniques coming up in this notebook. We might not get to it today, but we're going to study particularly what can we do to prevent overfitting, because overfitting is the more common issue with machine learning models. They tend to do so well at learning from data that they pick up on small details and patterns in the training examples that they're exposed to. They don't do a great job at generalizing to new examples. They can struggle at that. So that's overfitting, is struggling to generalize to new examples, but you do really well on your training data. So it appears like you have a good model, but it's not able to go and make predictions on test data very well, which means we would not want to use that model in the real world, right? Because it's not able to generalize outside of what it's already seen. And that's not a good thing if we're trying to use it for real world examples, right? So overfitting is a real issue. You see it all the time. I've seen it many, many times in the real world, real industry work that I've done. Overfitting is a challenge for a lot of machine learning models. And so we need some techniques to overcome overfitting, and we're going to study some of those coming up shortly. Um, one of the things that we can do, one of the things that we can do to detect overfitting is exactly what we just did, which is you split apart your data into training and testing so that you have a chance to do an evaluation to see if you're even overfitting in the first place. You want to see that performance be consistent from train to test, right? You want to see consistency. What you don't want to see is performance that drops off on the test data. It's much worse. You don't want to see that. That means that your model is overfit to your training data, and it's not going to perform well in the real world. Okay. So we're going to have a couple ways to overcome that. Talk about that. Now, the opposite can actually happen as well, which is called underfitting. And underfitting refers to the fact that a model is too simple and it actually just performs poorly across the board. So if we see poor performance on the training and testing data, that's a good signal that the model's underfit. And that means it's too simple usually, and you should try using something more complex. So the best way to combat underfitting is to use a more complex model. And as we go through and learn about the models, we're going to learn about which ones are simple and which ones are complex. So we're going to have a scale of kind of complexity. And if you're underfitting, you want to bump up to a more complex model. If you're overfitting, One way of combating that is to actually go down to something more simple, go the opposite way to something simpler. So we need to learn, right now we've only learned linear regression, but we will learn other models, in the future, and we'll talk about their complexity and how they're related to each other. Okay. But these are two issues we see. Just to draw that out again, is if we have a train test split where we have 70-30 split, let's say, and we perform really well over here, but we go to apply that model over here and it fails, its accuracy drops off significantly, more error. That's definitely overfitting, which is not good. Right? And then underfitting is just not performing well in either case. So even on the training data itself, your accuracy is not very good. So you're not really learning effectively. You're underfitting your model. So that's underfitting case. Okay. All right. Now, the issue is that it can be very difficult to balance these two and get it correct. That's what makes machine learning a little bit challenging, is getting this balance correct of simplicity and complexity. So you don't want to be overly complex that you overfit, but you don't want to be overly simple that you underfit and you're not able to learn effectively. So there's a bit of a trade-off there, and this trade-off is typically known in the community as bias variance trade-off, in which case it's basically like a complexity simplicity trade-off. It's another word for that. Um, and so it's thought that um, if you if you have if you have a situation where you're able to fit the training data very well, you risk not being able to generalize. In other words, you risk overfitting, and it's hard to combat that in a way. Um, and on the reverse side, if you have something really simple, you risk not learning enough. Even if you're trying to combat that overfitting, you risk not learning enough, and your model just doesn't perform as well as it could. So it's a bit of a trade-off there of trying to find the right balance between something complex enough to learn, but something not overly complex that it's going to not generalize to new data. That's the challenge. Um, like I said, we are going to have techniques to overcome this. So luckily, there are things to basically overcome this trade-off and and help us along the way so that we don't overfit. They basically prevent overfitting and allow us to use complex enough models that won't be overfit. This is in the this was in our lesson 3.2 notebook. So you want to pull that one back up. We were working on Monday. And just to recap this a little bit, remember we were building a linear regression. I wanted to recap some of the steps we took there, um, that we will be doing over and over again, and really the same kind of steps that we do here, we'll do in a lot of our model building, pretty much all of our model building that we do, whether it's regression or classification, doesn't really matter. We'll still be doing a lot of these steps, which are um, remember, first we split apart our data into kind of a features and a label, X and Y. And the reason that's important is because the model training uses the features and the label to help train the model, right? They use those separately. So we want to split those apart whenever we can. And so we have usually it's a good practice to call your features capital X and your labels lowercase y. And what we do with that is, remember, we immediately split that into what we call the training and a test set. And the picture we had for that was something like this, where we had about 70% of the data we used to train the model against, and then the other 30% of the data we use to test the model against, meaning that we build a model over here and we apply it to this set over here to make predictions. And then that's where the supervised learning really comes into play, right? Is on this test set we already have the answers. We already have the label. And so we can apply our model to this to the features over here, predict what the label should be, and compare that. We can get a metric, right, that compares how close we are in our prediction to the actual values. And that was some of our performance metrics. I'll recap some of those that kind of measure that distance away from our predictions to what the actual label is. But remember, we had this train test split function, which helps us split apart our features and our labels into these four sets of data. So we have our training features, our testing features, and then our training labels and our testing labels. So we have all of those. And really, these two guys are going to be used to train the model. That's why they're called underscore train. You're going to use to train that model. And then we're going to predict on these set of features and then use those predictions to compare to this set of labels, right? That's on the test set. And you notice here our test size is set to 30%. That's a pretty standard number. Anywhere between like 20 to 30% is pretty standard. Um, we'll typically use zero point 0.3, but it could be zero point 0.2, anywhere in between is fine. Okay, so we had that. Hopefully that we remember that from Monday. So we had a train and a test set. And then building the model was actually really, really easy. Once you have those train and test sets, we just import our model object. So from Scikit-learn, sklearn, um, linear model module from that package, we import the linear regression model, and then we do linear regression dot fit, and we pass in our features and our labels. And this is, again, this is where that supervised learning is really coming into play because we're passing in these labels. That's really what makes this work, right? We need those labels to help guide the model to make those updates. If you guys remember, the model is something that looks like this. So this was a bunch of different coefficients times the features, however many we have. And so these labels are really taking the place of this, and they're helping us make the correct updates to these coefficients, or sometimes we call them weights. These B0, B1, B2. Um, we find out what the optimal one is to get the best fit, right? To get the line of best fit. Um, that's what the model training, when we call this dot fit, that's really what it's doing in the background is finding all those coefficients, right? To end up with the line of best fit that has the lowest amount of error. Okay, so hopefully that makes sense. That's just the dot fit to train our models, and that's really going to be the case for uh, pretty much every single model that we train with Scikit-learn. It's pretty much going to be a dot fit. We pass in our training features and our training labels. Okay, so we had that, and this was the visualization of that where we had our test points kind of scattered, and we see our line of best fit is the one that goes through there with that minimal error. That's the whole goal. Pretty decent predictor. Okay. And then we talked about overfitting, underfitting. So just to recap this, overfitting is the concept of our model basically memorizing our training data. It performs really well on that training set, but it is not able to generalize outside of that. So it performs poorly on the test set or data that it's never seen before. Um, and that's overfitting. So the reason that it overfits is generally the model is too complex and it needs to be simplified a bit. And one of the things we're going to do today is see a couple of ways we can alter the linear regression model if we are overfitting to prevent overfitting. Um, so there's going to be ways to handle this. And so we're going to explore some of those today. Underfitting is kind of the reverse of that. Remember, it's where the model is not learning enough, so the performance is poor even on the training data. It's not good on the test data either. that is a sign that the model is probably too simple and maybe we should use something more complex, like go from a linear regression, maybe to use a polynomial regression, or maybe use an entirely different model altogether. If we're underfitting, our performance is poor, it's a good signal we should try something else. Um, okay, so we talked about those. And one of the things we also talked about was evaluation. So if you guys remember, we had different metrics that we could compute to get a gauge of how good our model is actually performing. One of those was MSE, which is this mean squared error function. So we did this example during class last time on Monday, where we were able to generate the mean squared error. That's one of our metrics, and we can see what the mean squared error is on the training set and see what it is on the test set by just passing in our training predictions and our training labels, our test predictions and our test labels. We pass those into this mean squared error function, and it computes the MSE. And that's a helpful function from the scikit-learn metrics package or module, I should say, and we'll be using that quite a bit to do, evaluation of especially of regression, right? Mean squared error is probably the most common performance metric we can have. And if you guys remember, what it's really doing is measuring these distances. So mean squared error is kind of like the average distance away from our points to the actual to the predictions, which the predictions are all on this line. So it's like measuring on average how much error do we have on average, right? And the idea is the closer to zero, the better. Generally means that the distance away from our prediction to our points is pretty low, the closer to zero it is, which is pretty desirable. So a low MSE is kind of what we're looking for. Closer to zero, the better. And so if one model has a lower MSE than another, it's a better performing model, right? It has less error. Okay, and then we also looked at the R squared or sometimes known as R2 score. This is another metric that we could use that measures the variability of the predictions and if our model is capturing that variability well. And so R squared has a range of 0 to 1. 1 is better. That means the model is capturing the changes in the output. Our predictions follow along with those same changes. So they're pretty close. So closer to 1 would be a better score. So we have those kind of metrics. So like on this data, this would show that this model was underfitting. Remember, because this MSE was bad and this MSE was bad. Um, and what we should think of these in the units of what our labels are. Especially if we take the square root of this, the RMSE, that was another metric we had. The square root of this is actually in the exact units that we have for our labels. So in this example, this was the units or the sales versus the TV products, right? And so this would indicate that on average, if we take the square root of this, in the square root of this, we have um, we're on average about 11 sales units off squared. So if we take the square root of that, it's somewhere around 3 to 4, um, somewhere in between 3 and 4 units off. And this is as well. And because both of these are still not close to zero, this would be under fit. And this shows that as well. This isn't that close to 1. It's decent, but it's not that close to 1. So we would say, and performance is poor on both training and test sets. That's the key indicator of underfitting. It's poor on both. Yeah, exactly. High MSE correlates to underfitting. Yes, yes. And what's key is it's high MSE on both the training and the test sets. If you have a high MSE on your test set, but a low MSE on your training set, that's overfitting, right? Where it's not generalizing from the training set to the test data that it hasn't seen before. That's overfitting. So the key is high MSE on both sets. All right, so we talked about that. We did polynomial regression last time. So that was doing that was making a curved graph by transforming the features into polynomial features and then doing linear regression with that. So you guys remember from Monday we did this where we took our features and transformed them according to this polynomial features from Scikit-learn. So we can go all the way up to whatever degree we want. So we put in 4 here, but there's nothing special about 4 really. This is just testing it out. And we generate the polynomial features, and we can fit a linear regression on those polynomial features, and we get a slightly better model, right? It fits the data a little bit better than just a straight line. This curved line with the polynomial features performs a little bit better, and we could see that with the MSE, right? We could evaluate the MSE of this, and it would be lower. It would be lower than the curved line, and so that's something we could do. Um, we would just have to pass in these test predictions, the training predictions, and then the test labels and training labels and pass those into the mean squared error function, and we could compute that, right? Wouldn't be hard to do. All right, and then finally, where we left off, is on our performance metrics. So we talked about mean squared error. That's that average distance away from the labels to our predictions. And we take the square root of that. It's basically measuring the same thing, but it's the square root of it is more interpretable because it's in the same units as our label. Um, Mean absolute error is the average distance of the absolute value. So it's not the squared distance formula like a Euclidean distance, but it is a absolute value. So it's a little bit less sensitive to outliers. They don't get magnified as much, but it's not typically used as much as a mean squared error would be with regression. We talked about the last time because the distance formula or that distance is actually what's used to train the model. So it's a more natural fit for a performance metric for it. All right, and then we had our square. We just talked about that. Closer to 0 would be worse. Closer to 1 would be better. That means that the model explains all of the variability in the predictions. It captures those predictions closely to the labels um, very well. So 1 would be better. Closer to 1 would be better. All right. So that's where we left off. We're going to pick up from there with cross-validation. We've actually already seen one method of cross-validation. So we're going to we're going to kind of recap that and then talk about cross-validation in general and look at some more sophisticated techniques of it coming up next. But before I do that, any questions about anything we've covered to this point in the recap or anything from Monday? Any questions on that? All right. So let's talk about cross-validation. Um, Now, this term, cross-validation, refers to a technique that evaluates performance. And what it does is it divides our data into essentially training and test sets, which we've kind of already seen. And then we are able to train a model on the training set, evaluate it on the test set, and that's where we get the name cross-validation because we're crossing over our model from one batch of data used to train it over to another set of data used to validate those predictions. And there's actually different ways to do cross-validation. So cross-validation is a bit of an umbrella term for multiple ways to do that. We've already seen one way of doing that, which I'm going to scroll down to is known as holdout cross-validation. So that's what we've been doing so far. So this is just generating a train and a test set. Train tests split Um, that's what's known as the holdout cross-validation method. And this is exactly what we've been doing so far, which is you split your data into some type of split, usually 70/30, of a train and test. And then you train your model on this section of data and then apply it to this to evaluate performance. Right, so that's what's known as the holdout method. It is relatively simple. It's pretty fast to do. But there are more robust ways to try to divide up our data a little bit more evenly. Instead of just having one split, we can actually do many splits, which is the idea of the next kind of cross-validation I'll cover. But holdout method is one that we've already studied. It's the most basic type of cross-validation you can have. Um, so holdout, this is the most basic. And we've already been working with this type. Okay. So we've already seen holdout method. Let me explain to you a more sophisticated method, a little bit more advanced of a cross-validation, which is known as k-fold cross-validation. So this is going to be a little bit more advanced of a technique, but this is the idea of k-fold is that you take your data set and you split it into k number of what are called splits or folds. So you take your data and let's say k equals 5. So we have 5 splits here. Okay. So let's say k equals 5. We have 5 splits. So what we're going to do is we're going to train our model on k minus 1 of those folds. So if k was 5, we had 5 splits. We're going to take our model and train it on 4 out of 5 of those splits. So let's say it's these 4. We'll train it on these 4. Okay. And then what we do is the one split that's left over, we will test our model against that split. So we'll test here. Okay. Now this sounds very similar to the holdout method where we're doing a train test split, but it's a little bit this k-fold cross-validation is a little bit more sophisticated because we repeat this process that I just mentioned over and over for all combinations of the splits. So then what we'll do, this is just one trial that we'll do it again, but this time we will pick 4 different splits. So this time we might pick, let me do blue. This time we might pick this one, um, this one, and this one. And then those 4 we will train our data on, and then we will test against this one. Okay? And we'll repeat this. Repeat for all combos of the folds. Okay? So we'll repeat that. So essentially what we're doing is rotating through. Every time we rotate through, one of the folds is going to be left out as a test set. Now, this is a little bit more robust than just a train test split, right? Because we are exposing our model to more of the data in doing this, right? Because we're going to split it evenly into 5 or 10 splits. Those are pretty common number of folds to use, 10 or 5. Those are the ones I've most commonly seen. But we're going to, by rotating through which folds are being used for training, which ones being left out, we are exposing our model to more of the data this way than just doing a single train test split, right? So now what do we do with the results is every time we do this, we generate an MSE, let's say, or some type of performance metric. So let's say we generate an MSE from this guy, we generate an MSE from this version, and we generate an MSE for all combos. Each combo we generate an MSE, and then what we do is we average the metrics. or in this case, if we use MSE, we would average those together. So every time we do a fold combination and we keep four of them for training, one for test, and we rotate through all those combinations, we are going to generate an MSE for every combination. Then we're just going to average those MSEs to get a final. So the final MSE of cross-val of this k-fold, so the final metric is just the average of the performance on all of the fold combinations. Okay. So our final MSE, we just average all those MSEs from all of our combinations. Okay. Now, what's the advantage to doing this? It's way more robust of a estimate of the performance of the model because we're exposing it to basically all of our data, right? We're getting a sense of how it performs across all of those different folds, rather than just doing a single train test split, which is it's basic, it works, but it's a bit basic. So this is more robust estimate of the performance. Now, what's the drawback to doing this is that it's more intensive. So if you have a lot of data, this is going to be pretty expensive to do because you're going to have to, especially if you have a high number of folds, right? You're going to have to divide your data into K number of folds, and you're going to have to do this over and over again. And if it's a large data set, it might take your model a long time to train. It's going to be a little bit more computationally intense than if we just did a train test split. Okay, we just did a single like 70-30 split. We only do that once. We only train the model once, right? We train it on the 70, apply it to the 30% test data and evaluate performance that way. So we're only really using the model and training the model once. But in this K-fold, we're going to do it, K number of times, essentially. Or I should say one for every combination that we have to work through of all the folds. Okay. All right. Does that make sense? Any questions on k-fold cross-validation? So k is an important number here. It's how many folds, how many splits do you have? A typical value for k is going to be somewhere like 5 or 10. So 10 folds or 5 folds, those are pretty standard from what I've seen. But does the concept make sense, or is there any questions on it in terms of you're always going to leave one fold out, you're going to split it up into k number of folds, always leave one out, train on the rest of it, evaluate on that one that gets left out, and then rotate those through. And you're going to do that for every combination and average all those metrics. And by the way, there's going to be an easy function in Scikit-learn that will do this for us. So managing all these combinations will be really easy. It's actually just built into Scikit-learn. So we don't have to do this all by hand. Okay, this will be in Scikit-learn, it'll handle doing all these combinations of folds for us, and computing the average metric will be really easy. So um, we don't have to worry about that. We're going to see an example of this coming up shortly. All right, of k-fold cross-validation. But this is a really widely used technique. And again, like the purpose, you may be wondering, like, what's the purpose ultimately of doing this? It's to get a sense of if our model is going to perform well on new data. That's really what we want to know. Like, is the model going to perform well when I start to use it on new data that it's never seen before? And this k-fold is a decent indicator of that because we are varying which data it sees across many different folds, right? So it's kind of a good proxy to exposing it to different kinds of data each time and seeing how it performs, right? Because we're working our way through each one of the folds. There's always going to be one fold left out. We're going to change which fold gets left out each time, and um, that's sort of mimicking the idea of we're going to apply our model to new data and see how it performs. And it's new data every fold. How we know which model is best suits for which scenario because we have, yeah, that's a good question. So we're gonna learn this as we go along because we haven't covered all the models yet. But generally, the best advice I can give on that is you generally want to start as simple as you can get, and then if it's not performing well, then work your way up to something more complex. So we are going to have models that are simpler. We're going to have models that are more complex. The rule of thumb is to start with the most simple model that works. So you're usually going to have the same ones that you're going to try in the beginning. And linear regression is a very simple model. It's usually the first one you want to try for regression because it's the simplest. And for classification, we're going to have a similar, like logistic regression is the simplest kind of classification model we could have. So you usually want to start with that. And then if it underfits, like if we see it's producing a lot of error, then we work our way up to a more sophisticated model. So, um, that's the way it should usually go is simple to complex based on the performance. So we evaluate it and then we can repeat the process. If it's not performing well, we can try something different. That's more complex if it's underfitting. This is a good question. Is a model reset after training each K minus one fold? Yeah, it's essentially like a blank model every time, every fold. So, um, we imagine like you have a fresh model every K minus one combination. Yes. And the reason it has to be that way is because you don't want the other folds influencing the model that like on the next combination, you don't want the previous combination to influence the results on the next one, right? You want it to be a fresh evaluation on every combination of folds. Okay. All right, so let me describe to you a variation on what we just talked about with the k-fold. So there's another cross-validation known as stratified k-fold, and this is the same exact procedure as k-fold, except that this is used for classification. So when we do classification, we want to make sure that the different categories are going to be split amongst those folds in a proportional way. So what we don't want to happen is when we split apart the data. So let's say we're predicting spam, not spam. What we don't want to have happen when we do our splits is we don't want to have all of the spams end up in one fold and then every other fold has no spam, no spam, no spam, no spam, right? That's not very good because if we train against all these guys, we have no shot at predicting spam when they've never seen spam before. So stratify k-fold is used in classification and it's to make our splits ensure that they have basically a balanced number of categories for each split, so that we don't end up with certain splits with way more spams than not spams. So we do what's called stratifying, where we make sure the proportions are balanced across each split. So this is only really useful in classification, not really necessary in regression because we're predicting a value. But if we were predicting a category, like in classification, like fraud, not fraud, we don't want to do the split and have every single fraud example by bad luck in our shuffling and split end up in one split, and every other split has no examples of fraud, right? So we want to stratify this to spread out those frauds against all the other splits. Um, so uh, Again, Scikit-learn will take care of that for you. But if you're doing classification and you have an imbalanced data set, you really want to make sure you stratify k-fold. Imbalanced meaning that you have a different number. Like if you're doing fraud, not fraud, you have way more not frauds than frauds. Where that category is imbalanced, you want to make sure it's balanced across all your splits. So this is useful in classification only, not really regression, which is what we're talking about right now. But it's just a variation on this that ensures when we do those folds, um, the data is distributed evenly amongst those folds as much as we can. The labels are, I should say. Okay. So let's stratify k-fold. It's the same procedure. Once we have our splits, it's the same where we do k minus one of them, we train, test on that last fold, and then rotate through all the folds and average all the metrics. The same exact procedure. It's just the splitting itself is going to be balanced in a stratified k-fold. Okay, so holdout we've already talked about is just doing a single train test split. We've talked about that. One more variation that is a bit of an extreme version of k-fold. So it's actually the same process as k-fold, but it's an extreme version. Is if you set k equal to the number of data points. So you basically are. This is a really, really extreme k-fold where you basically are training on all the data. um, so you're training on all the data except one point, and then you test against that one point. Now, why would you ever do this? It's mainly for this reason here. It's to maximize the amount of training data that your model gets exposed to. Because instead of just doing five splits, which would be like these four folds are going to be used, and then we test against one fold. We're essentially going to use 99% of the data, right? One point is going to be left out. 99% of the data gets used to train. And then we're always going to leave out one point. And the issue is we're actually going to do that over and over and over again and rotate that one point to cover the whole data set. So we're going to train on 99%, leave that one point out, and then rotate through every combination of points until we've left out every single point, and then average all those together. So this is an extreme k-fold. Again, the number of folds is actually equal to the number of data points in this case. So we have every point is its own fold, and we train on everything but one, test on that one. This gets you the maximum size of your training data because you're basically going to have every point but one used in the training. This gets you the maximum size. However, it gets you the maximum expense, especially for large data sets. This is going to be usually you're not going to use this, especially for large data sets, because it's just too extreme. It's going to take you a really long time to work through every single point being left out. It's just going to take a while to do. So for that reason, the leave one out, that's why it's called leave one out, because you're leaving one out every single time, is rarely used. Don't really see it used that often, but it is an extreme version of k-fold cross-validation. Okay, but rarely ever actually used. I think the ones that get used the most are definitely the holdout method with just a regular train test split. And then the other one that gets used quite a bit is k-fold, or stratify k-fold if you're doing classification, but certainly k-fold in a regression case. Okay. All right. We're gonna do an example with these guys, so we'll do that next with the different cross-validation techniques. But any questions on what they are doing conceptually before we actually do the code example? Okay. Very good. All right. So let's see some examples. Let's go into our code and build a model and do the different cross-validation techniques on it. You're going to see it's actually going to be really easy to do, and it sounds complex, like doing the k-fold and leaving one out and testing. It sounds kind of complex, but I promise you, Scikit-learn makes it really easy to do. Um, and so we won't need to do too much besides just use the right tools from Scikit-learn. So we're gonna see that. So here we have some imports. The primary thing that's a little bit new for us is going to be these different kinds of cross-validation techniques. So we have our k-fold, we have our stratified k-fold, leave one out, which are those different cross-validation techniques. These are going to be used in combination with this cross-val score, which is going to keep track of the different metrics and then average them uh, while we do one of these cross-validation techniques. So this guy gets used in combination with one of these to, as we're going to see in the code, to average those metrics, doing the different folds, right? Doing performance against the different folds. Okay, and then of course we need a model. We're using linear regression. That's the one we've studied so far. And then we have just our regular metrics if we want to compute those, um, using maybe just holdout, right? And holdout, which is just a regular train test split, we could use these guys to evaluate performance. But in a more sophisticated k-fold style of cross-validation, we're going to use this to evaluate the performance. Okay, let's see. So we're going to be working with this housing with ocean proximity data. You guys should have this one. Uh, so you guys should have this one. So if you want to follow along and run it yourself, you can load that one in. I want to make sure that I have it. Let me pull that one in. So it should be this guy. I'm going to load that in so I can make sure I run it with you guys. Um, so let me run this. Do you guys have that data? The housing with ocean proximity? It's another housing data set. Um, but it's a little bit different than the ones we've seen before. It has a special feature for how close it is to the ocean, different locations. So it looks kind of like this. If we load it in and do our dot head, which is usually what we do, right? We can see that it's got these features. So it's got bedrooms, total rooms. Um, it's got median age. Now looks a little strange for total rooms and um, bedrooms and population, etc. But it's got those because it's representing an entire neighborhood. So it's an entire neighborhood, and we're looking at this. This is actually going to be our label is this median house value for the entire neighborhood. So what's that median value in the neighborhood? And this is the total number of bedrooms, total number of rooms, population, households. So how many houses are there? Um, Median income, and of course these are scaled. So these are likely times, thousands. Um, but that's our data. We could describe it. So we can see the average age, average median age, which sounds a little weird, but it's because again, this is the median of data within a neighborhood. Um, so the average of those is about 28 or 29. We have um, total bedrooms. We can look at the min. There's some data that only has one, so it's likely only one house in there, um, which is what this represents. There's only one house, so there is some neighborhood that only has one house, and we see the median. We see the minimum median house values there, and then the maximum down here is a pretty big number. 6,000 households is the largest that we have in any one of these neighborhoods. Okay. So just a little bit of description of the data. Okay, so then we could run .info. So this is let me ask you guys, were you able to load this? Were you able to run this? If you're following along, were you able to load it and take a look at .head? Okay, great, great. Okay. So we're able to load that and then look at .head. Perfect. Um, okay. Um, then we run describe, which gives us that usual kind of statistical description, so we can see some interesting stats about those. What do you guys notice about the .info? Anything interesting that we see from there? Is there any missing data? Any features that have missing data? Can we see? Object, yeah, object type usually is string. If it's an object type, that usually means string. Python, when we read it into Pandas, it usually is just a string. So that makes sense. Like we have mostly numerical features, but then we have this ocean proximity, which is a string. Yeah, total bedrooms has nulls. That's right. Because you can see here, this does not equal the number of rows that we have. So this is the number of rows, which is about 20,000 rows. That's a good size data set, right? 20,000 rows. That's decent. We're definitely missing some data here for sure. We could count how much we're missing exactly by running this is na.sum. Um, and so we see that total bedrooms is missing about 200. 200 rows are missing total bedroom value. Okay. And then one thing I wanted to look at is, yes, this is a string. So remember what we can do with those? That's a categorical. So ocean proximity is a categorical string feature. So we can take a look at its value counts, which is usually a good idea to take a look and see what possible values that feature could be. So if we look at our, what are we calling this? Housing data, ocean proximity dot value counts. So here's the different types that one can be. So there's some neighborhoods that are less than 1 hour from the ocean. There's some that are inland. There's some that are near the ocean. There's some that are near a bay. There's even 5 of them that are on an island. So these are the different values of the ocean proximity. So remember, you can always do that. If you see a string feature, you can always take a look at what its categories are. And it looks like most things are less than 1 hour from the ocean, but it's kind of evenly distributed here, um, otherwise. very few islands. But as you can imagine, like this feature is probably going to be important for determining what the value is, right? Probably going to be important. Okay. So we need to deal with these nulls if we're going to build a model, right? So this is all of our typical data prep. If we want to build a model, we're going to have to deal with these nulls. What do you guys think we should do with the nulls? What do you think for total bedrooms? What do you think is a good strategy to do? Keep in mind we have 20,000 points, 20,000 rows, I should say, and about 200 of them are null, right? So about 200 are null. Um, so what do you guys think would be like a good strategy to deal with those nulls in that case? Average, we can't ignore it because we can't ignore that column. We can't ignore the whole column. So something needs to go there. Probably don't want to make it zero. I think average is a decent idea. Probably don't want to make it zero because that would indicate that there's no bedrooms and yet we still have a bunch of total rooms. So it probably doesn't make sense to do zero. Average, I think average could be a decent one. Now, in this example, what we're actually going to do is rows. We're actually going to drop the rows altogether. Now, why are we doing that? It's because we have so much data and only 200 of them are null. Okay, only 200 of them are null. So we're actually just going to drop the rows. Now, that's a choice. That's a choice, right? Is that we could fill in with the average like you guys are suggesting. What we're actually going to do is just drop the rows. It makes up it makes up about 1% of the whole data. So it's not that much of it is missing. We can drop those rows. So that's actually what we're going to do here is we remove all the rows with the nulls by doing drop NA. So this just drops them. So those rows are cut out. It's arguable that we could replace. It's arguable that we could just replace it with something. And I think you guys have good thoughts, which is the average, a default, assume total bedrooms. We could try that, yeah. Assign a value based on comparable home value. Yes, you could do that too. That's a good strategy, is to look at the other rows that are similar to it and fill in a value. That's absolutely fair. In this example, we're actually just going to drop those rows. But I think that's totally valid. This is a choice. We could fill in a with different values, such as the average, total bedrooms, um, derive a value, etc. So we could derive something, which I think, Brent, you have a good suggestion. That's a good suggestion. We could derive something like that and fill in the blank, and I think that's totally valid. We could take the average of the bedrooms. I meant total rooms here. Sorry, total rooms. We could fill it in with the total rooms for that category, or for that row. Many options. In this case, we're actually just going to drop those rows because they make up such a small percentage relative to the 20,000 rows that we have. It's about 1%, right? 200 rows is about 1% of 20,000. So we're just going to drop them. But that's a choice. We don't have to drop them. We could fill in with something. Um, And if we did that, we would use fill NA rather than drop NA, right? After dropping the rows, how many? So it's just so after we drop the rows, after we drop the rows, it's just going to be we still have all our other rows are intact, right? So if we look at this now, we now have slightly less entries. So now we have this many rather than this many, right? We dropped those 200. But they're all filled in. Yeah, they're so all the other columns are still filled in. We're cutting out the whole row. So if you think about our data set, we have all these rows and all these columns. What we're doing is like if there's a null here, we're just getting rid of that whole row, right? And so we still have all the other rows intact. We can drop them because we have a good sample size. Yes. That's exactly right, Ronald. Yep, we can drop them because we have 20,000 rows and only 200 are missing values. So that's totally fine. Drop in A removes all rows that has any null. Yes, that's true. It will go ahead and just drop any row where there's any null, no matter what column it's in. Yes. Index, yeah, the index is not getting reset. That's true. So what you can always do is you can reset the index. So if you want to, it's optional. We're not really going to use the index for anything that important, right? But what we could do is reset index. Uh, we could do that, right? Which will reset it. So now it gets reset. But let me actually, I don't really want to do that. I'm gonna reset this. Um, but yeah, we could do that. Okay. So now, importantly, there should be no missing data of this new one where we dropped NAs, right? So now this is good. If you now the reason we had to do this is because if we try to build a linear regression and we have nulls in there, um, the issue is like how do you build a model where you have something like this and these are null? Like how do you multiply a number by a null? Um, we can't really do that, right? We can't really do that. Um, so therefore, we need to get rid of nulls. Like the null's not really going to work in there. So we need to get rid of them for linear regression to really have a chance to work, right? To train it and be able to use it. You got to get rid of those nulls. All right. Any questions so far? So we haven't done any modeling yet. We're doing some data preparation before we get to the modeling. And we haven't done any cross-validation yet. We haven't set that up. We're just doing our data preparation before we get to the modeling, right? So we've dropped some NAs, we've checked it. Um, we're gonna do one more prep step, which is to um, change that ocean proximity feature into something numerical because again, how do you build a model where you're inserting a string into those like beta 1, beta 2, beta 3 times the features? You can't really do that when it's a string. So what we're gonna do, and I'm gonna get rid of this because I don't think we really need that, is we are going to run this get dummies function, which is um, our get dummies function is our usual one to uh, our get dummies one is our usual one to get our one hot encoding. So this is our one hot encoding here. We now are going to have data that's like this, right? So we have ocean. So by the way, this prefix is OP, which is short for ocean proximity, right? So we have ocean proximity less than 1 hour from the ocean proximity inland, ocean proximity island, near bay, near ocean. So these first five rows are near the bay. So they have a one there and a zero in the other spots. So this is good. This one hot encodes that feature into these numerical values, right? Were you guys able to run that one? The get dummies? So the reason that, yeah, that's a great question. How did it go ocean proximity? It's because that is the only string feature we have. That's the only one we have. So it's going to look for any non-numericals and one hot encode those, however many there are. So whatever objects we have, which are strings, it's going to automatically one hot encode those. Yeah, we could have, right. We could have went here and did, right. We could have done ocean proximity. But we only have one of those features, so it's just going to do that to the whole data frame on that one feature. So what we're going to do is go ahead and split it into an X and a Y, which the X is always what includes our features. The Y is what we are trying to predict, which is the label. Now, in order to separate those out, what we're going to do is assign X to be the variable that is our data frame minus this median house value column. So what this is doing is it's not permanently dropping because we're not dropping it in place, but it is returning us a copy of the data frame with the median house value column left out, right? It's dropped. So this is something we want to do because that will the rest of it will contain our features, right? So this will temporarily, or I should say, return a copy of the DF with median house value dropped, right? Median house value dropped. So we go ahead and drop that one. Uh, Now, remember, it's not permanent. It's just giving us the remainder of it, which is this housing data dropping this, and it's assigning that to X. And then we're taking the actual median house value column from the original data and assigning that to Y. So this is going to be our labels, right? So this is what we are trying to predict. Okay, so that is our Y, and that's always how it is. X is our features, Y is our labels. Hopefully that makes sense. What this is doing is this is going to get rid of that label column and everything else will be our features. And then this will just assign the label column to Y. All right. And then what we can do is pass X and Y into our train test split function, and this will generate the holdout set. So if we want to do the holdout cross-validation, this is how we would do it, is we would split the data into X train, X test, Y train, Y test, using train test split. So this is what we did last time. This would be for holdout cross-validation, right? Where we are just have that one set for testing, one set for training, one set for testing, I should say, right? So this is a pretty standard train test split. We pass in that X, we pass in the Y. We use a 30% test size, which is pretty standard, and random state so that we get the consistent shuffling if we were to run this multiple times. We get that consistent randomization. Okay. So we have that. And so now our X train is a percentage of the data frame of the 20,000 rows. And the X test is 30% of that. So it's only about 6,000 rows, which is what the shape of that is. Yeah, X is our features. So we're putting all of our data in that is our features into X. And so the most efficient way of doing that is to just take our data and drop the median house value column because that's our label column. So we just remove that. The rest of the data is our features. So that's what this X is, right? It's all of our feature data, all of our columns that is not the label column, essentially, is what that's doing. And then Y is our label column from our original data, right? Y is our label column. And so this will contain all of our labels, which is the median house value. X contains every column but the one we're gonna. So we ultimately decide that, but X is everything that is not our dependent variable, which is what we're predicting. So we're removing what we are trying to predict from X. X should be everything else. That's always how it's going to be. X is always going to be all of those independent variables that we're using to predict the median house value. So we are going to predict the median house value. We need to remove it from X. So we're taking everything but that column. So it's the whole data frame. It's the whole data frame minus this one column, which is the dependent variable, right? Exactly right. Removing the dependent variable and keeping all the independents. That's exactly right. Exactly right. So think about it in terms of the model. Let's go back to the features, right? Think about it in terms of the model. We are trying to predict this value. We're building a model to try to predict this. So we are going to make sure X is everything but this, right? So this is actually just Y. That's our label. That's our dependent variable, right? That's Y. Everything else is belongs to X. Everything else belongs to X, including all of these. Right. We choose this one to be Y because we're building a model to predict that. That's our label. All right. So we use X and Y to do our train test split. So we have our training features and our test features and then our training label and test labels here. Pretty standard there. Okay, so this is what's new is if we want to do k-fold validation, what we're going to do is create a k-fold object. So we have this k-fold from Scikit-learn that we already imported. We are going to create a k-fold where we are going to specify how many folds we want. So that is the in splits parameter, as this says. Um, this is going to be, in this case, we're going to do 10 folds. That's pretty standard. So I think the typical number of folds that I've seen and I've worked with in my career is usually 5 or 10. 5 or 10 folds. is the standard. Okay, so we're doing 10 folds in this case, and we're setting a random state because we're going to do shuffling. So in order to produce those folds, we're going to shuffle the data first and then split it into 5 folds, right? So this k-fold object is going to manage creating these splits for us, right? These even splits. I know I didn't draw it even, but it's going to manage these 5 folds for us, and it's going to shuffle the data and assign them to these different folds. And then what we're going to do is use those to do our training. We're going to execute the cross-validation using this k-fold object. Okay, so we create the k-fold. We initialize our model as well. So of course, in order to train something in the k-folds, we're going to need a model. In this case, we're using linear regression, right? Which is the model we've been studying so far. So you have a linear regression. Now, look how easy it's going to be in order to execute cross-validation. Is all we need to do is create a cross-val score function, or I should say, use the cross-val score function from scikit-learn. So we use that with the model we want to train. So our model goes first. So that's the linear regression object. Then our data, so our features and our label for our training. And then let me skip over this for a second. I'll explain what this is in a second. Um, but then we are using the cross-validation technique is our k-fold. So this is where our k-fold object goes in the CV parameter, which is cross-validation. So what cross-validation strategy are you using? We're using k-fold. And the k-fold we're using is this one we defined up here, kf. So we're putting that right here for this. And then in jobs um, allows us to parallelize this. So if we set it to -1, that's the default. It will actually train across the different combinations in parallel, which speeds it up. So you want to keep this to -1 if you can. So um, now let me describe the scoring. So what this means is we put in our metric here. And so you can put mean absolute error, you can put in mean squared error. Those are the two that we can use. And the reason it has a negative in front of it is because we want to find the one that has the lowest score. That's going to be our best model, is the one that has the lowest score. So we take the absolute value. I'm sorry, we take the metric and we take the negative of it, because the highest scoring one is going to be the closest to 0. So it's just we use the negative of the metric, because on the number line, like the highest scoring one should be the least, I should say the maximum negative that we can get. That's going to be closest to 0. So if here's 0, this will be like -1 is better than -10, right? So something that scores the maximum negative absolute error would be closest to 0. And something that has more is going to be on this side. So this is only the reason we need this is only just to keep track of the scores of each individual fold. Okay. So the reason we can do that is at the end we can kind of see which combination performed the best. It's going to be the one that has the highest value of the negative, which is closest to 0. That's just a convention. Yeah, it's because the cross-validation is looking to maximize the metric. So um, whatever has the best score is considered the best performance. But we are using something where lower is better. So we take the negative, and like the highest negative would be closest to 0, right? The highest negative is going to be closest to 0. So it's just because like we want the lower score to be the best. The lowest score should be the best. So we take the negative of it. And so something that is more negative is going to be worse. Yeah, that's the reason. So something that's down this way is going to be worse. Okay, so it runs this, and what you can see is if we actually print this out, if we print out our k-fold scores, what we should get is 10 different scores. And you can see we have 10 different scores here, which are all negative because we're taking the negative of the absolute of the mean absolute error. So what we would be looking for here is we want to take the average of these scores, but take the absolute value of them to get the best performance. So this is capturing like this is the score on the first fold combination. This is the score on the second fold combination. This is the score on the third fold combination, and on and on and on. And these are the absolute errors. Okay. These are the absolute errors. So if we take a look at computing the average, which by the way, we don't need this import because we're using the NumPy average, so that's fine. We can take the absolute value of those and take a look at the average MSE, or sorry, MAE. Now, I want you to think about this average performance. So this is our performance right here on the cross validation. This is our average MAE across all of our fold combinations. So that's an indicator of our performance, right? Um, for the cross validation. Now, what are the units of our original the original median value? They're already in the thousands, right? So if we go to that feature, they're already in these hundreds of thousands. So this is not a very good error. It's kind of high, right? Because it's in this is 49,000. That's how far away we are in absolute value on average is $49,000 dollars on the median value. That's not very good. So this score is not very good. So this model is not performing that well, and we can see that by comparing this error to our actual data. So this is right around 50,000, and our median house values are in the hundreds of thousands. So on average, we're 50,000 off when we make a prediction. That's a significant amount, right? It's a significant amount on average when our data is in about the hundreds of thousands here. So we have a significant amount of error, 50,000 relative to to our units that our data is in, right? So this score is not very good. Um, and so we see that from the cross validation. So look how easy the cross val is. Again, we just do cross val score. We put in our model, we put in our data, we put in our cross validation strategy here, which is k-fold, and we can generate these metrics across all the fold combinations. So it's this function is taking care of rotating those and doing every combo, which is the 10 different combinations here of the folds. 10 different instances where you have, 10 different folds are the ones that are left out for evaluation. So it's managing that for us using this data, right? Using this training data here. Um, and we generate these scores. Okay, so that's k-fold. It's not hard to do. All you have to do is just use a cross-file score. And we could change this to mean squared error. We could do that too. That'd be pretty easy. So that'd be no issue. We just happen to be using the absolute error here. Of course, we could use squared error. Were you guys able to get this to run? K-fold scores? It produces an array of 10 different scores, which should make sense because these are we're splitting our data into 10 different folds, right? 10 different folds and leaving one out to do our evaluation on. So the one that gets left out every time is what's producing these scores. So there's 10 different ones get left out when we rotate through all the combinations. And so we average these scores and we get about 50,000 in error on average. What do you think would be acceptable? So if we're predicting the price, like if we're a real estate agent, we're predicting these prices and they typically are, yeah, close to zero would be great. That'd be fantastic. Closer to zero would be better. The average is 206,000. So 50,000 is a decent percentage of that. So you can compute it as a percentage, right? So 50,000 is a decent percentage of that. Probably you want this to be less than 20,000 would be about 10% error. 20,000, right? So maybe like 30,000 somewhere in there. Yeah, 10% would be 5% error. 10,000 would be 5% error. That's true. That's true. So that would be much better. So being closer to zero, like the smaller the better, of course. Of course. But yeah, I would say an acceptable percentage of error is probably 20%. Probably 20%, which would be like 40,000 or less would probably be acceptable. Usually when we build models, um 80% accuracy is usually considered decent. Usually considered decent. 80%. So I'd say 40,000 or less would be kind of ideal. Does that make sense to answer the question? That's a good question. What value is acceptable? I think probably less than 40,000 would be ideal. That's right around 20% error. All right, so that's k-fold. Let's do just a regular holdout now. So this is just using our training and test data, doing model.fit and calculating an MSE on the test data. So this is just the holdout strategy here where we just have this is less robust, but it's a lot quicker to do and easier to set up, right? So this is using the holdout strategy. So just a regular train test split. Are we going to rebuild the model? No, not necessarily. There's some things we could do, most likely. And like one thing we did not do was scale our features. Remember I said that's a pretty important thing to do, is to scale our features. We did not do that. So that would be an enhancement to this that we're going to. So I actually do think we'll do that later. Yes. So I think we will actually do that now that I'm thinking about it. Yes. One of the things we can do is scale these features using like a min-max scaler or a standard scaler. That's actually going to help us. That's going to help us do better predictions. So that's one thing we could do. But yeah, we'll try to see if we can get better. It should help it. Yeah, usually you want to scale the data. That's something we didn't do in our preparation step. We did a lot of the things we should do. We removed nulls and we did one-hot encoding to the proximity feature, like this one. Those are good to do, but we didn't scale any of the features, right? We didn't scale any of them. It will have an effect. It usually when we scale it, it'll be a better model. It'll learn a little bit better if we can scale the data. So that way, like these like ages aren't drastically different than like in scale than total bedrooms or income, those kind of things. So we usually want these to be in a similar scale range. So I think we'll scale them coming up in a bit, and it should help the model. We've talked about that before, right? Scaling usually is a good idea to do when you're prepping your data for modeling. No, you want to scale your test data as well. You're going to do both. You're going to scale your training data, you're going to scale it. So that's actually a good point you bring up is any transformations you do on your training to build your model, you should also do on your test set so you get an apples to apples comparison. You should always do the same transformations. Yes. Would scaling data impact K? Yeah, it could make it better. It could yeah, it should impact it. We should get a better model so when we do the different folds, we'll get better scores. Yeah. It will impact. Uh yeah, if they're so that's a good point. If they're going to use our model, then yes, they have to scale the data as well. If we build the model on the assumption that the input is scaled, then yes, they have to also scale their data when they're using it with our model. That's true. I mean, not really. I'll show you why. There's something that's actually going to make it easier, that will automate doing the scaling for them, so they don't have to do the scaling manually. It'll happen automatically when they use the model. I'm going to show you something that's going to automate that, which is going to be called a pipeline. So that part will be automated, and they won't have to do that. So it won't be heavy on the user. No. In theory, it is, but Scikit-learn has a really helpful tool to make it easy to do that. So I'm gonna show us that later on in the notebook. No, the data is not for a single house. It's for like a neighborhood. So there's a certain number of households in the neighborhood, and we're predicting the median house value of that neighborhood. Yeah. So there's a certain number of households. There's like a median income, a population, certain number of people that live there. Proximity generally of where that location is. It also has a latitude and longitude. So, and a median age in that neighborhood. So yeah, it's not just a single house. Okay. Let's go back to this was the holdout strategy. So this is a lot simpler. This is just model.fit, right? This is just model.fit on the training data. And then we can predict on the test features and generate test predictions. And then we can compute our error on those. We can compute our error amongst the test predictions and our test label. So that's our useful mean squared error function, right? To compute the MSE. Let's see what the MSE is. So MSE is right here. Um, Now what we could do is we can take the MSE and we can take the square root of it. So let's actually do that. Let's do np dot square root of the test MSE, and we get 67,000. So that's pretty high on this. So when we just now look at the difference of that, right? When we just do a train test split, um, when we just do a train test split, we get a worse score because it's not as robust, right? We're not showing that to many of the other folds. So we get a lot more error this way on the test data. So this is actually worse performance just doing the train test split. This is a really high error. Yeah, we can. We can. I'm gonna show us how the scaling will be done automatically. Yes, we can. There's a really easy tool to do that will scale it automatically. It's going to be later in this notebook. I'll show us it. All right, so just to recap this, this is fitting the model. This is fitting the model. This is making the predictions, right? Model.predict. So this is making the predictions, and then this is calculating the error, the mean squared error, which is looking at our test labels versus our test predictions, right? And this is computing the distance, the average distance away from these values to these values, right? And then we can also compute the R squared, R squared, and we see that it's not a very good R squared. 65, it's not a very great model, because closer to one would be better. So this is not very good. We know that. We knew that from the cross-file score, but this is just doing a holdout where we do a train and test split, right? So it's a little bit simpler, but it's not quite as robust. It's not quite as robust as the cross-file, but it works. We can do holdout. Um, we can do holdout to quickly evaluate a model and see if we need to make any adjustments. It's a little bit quicker to run. Okay, and any questions on it? Does it make sense what we're doing here? Model.fit to train it, predict to get our predictions. This is pretty standard, right? To train is the model.fit, and then to use the model to predict, we predict on the test features. So this is passing on all of our features into this model to generate predictions for every row. That's something I also want to point out that may be a little bit confusing, is this is a data frame. So we're passing in a bunch of rows of features with columns, right? So we're passing in a bunch of data that looks like this. And what we're doing is essentially making a prediction for every row. So this will generate a prediction. This row will generate a prediction. This row will generate a prediction, and on and on and on. So this predict will predict for every row. And so we end up with this collection of predictions here for each row. And we're comparing those to the labels that we have for those rows from our supervised learning, right? From our data set. So that's truly supervised learning, right? We have the examples and we're comparing those to what our model is predicting to get our performance. All right. So let's try the other, just so you can see it, the leave one out. Now the leave one out cross validation is going to actually work the same way, where we put in the leave one out strategy inside of the cross val score. Now here we don't need to specify how many folds there are because we know how many they're going to be. It's going to be the number of data points, right? So which is actually going to be quite large because there's 20,000 rows. So this is going to be extremely intensive because we are doing 20,000 examples and leaving one example out to be our validation, and then doing that across every 20,000 examples. So we could do it though, just to see how it works. We have this again, leave one out. We generate our cross-val score from our model, our data, and then same scoring that we had before. But this time we change our cross-val to be, instead of our k-fold object, we have our leave one out object, which is this. Um, and then we could run this. We can compute our average across the all of the folds. Now, this is going to be a lot bigger of an array. It's going to be a 20,000 size array, and we're going to compute the average across it. So let's do that. It's going to take a moment because there's lots. So if you notice it when you run, it's going to take a little bit of time to run because it's running across all 20,000 examples and leaving one out. So you have 20,000 and then one left out to test against. So it's quite intensive. You can see it's taking a lot more time. It's still running. It's taking a while. Okay, just let that run. Still running. So if you guys try running this, it's going to take a little bit of time. Hopefully that makes sense why it's taking so long, right? It's because it's instead of doing 10 folds, it's putting every data point but one as the training set and then iterating through all 20,000 points. This takes a while to do. Let's see what RAM, our memory is a little increased. Okay, still running. That's okay. I'll let it run. Come back when it's finished. Yeah, exactly. This is giving us our performance evaluation. This is like the average error across all of our different folds. Now, this is the extreme case where we have the number of folds equals the number of points, right? So it's an extreme case, but yes, it's just like K-fold. It's giving us that performance estimate. Okay, I finished. It's about the same, right? This is still around 50,000. Not much difference, right? Still right around there. But look how much longer it took. That took 2 minutes to run. The other one was pretty instant, right? So this took about 2 minutes to run. So um definitely yeah, definitely don't want to run this too often. I think that it's generally preferred to do k-fold if you're going to do cross-validation. Generally want to do k-fold or just the regular holdout train test split. Generally better than doing leave one out. It's just going to take too long, and it results in about the same kind of score as the K-fold. Okay. Any questions about the cross-validation that we just did? Okay. Good. And as this says here, that the stratified k-fold is usually used for classification. Again, we're not doing classification yet. That's going to be in lesson 4. So we don't need to worry too much about that. Just for regression, regular k-fold is preferred, right? Because we don't need to worry about distributing categories amongst our folds in any regression problems. And as we see, the error is kind of high. There's going to be some things we can do to improve that, which will be later on. We'll learn about some more advanced models. This signals that the performance is bad. We probably need a more complex model. One thing we could try before we try a complex model is to do scaling. We will try to do scaling. I'm going to show us how we can do that coming up in a nice streamlined fashion. But outside of that, if we still had bad performance, we would likely need to use a more advanced model. And we'll learn about more advanced models in the next lesson. And what's great is some of those advanced models can actually be used for regression. So they have variations that can be used for both classification and regression, which is pretty cool. So I'll point those out when we get to them. Um, okay. So what I want to talk about now is a way we can combat overfitting. So if we have overfitting, which remember that is the case where the we see good performance on the training data, but then it doesn't generalize over to the test data. We get poor performance on the test data. There's a drop off there. That would signal overfitting. And one way of combating overfitting is to do something called regularization, which we're going to talk about next. So the key idea in regularization is to change our the change the way we train. Essentially, what we're going to do is modify our training uh, error function, or sometimes called the objective function or loss function. We're going to change that to add a penalty to penalize excessive complexity. Essentially, the way that we're going to penalize is by making sure the size of the coefficients doesn't grow too much, which should mitigate overfitting. Because remember, in linear regression, what we are learning are the coefficients, right? We're learning the beta 0, the beta 1, the beta 2, and on, however many betas there are, beta n. We're learning all of those guys through the regression error function. We're trying to minimize that error function. That's how it trains. We talked about that on Monday. Um, so what we're going to do is basically penalize these guys growing too big and making sure we kind of keep them small so that no one coefficient has a dominant effect on the model. And this should help with overfitting and complexity. It should make the model simpler because all the coefficients are going to be encouraged to be smaller. They're not going to grow too big. And this has the effect of making the model, so basically make the model simpler. Make the model simpler is what these regularization techniques are essentially trying to achieve. Is remove complexity, make them a little bit simpler, make these coefficients smaller so that you can generalize a bit better and prevent overfitting. So we want to prevent overfitting, right? Is what we want to do. So there's going to be a penalty, and I'll show you where that penalty gets added and kind of what it looks like. But to control the level of that penalty, we are actually going to introduce another parameter to our model called alpha. Alpha is going to scale the penalty. So if alpha is really high, that imposes a stronger penalty on the coefficients, which will make the model a lot simpler. So the higher the alpha, the simpler the model we will get. And the risk with that is we actually underfit. So if alpha is too big, we may underfit the training data a bit too much because it will make the model way too simple. And I'll show you what this means mathematically in a moment. Um, but on the other hand, if we have a lower alpha, this will have a lower penalty. It's a weaker penalty term, and that'll lead to a model that is a bit more complex, which could risk some level of overfitting. Um, so there's still the risk of overfitting if you have a low alpha. And of course, if alpha goes all the way to 0, there's no penalty at all. So you're back to your original linear regression, which could risk a lot of overfitting, right? So you generally want to pick an alpha effectively, and actually we're going to see what's the best way to pick alpha. We're actually going to learn how to do that. I'm going to show us how, doing some tuning techniques to pick what alpha should be. But a pretty industry standard alpha that most people default to is alpha equals to 1. So just 1, which signals that there should be some penalty. We just have alpha equal to 1 as a standard penalty. We don't want it to be too high. We don't want it to be too low. Like we don't want it to be a fraction. But a penalty of 1 is usually good enough. Okay. I'm going to show you where that comes into play in a moment. But the whole purpose of doing this is to mitigate overfitting, right? That's what, and doing this penalty is called regularization. So going beyond just regular linear regression, adding this extra penalty to the training process, to penalize large weights, large coefficients, is known as regularization. Okay. And there's two common penalties that are added. So there's actually two different variations on the penalty. We're going to study both of them, and they're known as lasso. So if you take linear regression and add a particular type of penalty, it's known as lasso. If you add another type of penalty, it's known as ridge regression. We're going to study both of those and what their differences are. But these are the primary two regularization models that are used to take both of these take regular linear regression and just modify the training process a little bit in different ways, two different ways, using that alpha um, to penalize the terms in slightly different mathematical ways. So we're going to learn about these two guys, lasso regression. Both of these are just offshoots of linear regression. So the underlying model is still linear regression. It just adds different types of penalties to the training process. So both of these are still in the family of linear regression. In fact, in Scikit-learn, they both are still from the linear model family inside of the linear model module, which is where linear regression comes from. So there's still linear regression. They just have different styles of penalties added to them, which we're going to see. Okay. So just to recap that, regularization is the process of adding a penalty to the training to discourage complexity. In this case, we're going to discourage large coefficients, and this should help prevent overfitting. And so these are going to lead us to two different offshoots of linear regression that have two different penalties, lasso and ridge regression, which we're going to study next. But they function the same way as linear regression. They will just have different penalty terms added onto their training process to discourage again those large weights. Okay, any questions about regularization before we first look at we're going to look at our first variation on our first regularization technique, which is going to be called lasso regression. Okay, let's look at lasso regression. So what is lasso regression? It's actually lasso is short for least absolute shrinkage and selection operator regression. Um, and this will function by adding a particular penalty to the linear regression model. So again, it's based on linear regression. That's the underlying model. It's just that during the training process, we are going to add a penalty which has the effect of shrinkage of the weights. That's why it's called shrinkage. It encourages smaller weights through that penalty. And it also will shrink some of them so much that they'll become zero. And so it has an effect of kind of selection, which means that some of them get wiped out to zero. And this means that whatever is left over is kind of what's selected as our features because the other ones will have zero weight applied to them. So this penalty will really favor small weights and penalize really large weights. In fact, it will favor small weights so much that some of them will actually be shrunk to zero during the training process. And the ones that are left over are the ones that are what we call selected because they are the ones that remain in the training after the other ones get coefficients of zero. Now, when you make some of the coefficients zero, you are inherently making the model simpler, right? There's less features involved in the prediction that are less features that have an effect on the prediction. So this definitely makes the model simpler. This lasso, this shrinkage and selection process makes the model simpler for sure. Um, and this is supposed to reduce overfitting, right? If you make the model simpler, it's not as complex. It has less of a chance of memorizing training data and not generalizing over to test data. So our whole goal with regularization is to make our model better at generalization, right? Over to test data from the original training data. Um, so how does this happen? We have to go back to the uh, training process. If you guys remember, I wrote out this equation a little bit earlier, which is the distance. This is the sum of squared distance between our labels and our prediction. This is basically the mean squared error calculation that we're trying to reduce when we build our model using the training data. So this is just in standard linear regression. This is the um, sum of squares distance, right? So this is what the model is trying to minimize when it learns these coefficients. So when it learns these coefficients, it's trying to minimize this guy. Minimize. It's trying to find the betas that minimize this quantity. Mathematically, that's what it's doing. And there's a algorithm that will discover what the best betas are that actually minimize this. That gives us the line of best fit. Right? That's what we've been talking about for regression. Now, in regularization, here's, by the way, here is that same thing, but we've just inserted our model for the predictions. This is our model, just a fancy way of writing down our model, right? It's the beta zero plus all of these betas. So beta 1, x1 plus beta 2, x2 plus on and on and on, right? That's what this means. If you're unfamiliar with the sigma notation, it just means sum. So it's the sum of all these guys are this term. So this here is just a regular linear regression training, regular linear regression training. So the training process solves for these parameters, right? It solves for these weights. We discover what those are by minimizing this quantity. That's the whole training process. But when we do lasso, we add a penalty, which is this. Here is our penalty. So basically, we take our linear regression training, which is this, and we add on a penalty, which is this. And you can see exactly what this penalty, when you minimize this penalty, it's when these weights are small. So this encourages, so minimizing this quantity encourages small weights, encourages small betas, beta I, right? You or in this case, beta J. Sorry. This encourages small beta J's because we want this thing to be minimized. Minimized. So what's going to make this minimal is, of course, the line of best fit and small weights, right? Are going to bring this error down the most. So and here's our alpha, right? Here's our alpha. So you can encourage a higher penalty with a larger alpha or a lower penalty. If alpha equals 0, what happens to that term? It just goes away. So if alpha equals 0, there's no penalty. And we're back to regular linear regression. We just have regular linear regression because we have no penalty at that point when alpha equals 0. So the smaller alpha is, the less penalty we're enforcing in the regularization. Okay. Now, what happens is in reality, when you train with lasso, so this is lasso, is this particular penalty. This is called the lasso penalty, or sometimes people call this the L1 penalty. L1 just comes from the fact that this is the first power or absolute value. So it's not a squared penalty, it's a single power penalty there. But when you add this lasso penalty, what can happen is it does, because you're minimizing this, it does encourage some of these weights to become 0. So if you're really trying to get the lowest quantity of this, the lower the better. What makes this thing lower is, of course, if some of these go away. If some of these go to 0, then that of course will lower this as much as possible, right? So what happens during the training is some of these coefficients actually they're encouraged to be small because of this penalty, but some of them will actually become zero in order to get the best model, the best fit. Some of these will actually get so small that they'll basically become zero. And that means that feature basically has no effect anymore. It's been the model has been simplified, right? That feature no longer really has an effect. So just to call out the alpha again, if alpha is zero, basically you have your linear regression. You're back to linear regression because alpha zero is just wiping this out, and you're back to linear regression. If alpha is infinity, now if alpha is infinity, that's an extreme. So if alpha is infinity, the only way to make this minimize is if all your coefficients are zero. If every beta is zero, then this will lower the error as much as possible. So you basically have no model. So if all coefficients are zero, you have no model, and that's useless. So you don't want your penalty, you don't want your alpha to be huge, is what this is saying. You also don't want your alpha to be small. You're basically back to linear regression. So you want something in between. And the typical value is alpha equals one. Typical is alpha equals one to have some level of penalty there. So just a regular penalty term. But we are actually going to have a way to test and evaluate which alphas are the best. Um, Basically, you can have you can have a penalty that's close to zero. You can get rid of this if just a regular linear regression performs pretty well. You can basically have no penalty in that case. Yeah, so near zero, or like it could be that adding a little bit of penalty actually helps the overfitting, and it could be really small. One thing that we're basically going to do is have a strategy to try out different alphas, try different alphas, and evaluate performance. And then we can decide which. So that's what we're going to do is have a strategy to just plug in different alphas, generate like train the model, and then see what its performance is and see if those alphas are good. Which alpha is the best? We can evaluate that because we can train the model and see what its performance is, right? Yeah. Yeah. So we'll do that. We'll practice that. Okay, great. Any other questions about this lasso regression? So remember, this is linear regression here. This is how you're training to find the betas in linear regression. So this is just linear regression um, training function there. We're adding a penalty, which is this is the lasso penalty there, right? We're adding that. This is known as regularization. And the goal of regularization is to prevent overfitting. So you add a penalty here. This makes the model simpler, which prevents overfitting. It helps you generalize better when it's simpler. Any questions conceptually on this? We're going to do a code example with it coming up, but any questions on this? Yeah, so that's the thing, Ronald, is you may be willing to sacrifice some accuracy in order to generalize to unseen data. Because remember, that's what we're really trying to get after is we may be willing to sacrifice some accuracy on this training data in order to have it perform better on the test data. right? We may be willing to do that. That's an okay sacrifice. As long as like if it generalizes better, that's what we want. That's what we're trying to do here is add a penalty, make the model simpler, and help it generalize better to new and unseen data, right? That's that picture I've been using with the train and test split. Where is the square? So in the model, there's no square. So remember, the model is this equation that has no squares in it, right? It's beta 0 plus beta 1 x1 plus beta 2 x2 plus beta n xn. That's the linear regression model. This is the now this is the model, but this is the equation that helps us train and find the betas. This is what we find the betas with. So we'll continue. We were talking about the lasso regression, which it takes linear regression, right, which is this optimization, and adds in a penalty scaled by the alpha. And what that does in order to minimize this whole thing, it encourages these to be small as possible, which makes the model simpler, right? The weights don't get overly big and complex. They tend to stay small. And in fact, some of them can even go all the way to zero, which makes the model even more simpler, right? So let's practice using it in code. It's actually really easy to use. It's going to be essentially the same style and code as linear regression, except we're just going to have to put in our alpha parameter when we use the lasso. So here we are. From the linear model family, right, which makes sense. It's a linear regression offshoot that has this penalty in it during the training. We are grabbing our lasso regression. It also has a version of the lasso that we're going to take a look at that is used for cross-validation, which is really convenient as well. So it has a cross-validation lasso, which is a really convenient combination of basically cross-val score and lasso all in one. So it actually is really nice to use that way. So we'll take a look at that example. But we are importing it. The main thing is going to be the lasso model here. We're going to be using a different data set for this one. So not the ocean data, but this hitters data, which is a baseball data set. So it has 322 rows with 20 different columns, and it looks like this. So you want to download that one. Hopefully you guys have access to that one. Um, so I will upload it into this. So give me a moment. There's that. And then we can run this. Okay. So we are displaying the data, and so it has the hitters' names, and then it has a bunch of different statistics. These are all baseball statistics. If you're unfamiliar with them, that's okay. It's not a big deal. But just different baseball stats here. Okay, were you guys able to load that? If you're following along, were you able to load that? You should have access to this data, the hitters CSV. This is the one we're going to use for the lasso model to build a lasso model. Yeah. Okay. Able to load that one. Perfect. Okay, so able to load that one, and we take a look at the head. So we're actually going to drop this unnamed column because we don't care about their name. It's actually just the batter's name, which is not going to be useful in modeling. And remember, that's generally true. Like an ID, a user ID, like a customer ID, a name, that's usually not going to be useful in any kind of modeling. So we're actually just going to drop that column and we're going to do it in place. And axis equals 1 means we're dropping that column. So we're going to drop that. And we should no longer have that column, and we have all of these guys now. So you want to run that. This will drop that. This will drops the column in place. And now we can see we have this data where it's now removed. So that column is now gone, and now we have these guys. Um, do you notice anything about this from the info? It looks like we have a couple categorical features, a few of them, league and division and new league. What do you notice about this? Nulls, yep. So there's definitely some missing data there that we're going to have to deal with. So it looks like there are 59. Um, there are 59. Now the alternative to doing that is we could just use our usual code where we do df dot is null, um, and then we do dot sum to total those up across our different columns. And we can see that we have 59 of those in the salary column. So this is the standard way of doing that, right? Standard way of doing that. And we have 59 of those. 59 of those. So we have to deal with it. Any ideas on how to deal with it? Any ideas on how to deal with it? This is 59 out of 300. So what do you guys think about that? It's a little bit different than 200 out of 20,000. A little bit different. We have about 60 out of 300. There's a decent amount. Any ideas on how to handle this one? Replace? Yep, we should replace. What do you think we should replace with? It's a floating point value. By the way, something unique about this that's a little different than usual too is that the this is actually the column we're going to use as our label. So we're actually going to predict the salary based on the rest of the features. So we definitely need to fill in these nulls, right? Because they're actually going to be the labels. We're missing some labels in our data. We definitely need to fill them in, yeah. So we're going to replace them. All right, so we will replace them down below. That's going to be coming up. We'll come back and replace them. Before we replace them, we're actually going to get our one hot encodings for those three different features we have. So we do get dummies with this. Now, of course, we don't need to do this if we just, so this code we don't need to do if we just pass in the D type here, which is, then we don't need to do this. So we can comment this out. So now what I want you guys to notice is this is the alternative to what we did before, where we are purposely just doing these columns, not the whole data frame, but just doing these columns. And then we can concatenate these one hot encodings. We're going to concatenate back to the data frame, right? So if we do our dummies and then do dummies.info, we can see that we end up with 6 new columns. And in fact, we can do dummies.head and take a look at what those are, right? So these are League A, League N, Division E, Division W, New League A, New League N. Okay. So these are our one hot encodings for these three different features, which are strings, right? So those features were strings. If you go back up, those were our only string features we had. So we've one hot encoded those so we can use them in our model. What we need to do is just concatenate this back to our data frame, right? So we just need to concatenate it back into our data. Okay. So what we're going to do then is um we're going to grab Y as our salary, and of course we're going to fill nulls on that Y coming up shortly, but we're going to grab Y as our salary and now before building a full X, we're going to take a look at X numerical as our data frame minus these columns. The reason we're doing minus those is because we are going to concatenate our dummy variables back into this that are going to replace these guys. So we're going to replace these anyways with our one hot encodings. We don't want the strings. So we're going to get rid of those. And we're also going to get rid of the salary because that's going to be part of that's just the label. So we don't want that in the X, the eventual X. Are you guys able to run this one? Hope I'm not going too fast. Are you guys able to run this? And does it make sense? What we're doing is we're putting our labels in Y, which is what we usually do. So we're going to predict the salary and we're getting ready to build X. But before we first want to get rid of those one hot the strings. This is getting rid of the strings and this is getting rid of the label. And that's going to be part of our features. What we need to do is build our final X by concatenating our dummies with this. Do you guys see that? We're going to concatenate our dummies with this to build our final X. But prior to doing that, we need to get rid of these string columns here. So we're dropping those from the data frame and getting a X numerical here. You can see the columns of that are just these guys here. So the results we need to concatenate this guy into this, and then that'll be our full X, all of our features. Okay. So you can see X is going to be pd.concat of this with our dummies. And uh, instead of doing this, I'm actually going to do the full dummies. We don't need to pick just a few columns. We're actually going to do our full dummies here and do X is equals 1. Now, the reason that's the case is because this will get rid of one column per feature and basically assume that if you have a zero, the other one should be a one. If you have a one, the other one should be a zero. So it basically makes that assumption because we only have two of them. So whenever there's a one, the other should be zero. So you can get away with just having these three, but I think it makes more sense to just have the full dummies. But by process of elimination, you can get away with just using two of them because anytime you have a zero, the other feature would have been a one, right? And vice versa. When there's a one, the other feature would have been a zero. So we do that one. And you can see all of our one hot encoding features end up back in there. So this is the code that I want you guys to run. I think it makes more sense. It follows along what we've been doing, which will concatenate our dummies back to our features here to build out our full X. So now X is all of our features. Remember, X contains all of our features now. So X contains all of our features. And so we have all of this now. Okay, were you guys able to run this one? We have Y, we have X. We still need to deal with the nulls in Y. So that's something we still need to deal with. But hopefully you have this now. All of these are numerical. So that should be good with the model. That's one thing about X is our X should have all numerical features, right? Because it's going to go into a model to learn those betas. So it needs to have all numerical features, right? These are going to be all numerical, which makes sense. We did one hot encoding to change all those guys to numerical. Sorry, I'm scrolling down. Okay. We do fill in the null later. Okay. Okay. Any questions so far? So we're just getting our data ready. We haven't applied the lasso yet, but we're just doing some prep. Now, hopefully you guys recognize that these are some standard steps that we're taking when we do our modeling. We have to do these data prep steps. They're necessary. And so if it seems like it's a lot of work, that's because it is. It is work that you do to prepare your data to get ready for modeling. You have to do that. Okay. So we're doing that here. Now we're gonna do our train test split because we're gonna do holdout here. So we're doing a train test split with a test size of about 0.25. So again, anywhere between zero point 0.2 to zero point 0.3 would be okay. Um, so uh, it's our choice. We could do zero point 0.2, we could do zero point 0.3, we could do anywhere in between there. We're doing 0.25, that's fine. That's okay. So we build our train test split right there. So pretty simple, and we've seen that a bunch of times with our X and our Y data frames there. We have our train test split. Okay. Now what we're gonna do is do our scaling. So we didn't do this last time, but we're gonna do this now as because we should get in the habit of doing that. Is we're going to go ahead and scale our features, and we're going to use the standard scaler here to do that scaling. Okay. Now we could use min-max scaler. That's fine too. We're just going to use the standard scaler here. And remember, we are going to use the standard scaler from Scikit-learn, and we're going to transform our features uh, according to our training data. So we have our pre-processing standard scaler here. So we import that guy, and then we build our standard scaler and fit it on the training data only on the numerical features. So that's which is going to be uh, all of these guys. So we're doing the scaling on all of these guys. Now, something to note is that we are not scaling all of these one-hot encodings, mainly because it doesn't make sense to scale those really. They're 0 or 1. They don't need to be scaled, right? They're already 0 and 1, so they don't need to be. Even if we were doing min-max scaling, it's going to put them between 0 and 1. It wouldn't affect it really, right? So these one-hot encoding features we're not going to scale because they're always going to be 0 or 1. There's no need to scale them really. But we're going to scale all the other features here that are floats. So that's these guys here, these numerical features we're going to scale. Okay. We don't really need to scale the one hot encoding. It's pretty much already scaled. Oh, you should change that. Go back and rerun this, but make sure you have your data type as int in here. Make sure you add that in there to change that over to integer and rerun that, and then rerun the concatenation. So make sure you run this, and then make sure you rerun this and rerun the concatenation part, which is this. Okay. So we go ahead and fit the scalar to this data, and then we're going to transform our training features, those numerical features. And then we're going to transform these features, the test features in the same way. So we're going to perform the same transformation from the scalar on the test data. So that's something really important I want to note here is that we always scale both the training and test data. We always scale both. Of course, we're going to train the model on the training data, but we are going to also test it on the testing data, and it also needs to be scaled because our model that we build is going to assume scaled features. The coefficients that it learns are going to be assuming scaled features. So we need to also scale our test data in the same way. So we're doing that as well. So we scale that, and now we have our training and testing features have been scaled. No, we haven't replaced. We're going to do that. We have not yet. We're going to do that coming up in a minute. Yeah, we haven't done that. Um, it is the label. We definitely need to replace nulls. We just haven't done it yet because it's not in the features, and we're doing all of our pre-processing to our features. Yeah, so we need to, and we're going to in a minute. Okay, so if you look at the data now, it's all been scaled. So these are all z-scores. These are all on a much better scale now. And we still have our one-hot encoding features, which are 0 or 1. So th this scaling should lead to a better model than if we didn't scale. So scaling is really important. We can see that here. Okay. Now, let me ask you guys, were you able to run this scaling? Are you caught up to here? If you're following along, were you able to run the scaling? Okay, great. Great. Awesome. Okay. So what we're going to do now is replace nulls by calculating the median of the data. So what I want you to notice is that we are taking the nulls. Now this is on purpose, is we are purposely taking the nulls out of the median calculation. So we're skipping the nulls when we compute the median because we don't want those nulls to affect the median calculation. So we compute a median salary here, and then we fill our nulls with the median salary from the training data. So this is our choice. This is a choice to use the median, and it's also a choice to use the training set median for both train and test. What we could have done, this is an alternative that we could have done, is use the entire column and then use the median of all of the data to replace. That's really up to us. This is one way of doing it. We could have done, before we did the split, we could have filled in with the median earlier. We chose to do it here mainly because it doesn't affect the features. So we could have done this earlier and did it before we did the split and filled the NAs. Really doesn't matter that much which way we do it. But we do need to fill in nulls. We cannot have those be null when we put it into our model. So some way we need to fill in nulls. And so in this strategy, we're filling in our Y train with the median salary from our training data. And same with this. We're filling in with the median salary of the training data as well. But that's a choice. We could fill in with the mean, with the average. Um, we could fill in with we could do it with all the data together before we split it. We could have filled in with all of the median across the whole data set. Either one works. You can do it either way. But we did it later here to show that it doesn't really affect the features, so we can choose when we do it, right? It doesn't affect the features at all. So we can do all of our pre-processing on the features and then do our label filling in nulls um, if we have them. X numerical, make sure you're running this. X numerical was defined here when we split it apart from when we dropped these columns here. So make sure you're running this. This is X numerical. Gets defined there. So go back up this cell where we split apart the Y and we have the X here, X numerical. Make sure you run this. Make sure you run this, and then you can run these. Then you run this to build X. All right. Are we up to here with this filling in the labels? Because then we can build our model once we're up to here. We've scaled everything, we filled in our nulls, we've gotten one hot encoding. Yeah, it is. That's why we spend a lot of mo time on data preparation with Pandas, right? That's why we did all that Pandas work, for sure. Yes, there is a lot of work before we can build a model. Yes. Do you guys notice that? Like the modeling is relatively easy. It's just a dot fit and dot predict. The modeling is actually really easy. It's all the other work that's more involved, right? More code. The modeling itself is really easy. It's just one line of like dot fit, dot predict. Yeah, pretty easy to do. And then you do evaluation, which is a couple lines. Yep. These are the common steps. All these steps we're doing are very, very prototypical in model building let's just go back through this to see what we did, right? We imported our data. We dropped this name column because it's not useful to us. So we dropped that. We filled in the nulls eventually. But if there were any nulls in our features, we would have to deal with those as well by replacing them or dropping the rows like we did earlier. Um, and then we do one hot encoding because of course we can't have any string columns going in our models. We got a one hot encode. We then build our X and Y by concatenating the one hot encoded back to the numerical features. Then we train test split, right? That's pretty common. Or we could do cross-validation either way, a k-fold cross-validation. Then we scale. So we didn't do this last time, but this is something we should get in the habit of is scaling our features. So we do that. And now we're ready to model. So now we're ready to model. So that's this part. Okay, so let's do the model. The model is actually pretty easy to do. So we're going to use a lasso. So we have a lasso model here. Notice what we're setting our alpha to. So the big parameter we really need, ignore this iterations. We actually don't really need we don't really need that parameter. So just ignore it for the moment. But the big one that we're setting here is the alpha. So when we did linear regression, we didn't need any parameters to go inside the linear regression object. We didn't need any parameters, right? Because there are really no parameters of it. But for lasso, the important one is the alpha. And so we need to know what to set alpha to. Let's start with alpha equals 1. That's a good starting place. So a typical starting point for alpha um, is uh, is 1. So that's a typical starting point. And so we can set alpha equals to 1. This max iterations is the parameter that governs the training process because it is iterative. So if for some reason we can't converge to the right betas and we've run it for 10,000 steps, once we pass 10,000 steps, it will stop and just give us the betas at that point. But it will likely never hit this number. It'll converge before then. So we don't really need to specify it. So I'm actually just going to get rid of it. It's not really a big deal. It should converge before then. Um, but if we want to set like a maximum step size in the optimization, we definitely could there. But not concerned about that too much. But here's our lasso, and then we're just going to do a dot fit on our data. So look how easy that is, just like a linear regression, lasso dot fit, right? So we do dot fit. Um, oh, I didn't run this. I'm sorry. I got to run this. Okay. Actually, that's a good example of what happens when you have nulls, right? So it says our null contains NaN. That's because I didn't run this, but now that should be filled in. Now we should be able to run this. Okay, perfect. So it runs. Okay. So you can see what the intercept is. This is one of our coefficients, right? The intercept is 457. And look, now what's really interesting about the coefficients is look at what some of the coefficients are. Some of them are actually zero, which is really, so some of them ended up being at zero, which is very, very interesting. That means that those features get canceled out and they're basically not part of the model, which is really interesting. So we have all these coefficients and some of them are zero. Yeah, negative zero is just because of the convergence. Like they started out negative and worked their way up to zero. Negative zero really just means zero, but they just were coming from, they were like small negatives and ended up at zero during the training process. They were negative at one point and ended up zero. Um, so yeah, negative zero just obviously means zero. It's still zero there. So what's interesting is some of these features ended up being zero, which you don't usually see in a linear regression. So if we were to train this using a linear regression, we typically wouldn't see that. But some of these turn out to be zero because, again, we're encouraging those betas to be small. We're encouraging them to be small. And so um, what happens is some of them can be shrunk all the way down to zero, meaning those features don't contribute. That's a really simple model at that point, right? So we've taken something complex that includes all of these features and actually reduced it into something simple that only includes these features, right? So that's what it does. Now we need to evaluate this to see how good of a model it is. But that's what this is saying here in this text is that a positive coefficient indicates that as the independent variable increases, the dependent variable also increases. Negative coefficient means as the independent variable increases, dependent decreases because it's reducing the value. And Lasso is known for feature selection by shrinking some of them to zero, effectively removing those variables from the model, from the equation, right? Um, so that's what happens. Some of them end up being zero. Were you guys able to run this lasso fit, which is the training of the lasso model? No, it doesn't ensure there's no overfit, but it helps with overfitting. It's supposed to help by making the model simpler, and this is definitely a simpler model because it's removing some of the features from the model, essentially, right? Because some of the features aren't going to contribute. It's a simpler model. It doesn't mean there's not going to be any overfitting, but it helps prevent it. That's what it's designed to do, is help prevent it. Yeah, so higher coefficient, yes, the higher coefficient means it's a more important feature towards the prediction. Yes, that's what it means for sure. The higher the magnitude, the more of a contributor towards that prediction it is. Yes. And it's not just it could be higher positive or negative. There like a higher negative is also a pretty big factor, right? So you want to think about it in terms of absolute value. Does not guarantee but helps. Yes. It doesn't guarantee it, but it's designed to help overfitting, help prevent it. Yes, absolutely. Okay. So let's do some evaluation. So let's do, in this case, we are going to do our dot predict. Oh yeah. I'm not sure why that's the case. Interesting. We could try increasing the max iterations. Okay, that's why. Yeah, so then you get that result with the higher max iterations. It doesn't get cut off there. I think that's why you probably left this in there, which is fine. You get about the same numbers. Yeah. All right, let's evaluate this. So we're gonna to do evaluation, I want you guys to see again, we should get in the habit of doing evaluation, which is taking our model and predicting on the training and predicting on the test sets, right? So we predict on the train set and calculate our MSE, and we calculate our R2 score, um, or R squared score, I should say. But again, the MSE is the one we're really going to use mostly. But we calculate, so we do our predictions, and then we compare that into our mean squared error with our labels, and we go ahead and do the same thing with the test, right? So we do lasso.predict on our test features, and we go ahead and compare that with the test labels. And so what we're doing there is generating our MSE. So we take a look at our MSE and we get 84,000 MSE. And so of course we could take the what we could do with that is take a look at the MSE on the uh, we could do mp dot square root and do the square root of the MSE test, and we get 340. So this would be in the units of our label. So if we go back and look at our label for some of those, um, so we are in 300s and our data is like right around the 500. So of course, if we describe this, we could see what the statistics are of it. So we could do df.describe and generate that, but that doesn't look like a very good error, right? If these are in the 400s, that's not a very good error. So again, it's not a very great model. But one thing I want you to see is that it's not overfitting. If anything, it's actually underfitting, which is what this kind of MSE suggests, right? Because our error here is 84, excuse me, 84,000. Um, our our error here is 84,000. Excuse me. And on the test set, it's 116,000. So these two errors are both bad. So it's not overfitting. This is actually underfitting. So it's not overfitting, it's actually underfitting. And so that's the risk with something like Lasso is that it's making the model a bit too simple, and we actually risk underfitting, which is what happens. We have too much error across both the training and the test set. Overfitting is when we have really good performance on the training set, but bad performance on the test set. We're not overfitting. We are underfitting because our performance is not good either way. Even this R squared is pretty low. It's not even at 50%. Okay. So we do the evaluation, and again, the evaluation just comes down to making predictions and computing our error amongst those predictions to our labels. That's always what the evaluation is going to be. For MSE, what's the ideal MSE? What do you think it should be? What is so think about it like this. The MSE represents the average distance between our predictions and the labels. So if we're getting it right all the time, what's that distance going to be if we're always right? What's our distance from what's our distance from our predictions to our labels going to be if we're always getting it right? Zero. Yeah, there's not going to be any distance. It's going to be right. It's going to be perfectly aligned, right? There's going to be no distance there. So yeah, an ideal MSE is zero. That's an ideal MSE. So anything close to like the smaller the better for MSE. The smaller the better. For this R squared, it's a scale between 0 to 1, where 1 is the best. So 1 would be perfectly aligned predictions. And again, this is we actually multiply by 100 to get because it's a number between 0 and 1, so we get about 47%, which is not good. Okay. All right. Any questions on this evaluation? I want to show you something which is, yeah, that's true. The scale of it matters on the data because you should always interpret your MSE in the scale of your labels because your labels, like in this case, our labels, we could take, for example, we could easily, let's actually do that. Let's take the average of our labels on the training data, and we could see what those are. So the average is 500, right? The average is 500. And look at what our square root of our MSE is, which is in the same units as our original. So we have quite a bit of error, 340 when our units are right around 500. So that's quite a bit of error. Yeah, MSE of zero means our predictions are nearly identical to the test labels. Yes, that's what MSE of zero means. There's zero distance. So closer to zero, the better. But we talked about it as you really, so the rule of thumb should be what is your RMSE as a percentage of your typical value? So your typical values in the 500s, our RMSE is 340. That's just really high. That's over like 60% of that value. So that's just a lot. That's too much error. What we would love this RMSE to be is under 20% of the typical value. So that means on average, we are 20% or less off in our prediction. That would be good. That would be pretty good. That means we're like 80% accurate, right? That'd be pretty ideal. So you got to think about it in terms of this RMSE, which is in the same units as your labels. This is the RMSE, which is in the same units as the labels. So, and then to interpret this, we have 340 is compared to typical salary unit of 500, right? So this is quite a bit. When the typical value is 500 and we are off on average by 340 units, that's so much relative to the typical value. That's a lot of error. That's not a very good model, right? It's underfitting. It's definitely underfitting. Yeah, so that's a great question. What should we do from here? So, because we're underfitting, we should use a more complex model. So we're going to learn about those in lesson 4, but we should use something different. This linear regression is still too basic. Even with lasso, it's still too basic. Yeah, we're underfitting because but it could also be we're underfitting with a regular linear regression. We should test that out. And maybe it would be an exercise for you guys to test that out yourself. It shouldn't be hard to do. You already have all the data scaled. So do you see how you would do that? You would just come in here and build a linear regression rather than a lasso and do dot fit, and then you would evaluate it the same way with a dot predict. It's really easy to do that, and then we can compare that to this. It shouldn't be that hard to do that, right? And something you guys could do for sure um, is build the linear regression and actually compare it and see what kind of difference it makes. I mean, we honestly we could do it ourselves. We could do it right now. Maybe it's worth trying that. So let's build a linear regression for comparison. So we have our linear regression uh, is linear regression, and then we do dot fit, linear regression dot fit, right? So this will train it, and then we can evaluate it. So lin MSE is mean squared error, and then we can do our let's do our training. Let's do the training, and then let's predict. Actually, let me do that here. Y prediction train linear equals linear regression dot predict. And then we're going to predict on our training features. Okay, do you guys see what I'm doing? I'm building a linear regression for comparison. I'm doing dot fit here to train it. And then I'm making some predictions on the training set, and we're going to evaluate those. I'm going to replace that here with Y pred train linear. So these predictions. Okay, so if you guys want this code, I can paste it in. So let's see what the RMSE for just a linear model is. It's a little bit better. It's better for sure. So 289 is better than this 340. It's better. It's getting closer to zero. It's still underfitting though, right? And that's just on the training set. Let's look at let's do the same thing, but let's change this. Let's swap this out for test. And then let's do test. And then let's do test, test, and then test. Okay, so this is producing test predictions on the test set. We are generating an MSE test, and then we're doing an MSE test, which is using the test labels and our test predictions. And then we take the square root of that for our MSE, and then we're going to generate that. So still underfit. I mean, this is still high. This is still high on the test set and versus on the training set. So it's still pretty high. Even the basic linear regression is still underfitting. Still underfitting, right? Even without the lasso, which is lasso is supposed to help with overfitting. It's definitely not overfitting. It's definitely underfitting. But this is a signal that it's kind of overfitting because this is performing better on the training data and then it gets worse on the test data. Definitely gets worse, right? Did you guys follow? I'm just running this above. I'm running this above this. It doesn't matter where you put it. We could move it down. We can move it down to I just picked a new cell right here and ran it, but we could move it. Actually, let's do that. Let's move it down to after the lasso evaluation. Okay, so I just moved it there. And then let's move this down. So I just put it here after the after this. So this is basically the objective function, right, of the training process. So during the algorithm that runs when we call dot fit in scikit-learn, it's going to find these betas, right? It's actually going to learn what these best betas are for our model. This is our model here, right? It's the combination of betas times our features, plus an intercept beta. So that's our model, but we penalize those large weights in absolute value by adding a penalty term like this, where alpha is some level of penalty that we want to provide. Usually, alpha equals 1 is okay, but actually, what we're going to learn to finish out this section is there's going to be a systematic way we can test out different alphas that represent the level of penalty we want to apply to lasso or even ridge regression. So that was the lasso. And if you guys remember, using it was super easy. We worked through this problem with this baseball data. And we had, let's see, scrolling down, we split out our numerical data and we one hot encoded our categorical data, combined it back together. Hopefully that rings a bell there. And we actually scaled our data, which is pretty standard to do, is we do some type of scaling to our features, especially our numerical features, right? We want to scale those in some way, whether it's min-max scaler or a standard scaler, want to do that. And so we did that for this example. And then we ran the lasso regression, which is pretty easy to use. You just use the lasso object and you pick an alpha here. Again, we are going to have a way to test out different alphas that could be candidates, and we can see which one's the best. So I'm going to show us that today, coming up shortly. But that was the lasso. If you guys remember, we did that. Um, we compared that to basic linear regression, which is just this, pretty straightforward, just a dot fit and then dot predict, and then we can generate mean squared error. Um, Still not a very good mean squared error on this data. It's still fairly large. So it's still not, no matter which model we use, it's still not very good, but at least we can practice doing that comparison. That's what we did last time. We did this on Wednesday. Um, and then we saw that the effect of different alphas. Um, we had a lasso cross-validation example here. So beyond just using a regular lasso model, Scikit-learn has a lasso CV, which allows you to try out different alphas with cross-validation and figure out what the best alpha is. Now, we're actually going to have a different strategy that'll, instead of just picking random ones, we can actually supply multiple parameters that we may want to test, as many as the models may support. And in some more complex models, we'll have more than one parameter. Like Lasso only has the alpha. Um, Technically, it also has its max iterations, but really the only one that matters is this alpha. Other models have many more hyperparameters that we can change. And so we want a way to systematically test out those different combinations and to see which one leads to the best version of that model, let's say, the best results. So we're going to explore that coming up. So we had lasso. Now, this is where we ended last time. We had ridge regression. If you guys remember, this one is just a slightly different penalty. Um, it takes I drew it out for us. It takes the same penalty we had before. So it has that residual sum of squares error, which is the main one we use for linear regression, but it has a penalty with an alpha, and then it has the sum of the beta squareds, beta I squareds. So it has a penalty, but it penalizes slightly differently where it uses the square, not the absolute value. That's the ridge regression. And this has the similar effect of in order to minimize this, right? Because our goal in training a model is to minimize this quantity and find the best betas that minimize this. So generally, yes, you want to encourage lower values, but the once you get values that are a fraction, if you square them, they actually get smaller. So um, it's not necessary to shrink them all the way to zero. They will get smaller as soon as they're kind of below one. So they don't encourage it to completely go away, uh, like the absolute value does. It's just slightly different minimization. So what we see with the ridge is we don't see the features kind of get wiped out completely like we do with a lasso. In lasso, they get encouraged to become zero because that's kind of the only way to minimize an absolute value. But with squares, they can keep getting smaller and smaller and smaller um, fractions, and they don't have to become zero. It's not as harsh of a penalty. Um, so uh, the ridge was easy to use as well. And it also has an alpha that we can set. So it's literally the same exact code, just a different model, just slightly different penalty. And it results in different coefficients. You notice that none of them are exactly zero. Like with the lasso, you can get ones that are exactly zero. We don't see that with the ridge. You remember that. So we pointed out that last time. Notice the coefficients aren't zero. And then we can evaluate it. So we did our MSE calculation, which is a pretty standard thing where we use our model to predict on a training set, predict on a test set, evaluate those by computing the metric, like the mean squared error. And we can see if we're overfitting, underfitting. This is definitely the same kind of story we've seen with all these models is underfitting because the error is so big across both sets, across training and test. So it's definitely underfitting. Um, And same thing as Lasso, it has a cross-validation variation on it that allows you to try out different alphas and do different folds, so 10 folds, 5 folds, whatever, and compute try to find the best alpha that way. Okay. All right. Any questions on this so far from last time, from reviewing that a little bit? Hopefully that is jogging your memory a little bit on Ridge and Lasso. Um, where we're going to pick it up today is to finish out this lesson with one more model, which is going to be a combination of Ridge and Lasso. So you can actually combine them together in a linear fashion, those penalties. So you can actually have both penalties, the absolute value and the square. And when you have both penalties, that's a special model called the elastic net regression or elastic net model. So this is a combination of lasso and ridge together. So you have lasso, you have ridge, and then you have elastic net, which combines both of those penalties. Let me show you the equation. So here is the model. This is the same that we've always had. This is our usual model fitting for linear. This is a basic linear regression loss function or objective function that we're trying to minimize to find the betas. Notice how we have both of our penalties though this time. So instead of just having one of the penalties, we actually have both. So we have the lasso penalty and then we have the ridge penalty here. So we actually use both of them and try to find a balance of minimizing those two penalties. Okay, and notice how they instead of just a single alpha, we kind of have a balance on both of them. So we can actually weight the lasso one more, we can weight the ridge one more, we can weight them the same. We can change that around as much as we want. So they have two different weights there that they could be. Um, Now, what happens in reality is we're going to see this in the model is that usually what happens is these get combined into a fraction. So there's usually a ratio of lambda 1 to lambda 2, and this is sometimes known as the L1 ratio. And this is a parameter inside the model that we'll be able to set along with alpha. So we'll be able to set an alpha and then this ratio. the idea is that the ratio will allow us to control which one is more dominant. So if this number is bigger, the this lasso penalty will be weighted more. If this ratio is smaller, if it's less than one, for example, that means that the ridge regression is more dominant. So we'll have really this and this at our disposal. And um, alpha is kind of like you can think of it as a scale that is um, so lambda one, kind of like lambda one plus lambda two combined to equal alpha. So it's like um, our total level of penalty, and we can set that equal to one. We can set it equal to whatever we want. And so these will be in this ratio, and there'll be a total level of penalty that we can apply. So the model will actually use these two parameters when we do it. But that's how they're all related. Okay, so ridge uses both penalties. That's the only difference between Elastic Net uses both penalties. Um, so one thing I want you to notice is that uh, if we want, we could set this L1 ratio all the way to zero. Um, which if we do that, the only way this L1 ratio could be zero would be if lambda 1 is zero, so it would just revert back to ridge regression. So if this is zero, this will wipe out this term and we'll be back to ridge if the L1 ratio is zero. Okay. All right, so we have a elastic net model. Now it's used the exact same way as we did the other models in the code. So we have elastic net from the Scikit-learn linear model family, just exactly where we had linear regression, lasso, ridge. All of those came from this linear model. Elastic net also comes from there, and then the cross-validation version also comes from there. Um, so let's see. So when we build our model, it's going to be very, very simple, easy stuff because it's the same code that we always have. We just use the elastic net. We set an alpha. Alpha equals one is pretty standard, just like it is in the last one, ridge. That's industry standard is one. And then an L1 ratio of zero point 0.5. That's pretty standard as well. What the L1 ratio of zero point 0.5 is uh, that means that the lambda 1 to lambda 2 ratio is one half. So that's a pretty standard ratio as well. But again, we could set this equal to one and they'd be kind of equally weighted. L1 ratio of a half means that uh, the ridge penalty is a little bit more weighted in that situation. Okay. So once we have this model, we can do dot fit and we can run that on our training data and we can figure out what our parameters are, like our coefficients and our intercepts. Our model will have that. But more importantly, we can use our model to predict, right? So we could predict on a test set. Let me go back and load our data and actually run this. So we're going to be using the same data that we did for Lasso, which is I'm scrolling back up so I can load it. It's the baseball data here. Um, just run it from there. It's this hitters.csv, so hopefully you have that one. Let me load this. Okay, so we loaded that, and then that should load. Drop that unnamed column. We will get our dummies. and then concatenate those, split, scale. I'm just rerunning things. I'm rerunning things so we can see our model one more time. So we run that, take a look at that. That looks good. And then fill in the nulls on those. Okay, so we should be able to run our ElasticNet now. Okay, so let's import that and then let's build our model. So there we go. We build our model and the intercept is that. Now, of course, we can look at our coefficients. Let's look at that. Look at our coefficients. So remember, the coefficients are the betas. These are our betas that are in our model. So we could take a look at those now. It's somewhere in between. It's not a full lasso where we're going to see some of these be zero. It's not a full ridge. So the coefficients we get are different. They're somewhere in between there, those two models that we've already built. So not quite the same, somewhere in between there. And then we can use our model to make predictions and compute the MSE or the RMSE, I should say, as well. So we can take the mean squared error, pass that into the square root, and compute the RMSE. So still pretty bad. This is right around that 300 range of what we've gotten for our other RMSEs. So it's not like ElasticNet is any better than those other like linear or lasso or ridge. And that's not surprising because it's just adding those extra penalties. We don't expect it to magically get better. It's actually a more complex um, when we add those in, we're actually reducing it and making it simpler, and we need something more complex, I should say. So we're making it simpler um, by making it, penalizing our weights a little bit more, and so it's still not a good fit. It's not really surprising, right? It's still not really a great fit. And we can even double check that. We know our RMSE is pretty bad, but we can double check it with this R2 score, and it's still not good. Remember, a 1 would be really good. That'd be like a perfect linear model. This is still pretty bad. Okay. So as we said, the alpha controls the overall strength. So the higher the alpha, the more overall penalty we're supplying, which makes the model simpler. Um, but the L1 ratio determines the mix or that ratio of the lambdas, the lasso to the ridge. If you have it be exactly zero, you revert all the way back to if you put it at zero, you revert all the way back to ridge. One would be all the way to pure lassos. Somewhere in between, like what half is good. Okay. So this is another example of trying out different values of alpha in the CV to see which one works. Now, again, I'm going to show us in a minute a systematic way to do this, but this is just trying out different alphas that we set up uh, in this range. So we have different values between -2 and 2 logarithmically. So these are logarithm values that are between -2 and 2, and we choose 100 different alphas, and then we choose 100 different L1 ratios between zero point zero 0.01 and 1. And we run this cross validation with 10 folds. So this is quite a bit. So we were doing 10 folds and we're trying out 100 different options. Every time we do an option, we're trying out 10 folds to evaluate it. So it's going to take a minute to run. It's still running here. But again, what this is doing is trying out different alphas, and it's going to do a cross validation. And you guys remember the 10-fold cross validation is where we take our data and we divide it into 10 folds, and then we train on 9 of those, and then test on the remaining fold, and then we rotate all the folds 10 times. And that we average those mean squared error metrics together um, against those 10 different fold options to generate a basically like an average performance for that value of alpha. And we're doing that 100 times for all these different 100 alphas that there are and 100 different L1 ratios that we're trying with them. So that's quite a bit of processing, but it did finish. So we can see what our best alpha is and our best L1 ratio. So we get the best alpha is this, best L1 ratio is this. And therefore we can build a model with those with just these two guys as the alpha and the L1 and see how that performs. We build that model and then we predict on the test set and we generate the RMSE. It's just a little bit better. It's still not, it's just a little bit better, but it's still not good, right? It's still 338. It's just way too big. Remember, this is RMSE, so it's in the units of our target variable. So it's in the units of, if we go back to our data, actually, I could just print it out here. This RMSE. If I just do this, we could take a look at DF, or I could look at Y test, and you can see some of these values. These are these salary values in the hundreds, right? Some of them are in the thousands. But an error of like 338 is just too big. That's a really big error. That means we would be off by an average of 300 when our values, if we just do the mean, um, is only 550. As on average, it's 550, but we have this amount of error on average. So that's just a way too big of a proportion of error, right? It's just not a very good model. And again, we can verify that by looking at this R2 score. So if we go down here, still not very good. Here's some of our coefficients. So remember, you can always take your coefficients and line them up to your data columns so that you can get a sense of what coefficient belongs with what feature. So that's all we're doing here is just creating a series where those coefficients, instead of just printing out the coefficients, we're actually lining them up to the columns. So this tells us, remember, the larger it is, the more influence it kind of has on the final result. Either way, so like this has a big negative influence. This has a large positive influence. Okay, let me pause there. Any questions about the elastic net model? This model is a really good one to use when you are building a linear regression and it's performing well, but it's overfitting. This is a really good one to use because you can balance lasso and ridge. You can get the best of both worlds. So the main strategy is if you are using a linear regression and you see overfitting, meaning that it's performing decently. So on the training set, it's performing okay, but then on the test set, like it's not underfitting. It's performing pretty well on the training set, but then on the test set, its performance is much worse. That's overfitting. If you're overfitting, then this is a great model to use because we can try basically by rotating through different alphas and different L1 ratios, we can try out different strengths of penalty and different variations on lasso and ridge together. This is a really good model to use for those overfitting cases where linear regression is doing decently, but it's overfitting, right? So far, we haven't ran into that case because so far, no matter what model we've used, it's always underfit. So anytime we have those underfitting cases, it signals that we should likely just use a more complex model. And we haven't learned about those yet. We will coming up in lesson 4, but that's for this data, that's ultimately what we'd want to do is probably use a more advanced model because it's underfitting just using a linear regression and then using the overfitting variations of linear regression like lasso, ridge, and elastic net. Okay. Any questions on this on elastic net? The TV? Yeah, I think I have it. I could share it with you. I said that and now I can't find it. I thought I had it. I don't have it. I thought I had it, but I don't. If anyone does have that one. Yeah, I'll look one more time. I thought I had that one. Um, yeah, it's not in there. I had it. Let me see. Yeah, I don't have it either. I thought I had it in here. Yeah, I don't have that one. I don't have that one. I'll have to find it. I have this marketing data. I don't think this is the same one. I have this marketing data. I don't think that's the right one, but you can take a look at it. No, so for this example, we're using the same hitters data set that we used earlier for Lasso. No, that's an earlier one. That's from the very beginning of the notebook. So that's from this one. This is where it is. Sorry, this is where it is. You can find it here. That's right. It was from a URL. It was used in the very beginning of the notebook, and we did this. Okay, that's right. That's why I didn't have it downloaded. Okay. All right. Any other questions on the ElasticNet before I move? I'm going to move on to finding a systematic way to find the best hyperparameters. I'm going to show you a couple strategies to doing that. So far, we've just ran CV with some random choices. I'm going to show you a better, more systematic approach that's kind of the industry standard for doing tuning. Um, so I'm gonna show you that next. But any questions on the Elastic Net? Okay. And again, Scikit-learn makes it really easy for you guys because it just behaves the same way as any other model. You use the object and then you do dot fit and dot predict, right? So the dot fit is going to train it, and the dot predict is going to allow you to use that model to predict. It's super easy that way. Every scikit-learn model is like that, dot fit and dot predict. So it provides a really simple way to use basically every model. Okay. Let's finish up this lesson with a couple things. One of those things is going to be hyperparameter tuning. So what is this? The hyperparameter tuning is a systematic way to find the best parameters in a machine learning model. So a lot of machine learning models have what are called hyperparameters. These are not the betas that we learn during the training that's learned from the data. These are settings that we set ahead of time, like the alpha. That's a perfect example, like alpha or L1 ratio in the Elastic Net. We set those up ahead of time, and depending on what we pick for those, we get different performance, right? And so, what we really need is a systematic way to find the best settings for those hyperparameters as we are training our models. Um, the the main like idea behind this process though is going to be to systematically try out different combinations, as many as we want to try. And so we're basically going to have a strategy for tuning that is going to exhaust all the combinations of those hyperparameters that we want to try until we find the one that performs the best. And that strategy is known as grid search. Um, and essentially what it does is it sets up a grid which is basically like a matrix to say, okay, which parameters do you want to try? I want to try alpha and I want to try L1 ratio. Um, L1 ratio. Like let's say I want to try these two. So we set these up in a grid where we say, okay, I want to try this value, I want to try this value, I want to try this value, this one, this one, this one, and on and as many as we want to try. So we could set those up systematically, like a linearly spaced. Like I want to try every alpha between 0 and 10 spaced by one. Whatever, we can set up different ranges of those. But that's going to be in this grid. And then the L1 ratio, same thing. We can try out different values of these that we want to try. Let's say there's many of those. Maybe every tenth between 0 to 1, I want to try out. Um, so you set up your parameters and you can set up as many as you want in the grid. And then essentially what you're going to do grid search is you're going to work your way through every combination of those. So you're going to try out this combo, you're going to try out this combo, you're going to try out this combo. So the first value of alpha with every possible L1 ratio, then go to the next, try out the next value of alpha with every L1 ratio, and on and on and on. So we're going to try all combos in the grid. We're going to try all combos and we're going to find the lowest MSE combination. Find lowest MSE combo. So whatever leads to the best model is going to be the parameters that are deemed to be the best. And the idea is once we have found those, we know that we can go ahead and train a model with those best alpha and L1 ratio and on and on and on. Yeah, when you get so this goes back to the error. Remember that for a regression, the error is this measurement of how far off we are, right? So if we have a bunch of points and we fit a line through there, the MSE is measuring this distance, right? So what do you think is a good distance? Like if our model is perfect, what's the best distance from our predictions to the actual points? 0, yes. So the lower the better. The lower the better. So for an RMSE, the closer to 0, the better. However, the RMSE can be its units are interpreted in the units of our target. So what is deemed to be good is relative to our target. Like let's say our target is in the thousands, like it averages in the thousands. If we produce an MSE of 50, or sorry, an RMSE of 50, that's pretty good, right? Because our units are in the thousands and we're only on average, we are off by 50 units, right? Our distance away is about 50 units. That's pretty good. So the RMSE is relative to your target variable. Does that make sense? Yeah, it depends on the target. It depends on what you're trying to predict. So that's why we got RMSEs that were in the 300s for those hitters, but the average of the target was in the 500s. So that's a really bad proportion of error relative to the average target value, right? If our RMSE was 300, but the target was sitting in the 500s, that's just too much error. Way too much error, right? That's just too big of a value. Our predictions are just off way too much in terms of that distance. So this was a bad model. It was underfit. We know that from the RMSE. So yeah, the RMSE closer to zero, no matter what is good, zero is being perfect. But to know what's good, you need to know what your target is on average, and then think of this as kind of a ratio to that average target. I think that's the best way to think about it. Okay. So going back to this grid idea is, so the grid is just basically laying out all possible parameter combinations and trying them all out by fitting and predicting until and generating a metric like an MSE until we find the one with the lowest MSE. So find the lowest MSE combination and that will be the best. That will be the best combo. And then if we once we know that best combo, we can use we can use that alpha, we can use that L1 ratio and use that model going forward. We can use those parameters in our model. So this strategy, it has a name. It's known as grid search. So it is a hyperparameter tuning process that tries out all combinations. So what's the benefit to this is that we get to test out a lot of different combos of those parameters like the alpha and L1 so we can be confident what the best model is, right? So we can pick the alpha and L1 perfectly because we're trying out a bunch of different combinations on the data to see which one's the best. What's the downside? It's expensive, right? It's an exhaustive search. So if you have many different parameters and you're trying out many different combinations, it can get exponentially expensive to perform this search. Okay, so grid search is great, except for the fact that it can be expensive if you have many parameters with very wide ranges that you're searching over, because that's a lot of combinations you have to test, right? And especially if you have a lot of data, that's going to be expensive to do. So we're going to practice doing grid search, but that's the pro and con. The pro is that we get to try out all these combinations and see which one's the best. The downside is it can be expensive to do that if you have a lot of parameters that you want to tune for your model, and you have very many different choices that you're trying to evaluate for those, and it just creates a really big collection of combinations that you have to try out, right? That's the only downside to grid search. Now, on the opposite end of the spectrum of that is a randomized search or random search. And this will basically just do a sampling of those parameters from kind of fixed specified distribution. So essentially what you do is similarly, you define your range. So you say, I want to look at alphas between zero, or sorry, between, let's say, yeah, 0 to 10. I want to look at a bunch of different alphas, and I want to look at a bunch of different L1 ratios that are between 0 to 1, 0 to 1. And what we do is we say, okay, I'm going to restrict only testing 20, 30, 40 times. I'm not going to do all possible combinations. I'm just going to randomly sample something in this range and randomly sample something in this range. And so, and I'm going to perform that experiment a fixed number of times. So let's say I set the sampling where I'm only going to do 20 evaluations. And so 20 times we're going to pick a combo randomly. So I'm going to pick an alpha and I'm going to pick an L1 ratio. And we are just going to sample those randomly from this range. And we're going to use those and test those out. And then but otherwise it's the same as grid search, whatever is the lowest MSE. So whatever is the lowest MSE is the best. So we evaluate those, we sample, we train the model, evaluate it, whatever is the lowest MSE. is the best combo. Now, what's the benefit to this is it's a much more controlled experiment in the sense that we aren't going to iterate through every possible combination in the grid. We basically set up a fixed number of times we're going to try out stuff. The risk to doing this is that you're not exploring all combinations, right? Because you're randomly sampling, you may get unlucky and you may not stumble into the best. You can make samples and figure out what's the best amongst your samples, but you may not be covering all the combinations. Does that make sense? The grid search is going to try every combo. The random search is going to randomly sample those combos. So it's not going to try every single one. It's going to try a limited number, however many you set up. Now, if you set that number really, really, really high, now you're starting to approach a grid search because now you're sampling so many of those combos that you basically are trying them all at that point, right? Um, so that's the way the random search. So by the way, both of these use cross-validation in the sense that when you evaluate a combination, you're actually doing it with cross-validation. So when you do an evaluation, you're going to do probably 10 or 5 folds where you split your data and then you test it on the rest of the folds and evaluate or train it on the rest of the folds, evaluate it on one of them, and generate an average MSE to get your evaluation. So every evaluation is using cross-validation. And hopefully you can see why this would be so expensive for a really big grid, right? Because you're trying out many different combinations, and every combination is going to do a cross-validation procedure. So it's going to train 10 times and test against 10 different folds and average those together. It's going to be a pretty expensive operation for a really big grid, right? Of parameters. But these are the two kind of systematic approaches we have at trying out different hyperparameters. Remember, those things are called hyperparameters. These are those choices that we have before we train our model. Those choices we have that affect the performance of the model, like the alphas, the L1 ratios, those kind of things. We have control over what they're going to be. This is a systematic approach to find out what the best value of those parameters is going to be on our data, right? Okay, so before we practice this, we're going to practice with grid search first. Um, any questions? I don't know if it has a built-in. That's a good question. By time limit, I don't know if it has a built-in way of doing it, but you could certainly set up like a loop um to wrap around. Do you know what I mean? Like you could set up a loop where you check the time if the time elapsed as you're doing the search, if the time elapsed is greater than the time limit, then you can kind of break early. So it's not hard to implement that, but I don't know if it has that built in. I don't think it does because I don't think it really cares how long every evaluation takes. It's just going to exhaust all those, especially in a grid search. But yeah, I there's probably a way to manually kind of set up a time loop. So hyperparameters are settings that we have on the model itself. And a really good example of this is like the alpha and L1 ratio in the elastic net. So they're not things that we um, learn from the data directly, like the betas in the model. Like those get trained directly by doing the least squares process, right? By doing that gradient descent and all that optimization. Um, so these are not learned from that. They're actually set ahead of time. And so what we're saying is the best way to understand the effects of those is to try out different combinations of those until we land on the best one, right? So hyperparameters are those options we have in the model, like the alpha and L1 ratio in the elastic net. Many models have hyperparameters. We're actually going to see that in future models that we study. They have options that you can set that affect their performance. And so this is just a strategy to evaluate those different options to see which one's the best. Yeah. So again, hyperparameters, those are settings on the model itself that affect the performance of it. And basically, we have the two strategies here. We can set up an exhaustive grid and search through all of those until we find the lowest MSE option, or we can randomly sample potential options, try them out, and see which one's the lowest as well, and do that a fixed number of times, um, sort of like a fixed number of trials almost, which has a risk of not trying out every option, but hopefully you try out enough that you've explored the space a bit and you get some quality choices there, but no guarantees, right? No guarantees you try everything, which is what a grid search will do. It'll try everything. Okay. Now, luckily, per usual, Scikit-learn has something to manage this process for us in terms of grid search. Um, so in that way, we will not need to manage this process ourselves. We can just rely on Scikit-learn. And so if you're doing hyperparameter tuning, this is going to come from the model selection module inside of sklearn. So we're going to import from sklearn the model selection module. We have our grid search cross-validation. Okay, that's what the CV stands for, grid search cross-validation. So this is going to do that grid search strategy. We're going to set it up with our dictionary essentially of choices. So we're going to say, hey, here's the alphas I want to try. Here's the L1 ratios I want to try. And here's my other settings like uh, how many folds I want to use, what my random state is for the shuffling. So we'll set all that up. Um, and then we'll just run the grid search. And then what should come out of that is the best options for our parameters from the grid. And then we can use those going forward we can build a model with those best options, right? So we're really doing some evaluation here of what is going to be those best alphas, those best O1 ratios on our data set, right? And the only way to really know that is to evaluate them because they're not things that are learned during the training. Hopefully that makes sense, right? They're not things that we learn directly from training. They're things that we have to set and then kind of evaluate and see how they affect things. Okay, so we have Grid Search CV. That's going to be our primary tool to do the evaluations of the different hyperparameter options. Grid Search CV. We're going to set up our cross-validation object here. Now, I want you to pay attention to this is that it's a slightly different version than the K-fold we had earlier. So we've used K-fold before with a certain number of folds. This would be 10 folds, and we can set a random state for the shuffling that happens in the folds. But this is actually a slight different variation on it where it is a repeated K-fold where we do three repeated trials. Now, why would we do that? It's to be extra, extra, extra careful with the shuffling. So what this means is we do three different shuffles. So we do K-fold, we actually repeat it three times with three different shufflings. That's all that means. So the repeated K-fold is actually a bit beyond the just basic K-fold. What basic K-fold will do, we'll shuffle and then do our splits into 10 splits and then train on nine of those, test on the other one, and rotate through all the splits. We're actually going to do that process three different times with three different shuffles. And we're going to average 30 results instead of just 10. So repeated K-fold is just going above and beyond to do extra to repeat the K-fold three different times. In this case, only three. We could do more. But now, is that necessary to do? You could argue not necessarily, but it just provides extra robustness uh, beyond just our single shuffle and then split and then rotation of those folds, right? We're doing it actually three different shuffles So we're repeating our k-fold 3 times for every. Now, this is the thing is we're doing that for every evaluation. So it is going to be more expensive than just a basic k-fold. So we have 3 different k-fold trials that we're doing essentially. Okay. Hopefully that makes sense. This is the repeated k-fold. We haven't really seen that before. We've only worked with the k-fold, which would get rid of this repeats option and only have 10 splits in a random state for the single shuffle that we do, so we can recreate that same shuffle every time. But now we're actually going to do 3 random shuffles, 3 different trials. So one shuffle creates the and then create the 10 splits, evaluate, then go back and do another shuffle, another new 10 splits. So one thing that should be clear is that we get different splits every time because we're going to shuffle once, right? We're going to shuffle once and generate our splits. And then we're going to shuffle again, generate these splits, which are going to be different, and then shuffle one more time for 3 different times, right? And then get these splits. And then we're going to get 10 metrics here, 10 metrics here, 10 metrics here, and then average all of those together. So it's a bit more just going a extra above and beyond for a K-fold. Okay. All right, so here comes the fun of when you do grid search. Now, the grid is actually just a dictionary. It's a Python dictionary where you declare what your parameters are going to be inside the dictionary and you set up a range of values that you're go or a list. It can be a list, it can be a range, but some declaration of what you are going to test and evaluate inside of your grid search. So the grid is initialized as an empty dictionary. And then what we do is we say, okay, in my grid, I want to check different alphas. So we're going to add a collection of alphas in here that we're going to test. So let me make a comment there. We add a range of alphas to test. And this range this is just like the Python range. Um, this is just like a Python range operator here, where this is going to be so it's going to be every value between 0 and 1 steps with a step size of 0.1. So it's going to try a bunch of different alphas between 0 and zero point 0.1. Sorry, 0 and 1, stepping by 0.1. So it's going to try 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, right, all the way up to 1. So that's what this will do, and it's a NumPy range. So it's just all those decimals between 0 to 1. You can use either. That's valid. Yeah. You can do that to create a dictionary, or you can use the keyword dict. You can use either one. Either one works. Whatever you want to use. They're the same. Yeah. The reason people prefer dictionary is because sets are created with the same braces. So it makes it clear what you're creating as a dictionary if you use this. That's the only advantage, is it's just plainly obvious what you're making. Because technically you can make a set with the curly braces as well. Yeah, no worries. Okay, so we have our alphas here. So what I want you to notice is that we are going to try out different alphas, and that's the only parameter we are going to try in our ridge regression. So we're gonna try ridge, but just try different alphas in this range in our grid search. So the grid search CV takes in a model, it takes in our grid dictionary, which is really critical. We need that dictionary to declare what we're going to try. We need a scoring to find the best, Now remember, it uses the negative to find the lowest, which is going to be the least negative option. Otherwise, it wouldn't, just based on the optimization, it would look for the highest value. So the highest would be closest to zero in this situation. So we use negative. And again, we could use squared error. It's using absolute. We could use squared. Uh, either one works. More typical would probably be squared error, but absolute is fine. Here's where we have our repeated k-folds. We pass in our how we're doing CV. That can be it can be a k-fold object. It can actually just be an integer, which is say I just want to do 10 splits or 5 splits to do every evaluation. But these are the bare minimum that you need, just really the model and the grid and your CV, what metric you're using to evaluate what's going to be the best. And then this in jobs is to parallelize. If you have it set to -1, it's gonna try out all the grid options in parallel, which is nice. It's gonna help speed up the overall search. Okay, so let me mark that down as in jobs equals -1, tries out the combos in parallel. So in this situation, we actually don't have more than one parameter. We only have the alpha. So we're really just going to be systematically working our way through every alpha and evaluating which one's the best, right? With this. And notice that in order to use this grid search, all we have to do is call search.fit. So it works kind of like every other model does, right? It's the grid search dot fit, and we pass in our data. And we once this prints out the results, you get a results object, which has a best score and then a dictionary with your best parameters. So whatever your best grid member was or grid members, it prints that out, and you can from that we can grab our best alpha, which let's confirm what that ends up being. Oops, we need to import repeated k-fold. So we'll import that. Oh, I didn't. Let's do from sklearn dot linear model import ridge. Okay. Okay. So it completed the search, and what we found is this is the best score is 238 for the mean absolute error, and the best alpha that we got was zero point 0.9. So the best alpha that worked here, the one that gave us the best score was actually zero point 0.9 as the alpha. So what it did is it tried out everything between this range, and zero point 0.9 was the best. So it did cross-validation, tried out every single combo in our grid. So if we want, we could actually print our grid so we can see what our combinations were. So it tried out all of these guys, and the best one that we had was zero point 0.9. Okay. So pretty cool how that works. And if we had other parameters, like if we were doing a elastic net, we could add those into our dictionary and it would do all combinations of those. So if we did, so for instance, to add to our grid, we could do grid L1 ratio. This would be for like an elastic net, right? Now, the ridge regression by itself doesn't have an L1 ratio parameter, but just as an example, we could try out different ranges, similar range, different one, maybe an exact list, whatever we want to do. So this is going to try out different ones between 0 to 1 as well. And so it's going to try out every combination of these from this grid. Okay, if we did that. But again, the ridge regression doesn't have an L1 ratio. The elastic net does. So The ridge regression only has an alpha as a hyperparameter. So we're only testing out that one. Okay, so that's grid search, CV. Pretty useful. This is pretty useful in doing parameter tuning. Again, when you want to try out ranges of different values and you can evaluate those to see which one is your best. And then we can use that best going forward. So we can, for instance, this is what this code does below it, is it fetches the best. You can do it this way, or you can do it, the alternative is to do results.best params. And then you can just grab it like this, alpha. Either way, you can do dot get or like this. This is just a dictionary, right? And you can grab your alpha. So that's the 0.9. And we can pass that alpha into the ridge regression and go back and refit it to our data, and then use that model going forward. So the grid search really just evaluates those different options, tells you what's the best according to this score, right? And you should, by the way, you should interpret this score in the positive sense. It's only negative because we're purposely making it negative to find out what the lowest option is, right? Because the lower is the better. So we purposely make it negative to make it whatever is the least negative is the winner. More negative is worse. So it's the really positive version of it is the true result for the error. And they are a tool from Scikit-learn to put together your model with your pre-processing steps, so they kind of get automated together. And they combine everything into kind of a streamlined process. You're going to see what that looks like, but it's a really nice feature of Scikit-learn. Why would we care about pipelines? They help organize our code, so that we ensure that we basically always run the pre-processing steps before we train and use a model with the predictions. So it bundles those steps together, minimizes the risk of forgetting a step. Because one of the things that can happen is when you do pre-processing, if you're doing it on the training set, you have to do it on new test data as well when you put it through your model, because your model is training against that pre-processed data. So in order to make sure you never forget that, you can bundle it all together in a pipeline, which is going to make things really, really easy to use and make sure that those steps happen in a repeatable way. Um, and it makes things easier to deploy that model as well because everything is together in one pipeline. So in the industry, I've seen this a lot. Um, People will do their initial exploration steps and initial model building. They may not use pipelines right away, but as they've found their model, they'll generally move it into a pipeline and all their steps into a pipeline so that it's easier to work with when you're deploying it and actually using it in the real world. So here's what a pipeline generally looks like. It's from Scikit-learn. It's this pipeline object. And the pipeline is made up of steps that we're going to see that are various uh, basically kinds of preprocessing we've seen before, like a scalar or filling in missing values, those kind of things we can put here in the steps, which is basically a list. Steps is just going to be a list of scikit-learn functions that we can apply to data, one of those being a model. And then whenever we use the pipeline, it's basically, it's going to be something like pipeline dot fit or pipeline dot predict. So the pipeline kind of behaves like a model. It's just going to contain many more steps than that, like the pre-processing steps we've worked with before. Um, and it also has some capabilities for caching, so you can cache some of the data in memory, so that if you're reusing the predictions, it kind of goes faster. So there's some options for that too. I'm not too concerned about that at this stage, but the main thing is going to be filling out our steps and then using the pipeline. Okay. So some important bits of information about the pipeline is that it is going to be a sequence of data transformations that will have at the very end of the pipeline the model. because of course we're going to do transformations and then train a model or predict with a model. So every, oh, can you guys hear me okay? Not able to hear me. Thanks for letting me know. Can you guys, were you able to hear me so far? Okay, make sure, yeah, it might be on your internet or your yeah, it seems like it's good. So no, you can't hear me? Check your volume, check your headphones if you're wearing headphones. Oh, no issues. Okay, perfect. Okay. Yeah, local internet issue. Yeah. Okay. Always let me know. Always let me know because it could be the case that it is me. So, always make sure to let me know. But sounds like, yeah, you may want to check on that. Um, so, okay. What I was saying is every pipeline is going to have a sequence of steps that go first and then the model at the end. So the order really matters. So the order matters in the sense that we want our transformations to go first. Things like scaling, things like filling in missing values, we want those to be first, and then we want our model to be last because we want those transformations to happen prior to training or prior to prediction. So usually what you'll see in these pipelines is a model at the end, right? A model that's going to be at the end of the pipeline because we want basically our processing steps, then our training, or our processing steps, then our predictions. So everything in the pipeline though is going to be from scikit-learn. That's how it gets automated in the sense that all of those things are going to have fit and transform functions built into them so the pipeline can use them. And then the last step is going to be a model that has a fit and a predict. So it's pretty standard that the last part of the pipeline is just going to be a model. Um, uh, So we can, as we do more modeling, we're going to play around with the pipelines quite a bit and see how we can change up some of the parameters. Like if we want to change a model's parameter, we can actually adjust it to do things like grid search or cross-validation. So we're going to see some examples of some pipelines, but for right now, mostly what we're going to see is how to build one and then how to use one. And then as we get into lesson four, we'll get some more practice with pipelines because we're going to start using them quite a bit to build our models rather than do manual steps, all the manual pre-processing, and then kind of building a model from there. We'll just include all of it together in a pipeline. Okay, so the example we're going to do is with this housing with ocean proximity. So we've actually looked at this data set before. So we have this ocean proximity data set that has the feature of like how close it is to the ocean, like the bay or the less than 1 hour. Remember we had that and it had the median house value for different neighborhoods. So we're going to work with that one again. Let me make sure I have that one uploaded. You guys should have this one. It should be in your data sets. I can upload it here in case you don't have it though. Does this use multi-threading? I think it does. Yeah, I think in order to do it can do um I think it can do processing in parallel for some of the pipeline steps. Now, does it use that all the time? Not necessarily because some of it is sequential in nature where you have to do one step and then you do the next step and then you do the next step. So it's not like you can do them in parallel. In terms of the like you need to know the output of one step to compute the output of the next step. Um, so it can, but it doesn't always lend itself well. The thing that will use multi-threading is like the training process could be parallelized. Like the dot fit can be for some models, it can be parallelized. Not every model. So long answer is, or the short answer is that it depends. Depends on what kind of transforms you're doing and what kind of model you're using, if you can really take advantage of that. Okay, so we load our data here and take a look at that. Do you guys have this data set? Are you able to load it in? If you're following along, are you able to load it? Okay. And again, we've worked with this data before, so hopefully it's somewhat familiar. Remember, every row represents a neighborhood, and we're going to end up trying to predict this median house value as our target variable, our dependent variable. And we're going to use the rest of these features. Remember that this feature is in particular going to need to be one hot encoded, right? It's going to be one hot encoded because it is currently a string, and we need to turn that into a numerical feature, which is the one hot encoded feature. So we're going to have to do that, but we're going to do that as part of our pipeline. Okay, so we'll be able to include that in our pipeline steps to do one hot encoding, which is nice. All right, so we're going to split apart our data as we normally do. So we're going to create our feature data frame, which is everything but this median house value. So we go ahead and drop that column. And then our target is the median house value. So it is just that column here. Pretty standard. And then we're going to train test split and split it into 30% test data. And again, random state, you can choose whatever you want to be. That just affects the shuffling. So whatever, doesn't really matter what it is. It's just so that when you rerun this, you get the same result in the shuffle. Okay, so we have our train and our test. So you want to make sure you run those. All right, so what we're going to do is take a look at our data and see if we have any null values. If you guys remember, this data actually did have null values. You can see it here in this guy, and exactly how many there are is from the sum. So we have 162 nulls in this data, and this is just a training data. So of course, the test data could have that in there as well. So that's something we're going to want to make sure we fill in the blanks on any data set we use, whether we're using the training or test set. Like if we're doing training, we want to make sure that gets filled in. If we're doing predictions with the test set, want to make sure that gets filled in. So we should be doing that. Now, what we're going to do is use this data to help uh, train our pipeline or use with our pipeline. We need to construct our pipeline. So far, we've just split apart our data. We haven't done anything with our processing steps in our model yet. So roughly, this should be the flow of our pipeline. What should happen is we should be doing some type of feature scaling, some type of feature manipulation. So that could be engineering, um, that could be doing the one hot encoding. So extracting new features like one hot encoding. We are going to be doing that. And by the way, this is when we use our pipeline for training. It's going to look like this, where we do our scaling, we do one hot encoding, we have our model here. So that could be a linear regression, that could be a lasso, that could be a ridge, it could be elastic net. Whatever model we end up using is going to be last in the pipeline. And we're going to run this pipeline. Ultimately, we're going to run pipeline dot fit, right? We're going to run a dot fit function and we get a fitted model as the result of this pipeline. Then when we use our model for prediction, we use our model for prediction in this lower part. It's the same pipeline, same exact pipeline, but this model has now been trained. So we now have a trained model here. So the great thing about the pipeline is it's the same. This is the same pipeline that we're using here. So it's gonna repeat those same transformations. It's gonna do our scaling, it's gonna do our one-hot encoding, it's gonna use our model, and it's gonna generate predictions and generate we can do predictions, we can do evaluation like in a cross validation. We can use it however we want to use it. Uh, but notice that the pipeline makes it consistent between training and test. We're using the exact same transformations, and the model is last. It's either being trained or it's being used for prediction, but it's last. Our transformations are up front, which are things like our scaling, things like our one-hot encoding, right? Those happen first, no matter what data we put through there. We put our training data through there, we put our test data through there. They're going to go through the same steps, right? So that's the design of the pipeline. That's what it's supposed to do. So our job is to create those steps. So we need to create those relevant steps and then put them together into this pipeline. Okay. So that's going to be the code we're going to see coming up is we're going to build out these steps and then put them together into the pipeline. Any questions on this diagram? Does it make sense what we're trying to do with this pipeline? We want to have repeatable steps during the training, during the prediction process. Okay. All right. All right. So, a couple of things we're going to need is first of all, let's jot down what steps we're actually going to do. We're going to need to deal with missing values. So we're going to we're going to need a pre-processing step that fills in any nulls. We always need that, right? So if there's nulls, we're going to fill them in somehow. We're going to define how we do that in our step. Um, and we also need to one hot encode and we need to scale, right? Those are pretty standard steps that we've dealt with whenever we're building these models, right? So pretty standard things. Fill in nulls, one hot encode any categorical data, whatever, however much we have, and then go ahead and standardize, which is the scaling. So this just is the same word for scaling our numeric features. So we're going to define those. So that's why we're going to go ahead and import from preprocessing. We're going to import our scalar. Again, we could use min-max scalar here. We're going to use standard scalar, um, but we could use min-max. We have our one-hot encoder here. Now, usually when we do one-hot encoding, we use pd.get dummies. This does the same thing as that, but because we're going to be building a pipeline, we actually want the scikit-learn version of get dummies. So this is the scikit-learn version of get dummies here, and we have to use that version in the pipeline because everything in the pipeline needs to be an sklearn object. It needs to be an sklearn tool or object. So instead of using pandas get dummies, we're using one hot encoder, which does the same thing. Okay. In fact, this basically just uses pd.getDummies under the hood. Okay, so it just uses that anyways. It's just code that builds on that. Now, what's really nice here is we're also going to use from sklearn.impute, we're going to use a simple imputer. Now, what this is an automated way to fill in missing values. So this is a fancy way of basically doing the fill NA on a data frame. So it's simple imputer. We are going to basically fill in the blanks. What we're going to do when we create this object is give it a strategy of how to fill in blanks. Should you use the average? Should you use the median? Should you use the max? Should you use the min? Should you use the default value? We're going to tell it what to do in this object. Okay, so we're gonna use this as our automated tool for filling in missing values. So that's really nice. This is gonna be a critical part of our pipeline, an imputer that's going to fill in missing values. So we have that. Yeah, coding to reduce coding, exactly. We have our pipeline now. So we have our pipeline. So our pipeline is going to hold everything. So we need the pipeline object to hold everything, and that comes from sklearn.pipeline. So everything's going to actually go into a pipeline object. We're going to see how that looks. Um, and finally, we're going to, from sklearn.compose, we're going to use a column transformer. The reason we're going to do this is because we are going to specify for some columns, like the numerical features, we should be scaling. For some columns, like the categorical features, we should be one hot encoding. So the column transformer will allow us to map different transformations to different sections of columns, which is really useful. So this is actually going to be a critical part of our pipeline to apply to make sure we only apply this to numerical features and only apply this to categorical features, right? So this column transformer will help us um, to apply preprocessing to particular columns. Like that ocean proximity is the only one that really needs this, but every other column is going to need this, all the numerical features. So we're going to use this column transformer, and again, we're going to see how this looks, but just trying to give you an idea of why we're importing all these things. Okay, so let's import those. This mentions about the column transformer. We just talked about it. It allows us to have a particular column or group of columns get the right transformation. So again, uh, looking ahead to our pipeline, the numerical features are the ones that are going to need scaling, but the categorical features are the ones that are going to need one hot encoding, however many categoricals there are. In this case, there's really only one, which is that ocean proximity. To go back to our data, you can even see that in the info. There's just that one. And we see that here, right? Just this one string column that should be one hot encoded. All these other guys should be scaled, right? They should all be standard scaled. So this will allow us to specify those distinctions. All right. So let's get started building our pipeline. So this is going to be really cool. We're going to build out the pipeline. Um, let's extract our numerical data and our categorical data. Now, this is a really neat way of doing that that I'm not sure we've seen before. So what this does is we'll take our data frame, particularly our training data frame, and select our data. That's what this select D types does, is select data from it, which includes only the object type columns. So only the object types. Now, what's that? The object type is the string, right? So this should select only this column because it's in the include. We go here, include only object types in the result. And so this should only have our one categorical column, which is the ocean proximity. So housing cat is going to have a reference to our, it's going to be a list that has basically just our ocean proximity feature because this select D types will make sure we only pick object types and grab those columns. So this is a way to neatly grab our categorical features here by including the object types. Now, on the flip side, we can exclude object types and get everything else. So this is going to be all other columns, which is excluding the object. So this is excluding this, meaning we should get all of our numerical features that way. So this will be all of our numericals by excluding the object type. And this will be our housing num, which is short for numerical. So this excludes the object type, meaning all numerical features, right? All numerical features there. Okay. So if we were to, let's double check this. Let's sanity check this. If we were to print out the housing cat, this should be just the ocean proximity feature, which it is. So just that one. If we were to print out the housing num, this should be all the numerical features, which are all these guys. So it's just a reference to those columns so that we can use those later when we're mapping this transform needs to go to this column, like the one hot encoding needs to go to this column, and the scaling needs to go to these columns, right? And so we have those names of those columns already at our disposal. So we're just doing that. And this is just a simple check. Are you guys able to run this? If you're following along, let me pause there. Make sure I'm not going too fast. So the issue with a specific data type like that is none of these are ints. They're actually all floats. So if we did float, I think that should work. But yes, that's the idea. Great. I'm glad to hear that. You're right there with me. Great. Glad to hear that. Okay, so we have our columns picked out here, which we're going to use later. Okay. All right. So let's go ahead and build out our steps for each of these types. So for our numerical features, let's build out our pipeline steps. So what we're going to do is build out a numerical pipeline, and it's going to be a pipeline with a list of tuples. And the reason these are tuples is because every tuple has a name. So here, this is a name that it can be whatever we want it to be. So we're calling it imputer. We could call it anything we want. We could call it fill in the blanks. We could call it null filling, call it whatever you want. We're calling it imputer because that's a pretty easy name for it and accurate name to what it's doing. Um, but the important thing is after the name you give it, you put in the scikit-learn object that you are going to use to operate on your data. So in this case, we're using a simple imputer with a strategy of median. Now that's a choice. We could use a strategy of mean, max, we could provide it a constant default value. But what this means is we are going to fill any blanks we find in those columns with the median value of that column. That's the strategy for the imputer. So that's pretty cool. This is kind of an automated way to fill in the blanks using for any column using its median, right? And so we could change that. We could put mean here or max or min or whatever. Um, but we are filling in the blank on any column with its median. And the reason this works is because we are going to apply this pipeline only to these numerical features. So that is fine. We're not going to apply it to the categorical features. We're going to apply it to only those numerical, so it should have a median value, right? So that's totally fine. So we're going to now look at how we're constructing the steps. We have a list of tuples. Here's one tuple, which is the imputer with a simple imputer of strategy median. And then we can have as many tuples as we want, which represent processing steps. So let me write that down. Every tuple represents a pre-processing step on our data. Okay. So we have an imputer step named imputer. And the reason it has a name is just so you can reference it in the pipeline if you need to. So it has like a reference name that you give it. But this is the more important part is the actual scikit-learn object that's doing the processing. So in this case, a simple imputer. But notice that we have a secondary step, which is our scaling. Now this makes sense. This is something we should be doing to our features, is we should be scaling them. So here we say, okay, let's fill in any blanks first. By the way, order matters. So, and what I mean by that is the simple imputer is before the scalar. Now that's important because what that means is we should be filling in any blanks before we attempt scaling. So that order actually matters. We're going to fill in blanks first. In this list, that's first. We're going to fill in blanks, then we are going to scale, right? Then we scale, which makes sense, right? So we fill in blanks first, then we apply the scalar to scale our features. So those are our two steps. So pretty simple. We are building on our two steps. Now, this is just one piece of the puzzle. We are going to put this pipeline together with our one hot encoding that's going to be coming up next and build out our final pipeline. But this is a pipeline that has two steps that will actually be used with a larger pipeline coming up where we do one hot encoding to our categoricals, and then we put a model in there at the end to train and use for prediction. So pipelines can actually be composed is something to realize there is that we can have a pipeline that contains a few steps. We can have another pipeline over here that contains a few steps, and we can actually kind of put them together into a final pipeline that has both pipelines kind of merged together. Okay, so we're gonna see that coming up when we construct our final one. Our final one, as you can imagine, needs to handle this mapping of basically saying, let's do one hot encoding to these guys, and then do this pipeline here to these numerical features. That's what our final pipeline needs to handle, and it will. We're gonna build that out. But let me pause here. Were you guys able to run this? Are you with me on this pipeline here? Does that make sense? Those two steps. One is filling in blanks with a median, whatever column. So we're at, so this is what's so amazing about this is going to automatically search for nulls. And if you come across a column with a null, it's going to use the median of that column to fill in the blank, right? To fill in those nulls. Okay, great. Glad to hear. Glad to hear. Okay. All right. So we are going to now put this together with a column transformer to basically say what steps are going to be mapped to what columns. So now you can see what we're doing here is using the column transformer, which is going to be a list of tuples again. So this is another list of tuples. But the important thing is um, each tuple has a name followed by, so it has a name, which again is generic. You can say whatever you want it to be. So here we're kind of shortening this to numerical. This is short for categorical. But the important thing is it's followed by a pipeline slash step, followed by a pipeline slash step, followed by a list of columns that it applies to. So you can see that pattern here. What we're saying is we're going to apply that numerical pipeline we just defined. So this is saved in a numerical pipeline object here. We're going to apply that to those numerical features. So this is that list of numerical features here. So that's how we do the mapping. We have a tuple here that says, okay, apply these steps to these columns. Those go together in that tuple, right? Apply these steps to these columns, and then apply this step. Now, what is the step? This is a one hot encoder, which is going to encode those features, and it's going to ignore basically nulls for now. That's a choice, but it's going to ignore basically ignore nulls and skip over them for now. We know there's no nulls because we already did an is in A. from before, and we know there's not any nulls in that ocean proximity, so this isn't going to be an issue, but that's what that would do. But we have a one hot encoder here, which we're going to apply to our categorical features. Now, of course, that's just the ocean proximity feature. But again, you see the pattern in the tuple is apply this transform, which is a one hot encoding, to this column, apply these numerical transforms, which is a whole pipeline. So it's two steps in a pipeline of an imputer and a scalar are going to be applied to this. Really nice. So those are going to be all together in this column transformer, and that is our way to signal that for these numerical features, use these steps. For our categorical features, use this step. And you know, if we had more than one step we were applying to categorical, we could build a pipeline for the categorical and it would and do the same thing. We have more than one step here, and so it's good practice when you have more than one step to just put that in a pipeline. Because we have more than one step, we'll just put that in this list inside of the pipeline, and we can map that pipeline to those features. Here we only have one step, so it's okay to just put that there and apply that to the categorical features. But if we had more than one step, um, it would be good practice to put that in a pipeline, which is what we do here, right? This pipeline is being mapped to these features. This step is being applied to this feature. Okay. How about that? Are you guys able to run that one? Does that make sense? What we have set up so far? So we're almost there. We almost have our final pipeline. We have our pre-processing basically done to say our numerical features should be processed with that other pipeline, and our categorical features should be one hot encoded. We're getting close. The only thing we're really missing here is a model. It's the only thing we're really missing is to have our final model training pipeline is to actually include a model, which should come at the end, right? So we should be doing these steps first, then doing modeling, which we know, right? We've done that many times. We've done our pre-processing and then we do our modeling. Any questions on that? Okay, fantastic. All right. So if we wanted to see, if we wanted to test this so far, we could. So we could run the pre-processing and actually run a fit transform on our data. And this will basically apply that pipeline to the data. Now, this would be a sanity check. This is a good kind of, this is a good sanity check that our pre-processing works. So it's doing what we expect it to do. It's not our final pipeline because we don't have our model in there yet, but this is just to ensure that all of the features are kind of behaving as we expect. So we can do that and we can take a look at the results. This looks pretty good. This all of our numerical features ended up scaled, which is pretty good. And we have one hot encoded features for that ocean proximity over here. Okay, so this looks reasonable of those steps being applied to the right columns. But this is a good kind of sanity check to just run our fit transform on our data to ensure those steps are actually happening. And they are. You can see here the result of the scaling and the one hot encoding. So that all looks pretty reasonable, right? And what we should also do is make sure there are no nulls in this, which there shouldn't be because we did the imputer. So we should be doing is NA dot sum, and there is no nulls anymore. So that looks pretty good, right? Those got filled in by doing our steps. Our pipeline steps executed really nicely on our training data. And and we were off and running. And there's nothing unique about the training data. We could do this to our test data as well and verify that those steps are running, and they would, right? There's nothing really that special about running it on the training data. Um, it should also work on the test features as well, and it does. You can check that for yourself. Okay. All right. So that's pretty cool. We can verify all that's working. Any questions on that? We're almost there with our full pipeline. This is not the full pipeline, but this is something that will run during our full pipeline. Of course, our features are going to be transformed according to those steps, and then it will be put into our model to either predict or train with. Um, so let's do that. Let's actually build out our final model here. So it's actually going to be really easy to do. All we need to do is put in our model. So here we're going to import the ridge model here. Now we could use linear regression, we could use lasso, we could use elastic net. We're just going to use ridge uh, just to test it out. And we are going to now put in a final pipeline. So we're going to use our pipeline. And so we're going to create a new one here and map our preprocessing to our preprocessing that we've already built. So this is a column transformer that already has all of our steps. And then notice what comes after it is just the model. Now that's pretty basic, but it makes sense that it should come after that model. And of course, this is a generic name. We could name it whatever we want to. Model underscore ridge is pretty reasonable because it is a ridge regression. But of course, we could change that. Okay, so that builds out our final pipeline. So now we have a pipeline, and what's great about that is this signals that all of these steps should be completed prior to doing anything with this model. So all of those processing steps are going to run and then we're going to do dot fit or dot predict. And that's really great. It ensures that all those steps are running together every single time we call dot predict with this model. So we're just going to use the pipeline in place of the model to ensure that all of those steps are running together. And this is kind of our final pipeline that we would use with like something like dot fit or dot predict. So let me make that a note of that. Now we can use this final pipeline just like a regular model, i.e. pipeline dot fit or pipeline dot predict. So you could use it in either fashion. To train the pipeline would be this guy, and then use the pipeline to predict would be this. And what we should realize is under the hood, these steps are running first, and then we train it, or these steps run first, then we use it for prediction. Okay. Questions on that? Does that make sense on this final pipeline here? It's just now it's really cool because we have a pipeline made up of a pipeline, really, right? A pipeline made up of a pipeline. But that's Scikit-learn allows you to do that, to compose pipelines in this way. That's pretty normal there. Okay. What I want to show you is we can actually use this pipeline in a grid search. So that's pretty amazing. We can use this pipeline in any way we can use like a regular model. It's just that now our pre-processing steps have kind of been packaged together with our model to ensure that they always run anytime we do any processing with this model. Um, so for instance, we can do a grid search just like we did with a regular with just a model, right? With just this, we can do the same thing with the whole pipeline. So the only catch is that you want to make sure in your grid you name things in the appropriate way inside of your keys in your dictionary. So, for instance, um, inside of the grid, we're going to set up the alpha that would be used with this ridge regression by referencing its name. So this is model underscore ridge is the name of the model inside of the pipeline. So you want to make sure that goes first. And then what scikit-learn does is it recognizes parameters that belong with this model by using a double underscore. So you have underscore underscore alpha um, here. So the double underscore signals a parameter belonging to model ridge in the pipeline. Okay. So we have a model ridge is just a reference to the model in our pipeline. That's the one we're going to test out these parameters with. And underscore underscore alpha is just a way to say this alpha belongs to this model. Okay, it belongs, so it's going to be used with that model in our pipeline. Um, Otherwise, it's going to work exactly the same way. It's just we need to line up this naming convention of scikit-learn. You just have to reference this to whatever name you provided here, and then underscore underscore parameter. So L1 ratio, alpha, whatever, right, would go there. Okay. So there is a range from 0.1 to 2, step size of zero point 0.1. And then we do our grid search CV. So this is exactly the same setup as we had before. It's just that our model is now the pipeline. So our pipeline is going in there. We have our grid going in there. We have our scoring is the same, negative absolute error. We're using five-fold cross-validation and we're parallelizing that search. So we're going to search through these alphas and basically fit this to our data and find the best alpha. So it's going to try out all those combinations and try to come up with the best alpha. So it looks like the best alpha was 0.1 for the ridge. Okay, is the best. So then if we wanted to, we could then predict using the model, which would be doing something like this. Um, and we could also go back and do something like, so we could now use this param. So we could do model equals ridge, and then we could put in our alpha. Alpha is our results, our best parameters, and then we get that model ridge alpha, and then we just rebuild our pipeline equals pipeline, and then we put in this new model here. So we could do this. This would be going back and just putting in our best alpha here for this model and then ensuring that's part of our pipeline. So we're just overriding that pipeline with the best model there to get the best model in our pipeline. Okay. So that's all this is doing is just initializing a new, I can put this code in here. This is just getting a model with the best alpha and then reinserting that into we're just overwriting our final pipeline there with the best model that we have. So pretty cool. That pipeline can be used basically exactly like a model, right? It's going right here in the grid search and being used entirely like a basic model. So we do dot fit. Um, and that allows us to use it. We could do dot predict. We could even do pipeline dot predict once we could go back and do final pipeline dot fit with this, and then final pipeline dot predict with this and evaluate. Okay. So pretty cool. That pipeline can be used basically exactly like how a model would be. Any way we'd use a model.fit, model.predict, we can use a pipeline. So grid search is, for instance, something that can use a model in there. But instead of just a model, we're ensuring we have our pre-processing steps kind of bundled with that model in this pipeline. Any questions on this example so far? Were you guys able to run it up to here? Were you able to run the grid search? Okay, great. Okay. Okay, so this is just showing you what's actually happening underneath the hood is we're doing some scaling, we're doing some one-hot encoding, um, and we're doing some we're doing a model here, and that's all part of our pipeline. And then we can use the pipeline however we want. So for example, I know it's not here, but for an example, we could use once we have this final pipeline, we can use the final pipeline to predict. So we can do predictions equals final pipeline dot predict, and then we can pass in our test data. Now, what happens on this is once we have ran our pipeline dot fit, we have a trained pipeline. And then when we run this final pipeline dot predict, this data is going to be transformed. It's going to go through those transformation steps, and then we would apply our model to it at the end to make those predictions, and then we can evaluate those predictions, which is what we're doing kind of here, right? Okay. All right. So in conclusion, we have gone through a lot of stuff here. We've gone through regression. We've done the regularization on regression. So hopefully we have a good foundation on regression. What we're going to do in a little bit is actually do some additional practice with regression on a new problem. We're going to do a capstone problem and do some additional regression work with that. So we'll do that next. Um, but the other thing we learned is how to evaluate the regression using things like mean squared error, RMSE, which is the square root of that, which is really cool. So we have a sense of that error, which is our distance from our prediction to the actual value. That's always what these things are doing like this, right? This mean absolute error metric from Scikit-learn is computing the average distance from these predictions to these test labels that we have, right? Those actual values. And that gives us a sense of, on average, how far away are our predictions um, to see how good of a model that we have, right? And we should be evaluating that error generally against the scale of our targets to see, how far off we typically are. Okay, any questions at all on this lesson on regression? Anything we covered up to this point? We're gonna do some more practice with the next. We'll do the capstone. So we just do some more regression problems. Yeah, that's another bad score. It's a little bit hard to interpret this though because it's MAE. So one thing we could do is compute mean squared error and then take the square root of it to get the RMSE, which is a much better evaluation metric in terms of our target. So we could actually run that if we go back here and we could generate, for instance, we could generate the MSE, which is the mean squared error. And it's the same exact function of using our predictions. Um, and then we could just print that out, mean squared error. So we have mean squared error, and then what we can do is let's take the MP dot square root of that. So that way we can generate the RMSE. So yeah, that, I mean, that's pretty bad. That's pretty bad. Now let's go back and look at our data though. So let's take a look at the average for our Y. Remember, one thing we should be doing is taking a look at what our let's take a look at Y test dot mean to get an average value. So the average value is in the 200,000s. So this isn't awful. This is 70,000. It's still a decent amount of error. It's not as bad as the models we had before though, right? This is an average median price of the house is in the 206,000 range, and our error is off by like 70,000, right? So it's not good, but it's not like as bad as it's not as horrible as we've seen so far, right? This is a little bit better of a model, a little bit better. Closer to zero would be better, right? But the smaller the better. But remember, this is um, even the mean absolute error is technically in similar units um, as the target. So 50,000, 60,000 here, 70,000, it's still a decent amount of error in terms of 200,000. So far, we only come up with models and test their accuracy with available data. We haven't used a model to make completely new predictions on No, we haven't done that. Except we know how to do that. So to make predictions on new data would be exactly how we're making them on our available data because we actually do that all the time. If we go back down to our model building, um, it looks just like this, right? Where we take, so for instance, we do predictions all the time on test data that was never involved in the training. So it's as if this data mimics new data that we've never seen before. So if we had new raw data, it would be the same exact process. The new now with our pipeline, it makes it a little bit easier because with the pipeline the raw data will go through those transformations, which it should, right? The raw data should, because if it's missing data, it needs to be filled in. If it has categoricals, it needs to be one hot encoded. So that's the purpose of the pipeline actually is to make sure that if we're dealing with raw data, those steps can happen on the data before it goes into the model, right? So that's kind of the purpose of the pipeline is to ensure that we run those steps ahead of using a model with it. But ultimately, that's how any scikit-learn model is going to be doing the dot predict, even if it's a pipeline, right? It's going to be let's go back down here. It's going to be dot predict. It's always going to be that on new data. Yeah. Okay. Really good question. So, what I wanted to do next was do some practice. I wanted to go over to the capstone session 5. So, in this course, we have some more capstone sessions. So, if you have a moment, you want to pull up those capstone session materials, the incremental capstone session materials. We're going to be doing session 5 today. So this is just, remember, it's just extra practice that we do after we've covered some concepts. So we are going to do some regression practice now that we've covered regression pretty fully. And then this will be good practice before we head into lesson 4 on classification. So I just want to do this practice now while it's fresh, while the material is kind of fresh in our minds. Do you guys have the capstone materials? Do you know where to get it in your LMS? It's in your LMS and the resources. the capstone materials. You want to download that so you can get the data and the slides for the instructions, right? Or the PDF, I think, for you guys. But let me ask you, do you have those? We want to pull up session 5 if you have it. Thank you. I was just going to share that. Appreciate that. Yeah, so this is going to be session 5. You're also going to want the data that we're going to use with this, which is going to be the bike rental data set. I'll share that with you guys now. So we're going to be using this bike rentals data set for this capstone. It's the one we're going to build a regression model off of. Okay. So you should have that one from the capstones data sets as well. All right, so let's go through this. We are going to be doing machine learning here. So we're going to be doing, so we're talking about that kind of example product, that Aura product that was in our original capstone. And in order to do, make decisions, it's going to have to build some models. In this case, it's going to be doing some bike rental modeling, which is the data set we have. So we're moving away from that healthcare data set, going into this bike rental data set as an example of the capabilities here. So we're going to do this first capstone. After we do classification, we'll do this practice. After we do unsupervised learning, we'll do this practice on clustering. And then after we do recommendation, which is the last lesson, we'll come back and do practice with building a recommendation engine. Okay, but we're going to do this one today. And then we will do these other capstones as we go along. So this will be session 6, session 7, and session 8 later on in the course. Okay. Um, Okay, a little bit about the data. So in this capstone, we're going to be working with a shop, like a retail shop that rents out bikes, and they have data on a per day basis with actually on a per hour basis on the number of bikes that they rented in every hour. So maybe 1 hour they rented out 20 bikes, another hour they rented out 30 bikes, another hour they rented out 15. So they have that data here in the CSV. They have other kinds of data like the environmental data, like what the temperature was at that hour, the humidity, if there was snowfall, if it's a holiday, the wind, the visibility, the dew point, solar radiation, rainfall, what season it was, what day it was. Like the functional is like if it's I believe it's like if it's a weekend or a weekday, which would be non-functional. Um, so based on those features, we have a bunch of tasks. Okay, so we have based on the rented bike count, hour of the day, temperature, humidity, wind speed, rainfall, and whatever other features that are in the data set, we're actually going to build a model to predict the bike count required for every hour to have a stable supply of rented bikes. So our goal is actually going to be to predict the bike rental count per hour. And we are going to do that using all the features we have at our disposal, like mostly those environmental features and what day it is, those kind of things. Um, so we're going to load our data. We're going to do our usual checks. So check for any nulls, handle those missing nulls. We're actually going to practice converting our date because we actually do have things based on a date here. So we can convert it over to a date time object, extract different features from that, like the month or the day of the week. We're going to check correlation using the heat map. We're going to do some plots, some very basic plots. The focus is going to be on the modeling, so I probably won't spend too much time on the plots today. But there's some plot tasks in here, like the histogram of the bike count, the histogram of the numerical features, box plot of the bikes against the categoricals. Um, So we can do some plots like that from Seaborn, for instance. Seaborn category plot of rented by count against features like hour, holiday, rainfall, snowfall. So we can see how that stacks up against like different hours of the day, different holidays, rainfall, different weather events. Then we're gonna start building our model, right? So encode our categorical features, identify target variable and do the split, and then do scaling and do three different models. So we're actually gonna build a linear regression, we're gonna build a lasso regression, and build a ridge regression for the hourly byte count. And we're gonna see which model performs the best. Now, we could and should build this into a pipeline. So that could be something we practice. But this initial instructions actually doesn't require doing that. But I think it's really good practice to build our model. So we could use get dummies, like it says here, hint use get dummies. We could do that and build our model that way. But more practical would be doing the steps we did towards the end of lesson three, which is actually putting everything together into a pipeline. Right, that'd be more practical, and then fitting the pipeline and predicting with it for evaluation. So uh, we'll do that. I think we'll do that instead because I think that'll be more practical. The pipelines are really useful. So the things we'll have to do when we build our pipeline will be making sure we handle the missing values. So we'll want that imputer in there for numerical features. We'll want our one-hot encoding, very similar pipeline to the one we built earlier. And then we'll want to basically map those to the right columns using the column transformer. And then we'll have our pipeline ready to go for training and prediction, right? Okay. So those are going to be our steps. Any questions on this before we kind of get started on it? Okay. So let me go over to the notebooks and let me actually do a new notebook. And I'm going to name this uh, Capstone Session 5. Okay. So I'm going to come back here and reference the steps here. Okay, so the steps are to load our data set and basically check for nulls. So we should be pretty adept at doing that. We're going to import pandas as PD. And I need to make sure the data set's available. So I need to uh, load that here. So we're going to use our bike rental. Florida bike rentals. And then look at the first 5 rows. I got a decoder error. UTF-8 codec can't decode by in. One moment. I think we have an error in the data set. Was anybody able to get this to run? Hopefully they Or did you get the same error as me? Give me the same error. I think we need to set a encoding. Having other issues. What other issues? Sorry, I think this data is kind of corrupted. I may need to open it externally. Okay. Let me open it. There may be just a bad character that needs to be removed. Okay. Let me try a different, let me try something real quick. I think the data is needs to be updated. Oh, it saved it as the wrong file. One moment. Okay, let me try uploading this. Okay, there, that worked better. So let me give you the data. I think it was yeah, I think it was the degree code was giving it some issues. So I actually just removed it. You can do that, or you could just work with this one. I removed the temperature had a strange like degree symbol that wasn't being parsed. So I just removed that in this data set. This one should work. The one I just sent you guys should work. Or yeah, I guess you could try the CP1252 with the original data, see if that works. Did that work for you? Okay, it works with that encoding. So yeah, you could use that encoding or uh, remove that temperature degree, which is what I did from that. So I use that other data set. Yeah, that opens the data, but it's not in a data frame. Which is what we wanted in a data frame to work with our models and doing all of our yeah, like that opens the file. If it was a text file, that's fine, but it's not in a data frame. We want it in a structured data frame so we can use it. Okay. So one of those methodologies hopefully works. You can either work with the file I sent and read it like this, or you can use the encoding. Were other people able to open it once they change the encoding? Okay. Okay, very good. Let's see what we have. Let's do df.info. Let's see what we have, which is pretty standard step to do once we first load in some data. So we have about 14 columns here. We have a date, and then we have which is an object right now, but we're actually going to convert that over to a datetime object in a minute. We have our byte count, which is what we want to ultimately predict. This is the target variable in our data. Remember, that's going to be the problem, is to predict that hourly byte count. The hour of the day that we are producing that byte count is a feature. The temperature, which is in degrees Celsius, I removed that from there, but it was in Celsius. Um, and then we have a bunch of different features, which are uh, kind of Boolean, like yes, no holiday, holiday, the season. So these guys are going to be good candidates for these are going to be good candidates for um, doing our one hot encoding, right? These are probably the three that we should pick to do some transformations to for our one hot encoding. Okay. Everything else is pretty numerical though, so those should be fine to keep those. But they're just going to be good candidates for scaling, right? Really good candidates for scaling. All right, let's go back to here. And let's go back to the tasks. So we loaded the data set. We are going to check for nulls. It looks like there's actually not any nulls, so there may not be any imputing that we really need to do for this. But we can check. So we can use is NA or is null and then do the sum. It looks like we don't have any, so that's good. There's no nulls. That's pretty good. So we don't have to worry about filling in any blanks really. But that would normally that would be an important part of our pipeline, right? Is filling in any nulls. Looks like we don't have to worry about that here. That's good. So we can we can do the date extraction. And now one thing that we're going to do is create purposely for this, we're going to create a weekend or weekday feature. Okay, weekday or weekend, which should be really easy to do from the day of the week, which we should be able to extract from this from the date. Let's go back to, by the way, were you guys able to run this? Just want to make sure everyone's with me. Checking if there's any nulls, we did that. Okay. All right, so we're following along there. We checked if there's any nulls. Let's do our conversion. So let's do df date, and this is going to be pd dot to date time, and then df dot date. All right, and then let's sanity check that it got converted by doing info. We might need this format. Maybe we should do this. Okay. So that actually worked. Let's see. Let's double check the date. Okay. So that worked. It extracted it into the right dates. Some weird encoding with this. So it goes all the way up to 2018 from the very beginning data is in 2017, the beginning of the year, right? So and then the tail is all the way in 2018. This extracts the date. If you guys want to run that, are you guys able to run this to extract the date? Okay, perfect. So this extracts the date. By the way, the reason we need this is because our date formats are not uniform. They were actually in different encodings. So some of them had the year, the string was in a slightly different format where the year was last or the year was first. So if we do format mixed, it kind of rearrange, it kind of puts it in a uniform arrangement with the year, it's year, month, date, but it parses that out correctly. So we have year, month, date in there. But this strings were in a mixed format. So we put that argument in there to handle that case. Okay, so the reason we're going to do that is that we should be able to create a day of the week feature. So let's actually do that and add it to our data frame. So we should be able to create day of week, and we should be able to extract the df date, and then we do our usual dt dot day of week. Okay. So, and then let's see what that does. So if we add that, let's actually see, let's see what our new features are. So we add that, it should go on to the end of the data frame as the day of the week is a numerical day of the week. So this is the um this looks like a Thursday or no, a Wednesday. I think that's the third day. Sunday, Monday being actually this would be a Thursday. I think Monday would be 0. This would be Thursday. Okay, so we extract that day of the week. So it's just we're adding a new column called day of week, which extracts the day of the week from the date feature, the date time feature, uh, the day of the week. And we're verifying that here it's now a new feature called day of the week, which is a number. Does that make sense what this is doing? Yeah, it's a Thursday. So I think, yeah, Monday is 0 and Sunday is 6. So Monday is 0, Sunday is 6. Yeah, so this should be a Thursday. This first 5 rows is a Thursday. And by the way, the data, this is all on the Thursday. This is the different hours of the day. Different hours of the day. Um, And the thing that we don't know about this is the necessarily the time zone. So it may seem strange that like this is 0, which is kind of like midnight. It could be in a different time zone. So we don't know that necessarily, but there is 250 bikes, 200 bikes, 173. It starts to decrease over these hours. Just kind of notice that. Okay. So by the way, we should be able to create a new feature. So let's create the weekend feature, which is we can create using uh, weekend, and we can take our df um, day of week, and then we can just say, is this uh, greater than or equal to 5? Because that would be 5 or 6. And we're going to um, put this as actually, let's just leave it like that. That should be fine. Nah, let's change it. As type int. So let's see this feature. Let's see if this works. So this is not a weekend because it's a Thursday, right? So anything bigger than 5 would be bigger than or equal to 5 would be 5 or 6, which would be Saturday, Sunday. So we know it's not a weekend day. This is 0. Okay. So just creating those features there, and I can paste these in. Does that make sense what I just did? Any questions on that code? And this is important. If you don't have this, this will be a true or a false, but we want it to be a 0 or a 1. So when it's actually true, this should be a 1. When it's false, it'll be a 0. So we want it to be an integer rather than a true false. So that's why I have this part. That's why I did this here to make sure it's an integer. Good. Okay. So we're pretty much doing that, and we convert it to day and extract day. Um, let's check our heat map. Let's do that. So let's import Seaborn as SNS. So we're going to do our heat map next. Let me make a note of that. So we're going to do heat map, heat map. So we're going to do SNS dot heat map, and then let's do df dot correlation, and let's make sure we do numeric only equals to true. And then let's do annotate equals to true. So that we get those correlation values that are displayed on the heat map. So what this is going to do is create our heat map with our correlation matrix, where we're making sure we only do the numerical features, of course, when we do the heat map. Let's generate that. Um, okay, so we have some uh, pretty mild correlations. Now, the ones that are correlated are the temperature and dew point temperature. Those are pretty correlated. So I think we could argue that we should drop one of those, probably just the dew point temperature we could drop. That's a really high correlation, right? Right here. Let me draw it in red. That's a this one here, which is the dew point temperature against the regular temperature. That's super high. 0.91 is nearly a one-to-one correlation. So that's a good candidate to be dropped. One of those guys, I would argue probably the dew point temperature we could get rid of dropping, um, and just keep the regular temperature because they're nearly identical. Um, if you go down here, day of the week and weekend are correlated, and that makes sense. That's a pretty strong correlation because, of course, if it's depending on what day of the week it is the weekend or not. So we could go ahead and drop the day of the week column if we wanted to because we've already derived the weekend feature, which is a simpler feature. Is it the weekend or is it not the weekend? Um, so we could probably drop day of week and be okay. That's a pretty strong correlation. Otherwise, it's all pretty weak. I don't see any other strong correlations uh, necessarily. So that seems pretty reasonable. Is that we could get rid of this one, and we could get rid of day of week and probably be okay, right? Those are pretty strong correlations. Zero point 0.8 and 0.91, pretty strong. Okay, were you guys able to run that one and see the heat map? And does that make sense based on what I'm saying? So we want to run the heat map and pass in that correlation. We want to make sure we turn this to true to only do the numerical features, and then this to true to show the value on uh, the heat map. Able to run that one? Great. Okay. Um, that's a good question. Any recommendation on how to choose between the two? Uh, Not really. I don't think it really matters if they're correlated to each other, then um, including one of them should give you the same information as the other, especially if they're really correlated. So it doesn't really matter too much. Um, the way that I would choose is to think about, like, I'll give you an example. In this day of week versus weekend, um, we could, I would argue, drop day of week because the weekend is a simpler feature. It is 0 or 1, and that's directly derived from day of week. So it has less um, complexity to it. It's a little bit simpler of a feature, and I think that makes it easier to work with. Um, but the truth is that we could do both options and try them out and evaluate the results, right? So, well, to be truly thorough, what we could do is build a model where we've dropped this one and do the evaluation, and then go back and build a model where we drop this one and do the evaluation, right? So that's the proper way to do it, is to actually just build both models with each one dropped and see which performs better. Otherwise, I tend to prefer to go for the simplicity, whatever one has kind of a lower range. But the truth is, if they're really strongly correlated, it's not going to matter too much because they're going to give you the same information, right? Because they're so strongly correlated. Like if I in this data, like if I know the temperature, I pretty much know what the dew point temperature is going to be. They're so correlated. So it doesn't really matter which one I drop. But yeah, prefer to go for the simplicity. Okay. Going back to let's do this plot now of the distribution of the rented bike count. So that should be taking a look at um the rented bike count and then just doing a histogram and we can see what that distribution is. Most of it is less than 250. But there are some values that are really high, right? There are some days that turn out to be over 3,000 into the 3,500 range. That's quite a bit. But most of the days are stacked over here in this like 250 bucket. So by far that's the most, and then it kind of decreases from there. Most values are in that range, and then it kind of declines. So that should just be this simple histogram here. So this is the histogram. That should be a simple one to build. Were you guys able to run that one? Sweet. Okay. Pretty basic. Just showing us how it's distributed, and we kind of notice that most of it is in the 250 bucket or below. But there's a good amount that's out there beyond, like in the 500, 7,500, 1,000, um, all the way up to there's some days that register with a 3,000 and above, right? 3,500. So in fact, we didn't do this, but it might be worth doing, is we could look at the describe because we never looked at the maximum. Um, so for the bike count, there are some days that are 0 and the maximum is 3,500, 3,556. And the median is around 500 bikes. Um, the average around 700. So that's just our usual describe. All right, let's see what else. Plot the histogram of all numerical features. So let's do that. So luckily we have a shortcut to do this. If you guys remember, we have our SNS dot pair plot, and we can pass in our data is our DF. Right? So we can pass that in. So this is kind of this is a nice thing to run that will generate the scatter plots of all the features against each other, kind of like the correlation, but at the same time produce the histograms on the diagonal, right? So this should be a nice plot to see all the histograms in one kind of grid. That's just this one. Okay, so pretty, this is obviously quite a bit of data, but this is all the features against each other. Um, Look at this. I mean, a couple things you see right away is look at the ones that are really highly correlated, like the temperature against the dew point temperature. Do you guys see this strong correlation here? So that's a very indicative of a very strong correlation, right? That's the temperature against the dew point temperature. That kind of makes sense that it's that was the 0.91 correlation. So of course it's like that. Of course it looks like that, right? Just a very strong correlation. On the x-axis, or sorry, on the diagonal is all the histograms. They're a little bit zoomed out, so difficult to see. But um, we can get a sense of how some of these are distributed. Like the first one, uh, sorry, this first one, which is the byte count we already did. Um, Temperature, we can see how that's distributed. It's this third one. It's kind of evenly distributed. Left of dew versus temperature. This one, that one is the hours versus the dew point. So it's kind of evenly spaced out, which would make sense because this data is across 2 years. So you're going to get a lot of seasonal data in there, right? So it's gonna vary across like seasons. Yeah, so it kind of looks, it's very evenly spread out. Okay, were you able to get pair plot to run? Takes a moment to run. Takes a moment, but it produces all of these plots, including all the histograms. And again, if we wanted to zoom in on any one particular histogram, we could do that. We just have to basically copy and paste this code and swap out this feature. Just swap out this feature and we can get a zoomed in plot of any one of those features, like the temperature or visibility or whatever it is. So what I want to do, I think we'll take one more break here, and then what we'll do is we'll come back and just finish up our practice. I'm going to start building the model. I know it wants us to do some additional plotting, but I want to get to mainly the plotting elements, including doing the pipeline one more time. So we're going to do that. We're going to practice building out the pipeline in a similar fashion to exactly how we built the pipeline earlier. And then we're going to build our models and we're going to practice that coming up. I'll probably leave the plotting to you guys to do as kind of homework if you want to do that. Just because I want to get to the modeling.
And with that, we have come to the end of this course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.